the audience. For that reason, we will prioritize people who did enter the questions in Slido over people in the audience. And so please use Slido, and help the session chairs by, if you don't have a question, you can also look at the questions that appear in Slido and upvote them or make comments on it so that it can help guide the discussion. Because what we do is we hold all the questions for a particular session to the end so all 4 speakers can comment on the discussion. So if you don't have a question, help us upvote, because the session chairs might have to prioritize, and they will know which questions in Slido that everyone finds most interesting. Thanks.
All right, welcome everybody to day 2 of Punch 4. So I've got just a couple announcements, and then I'll hand it over to the chairs of this session. First of all, I mentioned yesterday we have bathrooms down here on the first floor. We also have all gender bathrooms. They are on the 3rd floor, up where the outreach team is meeting. So you just go up the elevator, follow the signs to 3131, 3150, and in between those 2 conference rooms, there are 2 all gender bathrooms. Second of all, rides to airport. We are just informally gathering information about people who might be driving to the airport tomorrow and might be able to give other people a lift, or people who might need a lift. And you know what? And Carrie Dawn told me how to organize that, and now I've forgotten, Carrie Dawn, what you said. See Carrie Dawn in the front desk, and that's how we do this. Perfect. Okay. Next, today's schedule. We have, just like yesterday, however, we do have a poster session from 1 till 2. So we're going to have lunch from 12 till 1 and the poster session from 1 till 2. And the other thing that Carrie Dawn let me know is that all of your e-posters are now online, and you can get to them by the agenda. You can get to the agenda by the UCAR code on here, or through the punch page or the CPAS page. Also, the schedule tonight, we have a reception which will be serving food and alcohol from 5:30 to 8. And we're looking 8 o'clock, right, Carrie Dawn? That's the end of it. So that's it. Have I forgotten anything? All right, wonderful. Well, let's get started. So without further ado, let me hand it off to Heather Elliott and Sherilyn Morrow, who are the chairs for today.
Okay, our first speaker is Nikki Weil, and the title of her talk is Mesoscale Solar Wind Structures, Origins and Variability.
All right, hi everybody, good morning. Thank you for all getting up early, or not early if you have Oliver and Violet with you who got up at 6. I come from and where they go. Okay, so I'm the mission scientist of Punch, and I'm also Working Group 1B lead. Working Group 1B is about determining how much and what types of mesoscale structures are of solar origin, that means they come from the sun and survive all the way through the inner heliosphere, versus how much are developed en route. And we had a whole session yesterday about the ones that are developed en route, and turbulence is, the main way that we expect that to happen, and other dynamics. So answering this question of Punch 1B is important for understanding how the solar wind is formed. That's where those mesoscale structures are coming from, the ones that come from the sun. And then the ones that turn into turbulence, that provides critical insight into the energization, the kinetic energy, how that cascade works. And then ultimately, it's also important for space weather, because this is the variability that drives the magnetosphere on a daily basis. So in contrast to what Phil said yesterday, where he said that the regular solar wind does not cause space weather, it doesn't cause big space weather, but it still causes a lot of space weather. All right. Okay, so here's some examples, and I'm totally being biased here in talking about the mesoscale structures that are created by magnetic reconnection. And I'm showing some examples here because there's actually an enormous range of ways that magnetic reconnection manifests in the solar atmosphere. And they all make structures that go out into the heliosphere. And I'm showing some examples here. Okay, let's see if I can do this. Ooh. Okay, so on the left is an example that might be nanoflares. This is from Craig's paper in 2014 looking at downflows in core 2. We talked about it a little yesterday in the session on the alphane surface. Because any downward flowing waves or flows tells you where the alphane surface is. Anna Tenorani showed that these velocities and the velocity profiles and deceleration profiles are most consistent with actually a reconnection event. And there are lots of other examples of nanoflares too. So we know nanoflares is something that happens, but those are very small scale. In this case, we're probably talking about open-open reconnection, so component reconnection. In the middle here, I'm showing an example of jetlets. So jets and jetlets, and we're going to hear more from Noor and Alphonse and Radislav, and I think Samaya has a poster out there too on jets and jetlets. So these are all other ways that magnetic reconnection injects structure into the heliosphere. Of course, this is a very different magnetic topology, and it's a lot lower down where this is happening. This is yet another one, helmet streamers and blobs. We also talked about those a little bit earlier. These are like 1,000 times longer coronal loops. So again, very different magnetic topology taking place, but it's still magnetic reconnection that happens on those very last long closed loops, sometimes interchange reconnection, sometimes pinch-off reconnection. But either way, you make these structures that go out into the heliosphere. And of course, on the even bigger scale, you have stealth CMEs, which are kind of actually just like a giant streamer blob, and then of course, the really big flares and CMEs. This is super awkward, guys, this pointer. Anyway, the point is, in terms of magnetic topology, these are all vastly different ways of magnetic energy storage and release taking place on the sun. But they're all imprinting structures in the heliosphere, and they're all imprinting structures that Punch will be able to see. Some of these are small-scale flux emergence versus big-scale flux emergent, differential rotation, supergranulars. We heard about that from Bill yesterday. The amount of energy released is vastly different between these two. I think the energy released, like in these little nanoflares, probably pretty small, but like these jets, there's a lot of energy in those. There's not much energy in the helmet streamer blobs, but a lot of mass in those. So really different in terms of the topology and the consequences. And also the periodicities. The jetlets and the helmet streamer blobs have particular periodicities that tells us something about their formation, as opposed to random events, which these other ones are aperiodic. Okay, just to say one more thing about jets and jetlets and plumes. Jets and jetlets are known now to be related to plumes. These plumes are these structures up here that we see high up, especially during solar minimum, over the poles. And we can see them here in LASCO C2. And then I'm showing this image over here, which shows you what Punch is going to see. The jetlets and jets occur way down here. We're not going to see those directly. But Punch's view is up here, and we're going to see the consequences and these plume structures which are associated. All right, that's backwards. Okay, so mesoscales in general are, as I said, injected and imposed from the sun, from these and other processes. And then there's also evolution and round. And this was a paper that we did a couple of years ago, sort of summarizing all of this. And we put some sort of things, phenomenological things here on the side to give people context. Large scale are the things that we have always known are there, like CMEs and SIRs and things. There's things that develop en route and things like periodic density structures that survive. What I'm showing here is that right in this mesoscale range is where you actually have both things. You have things that come from the sun and also turbulence and new things developing en route. And so there's this competition of the two. And that's actually exactly what Working Group 1B is trying to understand. Because we know they're both there, but the question is how much? How much of each and how do they interplay? And this over here is meant to show the reason we don't know the answer right now is because remote images don't go low enough in their sensitivity and their resolution. And in situ, we don't have the breadth to actually be able to watch structures like that. But, dun dun dun, Punch is going to fill in that gap because it has the coverage and also simultaneously the resolution, the sensitivity, so that we can watch the structures as they advect through the heliosphere, watch new ones as they're created, watch the interplay between those processes. All right, so I said this earlier. One of the reasons that we care so much about these mesoscale structures, of course the underlying physics, but also because getting them right is important for the impact on the magnetosphere. And this shows you why. Here is that image we've been showing over and over again of the deep field resolution from Stereo Core 2. And I'm showing here the zoom in of this little upper corner right here. And that blue dot there is the dayside Earth's magnetosphere to scale. And so you can see just why we have to get all of these structures right, both within CMEs, CIRs, and within the ambient solar wind. Whether you hit one part of the CME or the other part, you can see that would vastly change the dynamic pressure that's impacting the magnetosphere. And that's what we're seeing with punch. We're seeing dynamic pressure because it's density. Okay, so here's an example, a cartoon example, of a series of periodic density structures or periodic dynamic pressure changes and how they will compress and relax the magnetosphere and drive ultra-low frequency waves in the magnetosphere. They actually drive radiation belt dynamics. And we know this happens, and I'm showing an example on the right of this happening. And I sort of alluded to this already. We know now actually that there are a couple of processes in the sun, in the sun as it creates the solar wind, that make periodic structures. Not all of them, but some of them. And so what I'm showing here is an event from a long time ago, actually from 1997, where we saw in upstream L1, we saw the solar wind dynamic pressure go up and down and up and down. And then we saw in the GOES magnetic field, which is here in the magnetosphere, we saw the magnetic field get compressed, relaxed, compressed, relaxed. And not just at random frequencies, but when we take the Fourier analysis of it, very precise frequencies. There's sort of a 20-minute frequency, there's a 1-hour frequency, there's a 10-minute frequency, and a 6-minute frequency. And I'm showing an example, but we've now done years and years of wind and GOES statistics on this, and these frequencies show up again and again. So this is a 20-year-old mystery that people were seeing this interaction and saying, but why would the solar wind have these periodicities in the first place? And we speculated probably something from the sun. And I actually went back and pulled out, Larry found one of the first events. There were a couple of groups looking at this, a group in Italy and a group in South Africa. And I pulled out Larry's paper where he found one of these events. And he actually speculated that it came from polar plumes. And he referenced a Craig DeForest paper from 1998. So that was a fun thing to remember. But at the time, remember, we didn't even know that plumes were related to jets or jetlets. And so the relationship to exactly what was going on and could it survive to the Earth, this was totally speculative. Okay, but we know more now because it's been 20 years. Okay, so first of all, that lowest frequency, we are sure comes from the heliospheric current sheet and the helmet streamers. And we're sure because we see it in Core 2 in the stereo data. That's what I'm showing here, is a series of blobs coming off. And this is actually just one blob. It's coming off, and then there's one behind it. So it's a time series of images, and you can see the blobs coming off. And we've done statistics on those blobs, and they come out characteristically with a time scale of about like 1 to 2 hours. So we know that that structure is coming from the current sheet. And in fact, Irina Gershkovich went in and looked at 14 years of ACE data and counted up all the times we saw these in elemental abundances, and she found that we were seeing them in situ at 1 AU in elemental abundances, which means that they came from the sun at this characteristic 90 minutes. All right, I'm just showing that we're seeing it in WSPR too, which is pretty cool. And actually the key thing here is this spectral analysis tool that we have to robustly identify the background and also pick out discrete frequencies on top of that. It's open source, and it's really crucially, Simone Di Matteo made it really user-friendly. My version was not. Simone's made it very user-friendly, and he will help you learn how to do it. So contact us if you want these tools, because we will help you learn them. We've also looked at the high cadence images in WSPR, and we're starting to see evidence of those smaller frequencies. We're really pushing the limits of the WSPR data, though, here. This was way beyond the specs of what, the requirements of what WSPR is supposed to do. But what I'm showing here is in these very high cadence runs that WSPR has done, we are starting to be able to pull out some of those higher frequency periodic density structures. And here's just a series of the high cadence images, and you can see a little blob, a little one, and we followed it all the way out. And when we do periodicity analysis on these, we are able to pull out, here I'm showing a histogram where we pulled out a couple of different encounters of these special high cadence runs that WSPR has done, and we found some of these higher frequency waves, higher frequency periodic density structures showing up at about 5-10 minutes, those kind of time scales. We can't do statistics yet because we just have like a day here and a day there is all. 3 minutes, I know, Sherilyn, I'm hurrying. Okay. Okay, so here, the latest thing that we've done, though, is we've taken 25 years of wind data at L1 and looked at the alpha to proton ratio, which, because that's an elemental abundance ratio, you can tell then which structures maybe were formed en route versus which ones came from the sun because they are showing up in the elemental abundances. And I'm showing the distribution over here on the right, the observed distribution that we see. And we get the one at 90 minutes, and that's a separate distribution, actually. And then we have this broad distribution between 1 and 4 millihertz. And if you compare that to some recent analysis of transverse alphane waves that they've seen in COMP and AIA, and you just look at their occurrence distribution of transverse alphanic fluctuations, and what we're seeing in counting up the occurrence distribution of frequencies at ACE, at WIN, they line up pretty well. So this is what we speculate. We speculate that there are two sources of periodic density structures coming from the sun. One of them is these current heliospheric current sheet ones. There are a couple of ideas. One of them is that it's actually the tearing mode at the heliospheric current sheet that makes these come out at this sort of 90-minute periodicity. For these other ones, these 1 to 4 millihertz ones that are very suspiciously near these sort of frequencies and also the frequencies seen now in jets and jetlets, we speculate that those are also magnetic reconnection, driven reconnection, but this other process where you have either pressure pulses from below causing the structures, or you could also have these transverse waves at null points and separatrices forcing reconnection periodically. And we think that's what's going on over here. And I'm putting the Nyquist plotted on here. It's right here. It's unfortunately right in the middle of the range of the occurrence distribution. But we will get a good portion of these structures, and definitely we're going to get these structures with punch. Okay, so that is my conclusion, is that because of punch's signal-to-noise ratio, resolution, field of view, we are going to have a measurement of a multitude of solar-created structures. We're going to be able to watch them as they advect through the heliosphere. We're going to be able to watch them as they interact with turbulence and other structures, and we're going to see how many of them really survive through the inner heliosphere. Is that good? Should I end up time?
Thank you, Nikki. Our next speaker is Alphonse Sterling from Marshall Space Flight Center. The title of his talk is Review of Coronal Jets and the Jet Heliosphere Connection.
Well, I'm proud to be, along with my friend here, one of the last mask holdouts. Okay, let's, Nikki. There are a couple of things that you're more familiar with than I am, and that's the periodicities regarding jets, and also this strong connection between jets and plumes. So anyway, I'll tell you some things that I do have some idea about. A lot of this work was done with Ron Moore and Navdeep Panesar. Okay, so anyway, basically coronal jets, they've been around for a long time, at least since Yoko. Shibata et al. Saw them in '92 and talked a lot about them. And Yokoyama and Shibata worked a lot on models. And other good friends and colleagues have done a lot of excellent work early on. Ralphie et al. Did a nice review, and there are some other reviews out there. So just to give you a footing, in polar coronal holes, these are from Hinode measurements in the X-rays. They can reach about 50,000 kilometers in length, and they have a width of about 8,000, 10,000 kilometers. And their rate, if you just count them from those X-ray images in the polar coronal holes, the two of them, then they're about 60 per day. This is from Savcheva et al. And they have a particular structure, which I'll talk about in a moment. Many jets show a twisting motion as they're lifting off, and the rest of the things I think I'll get to. So here's some picture of some of them. You can see 17 there and 18, and that's a very faint one there, 19. Anyway, this is looking at X-rays at the limb, and you'll see here, with that, those over there, there's a spire there, but then there's a bright point. This doesn't work well with this color table, but there's a bright point that is often asymmetric with the spire. It's off to the side. So let's see, we can see that more closely here. On the left is an X-ray image from Hinode XRT, and you can see the spire there, and you can see this bright point off to the right of it at the base. And we think that's key to what's causing this thing. So in X-rays, you don't see much besides the brightening there, but if you look in EUV, you see from that place where the brightening is, you see this absorption feature lifting off. And it looks like a filament lifting off, and just gets there and it gets entwined in the vertical field, and it goes out along that field. So we think this is just a normal, everyday eruption. This is a nice, EIT or something, filament eruption. It takes off. It's beautiful, of course. But, it leaves, and then in its wake, it leaves the flare. Okay, we've all known that since we were little toddlers, so that's the way it works. Well, apparently the same thing is happening with jets, too. This is a picture he put together for it. So here, basically, this is a picture in a polar coronal hole. It can generalize to more, to other regions. But the field is open on the left-hand side. It's all negative. But there's this intruding positive there. It's just there, and it gets in the way. Well, what does it do? This positive is there, and then it spreads out to the negative, and it fans out like a flower. This is a cross-section of it, so it looks like two lobes. One side of this lobe, one side of that has more potential, more energy built up in it, and the field is wound up, and it holds a filament. That filament gets kicked off by some magic, which I'll talk about in a moment. And when it does, it makes a normal flare right there below it. The reconnection, just like in the previous EIT movie. And that's the bright point. But then, if you follow the fields here, you can see that when it reconnects up here, it's going to be oppositely, pointing, so it can reconnect. And that leads to this bright, hot stuff coming out. And then eventually this field around the filament gets eaten away by this reconnection, and that cool stuff can flow out along it too. So that's what we think is happening with these jets. They're nice simulations by Wiper et al. And Farid et al. So what causes these mini filaments to leave their nest down near the base of the sun? Well, several studies have found flux cancellation to be active. And then there's some other things. There's some emergence plus cancellation, but we usually find cancellation of the work we do. And Kumar et al. Talk about shearing motions are to be more important than the cancellation. But anyway, getting together and coming close, and in some cases, certainly at least, cancellation seems to be it. So here's a on-disk jet, and this is looking in AIA, and so you can see the mini filament erupting there. Well, these are, the red and the green are the magnetic field elements, and these elements here are close together, and if we follow these over time, we see that they come together, so that movie I just showed you was, I don't know, like a half hour or something, and this is several hours. So over several hours, these fields come together, and there's cancellation, and just at about that time, you get the jet. And we've seen this for numerous jets. We have cancellation rates and all this business too. So anyway, that's the basic picture that we have for how jets are formed down in the low atmosphere. Now for this audience, of course, I want to talk a bit about the heliospheric connection. Well, there are at least these three I can point out. There's CMEs and outflows, and I'll talk a little bit about these white light jets, aka narrow CMEs. They can also make broad CMEs. I'm not going to talk about that here. I'm also not going to talk about this, but it's interesting. Bernie Jackson and company with you et al. Have used SME to see the consequences of jets far away in the heliosphere. Okay, plumes. So there has been talk of plumes. Let's see, let me read what I have here. Small scale jets occur both in, so there are these small jets, which we call jetlets, and they occur both inside and outside of plumes, which I'll talk about a little bit. And some jets may actually start plumes, which was mentioned by Ralphie et al. In 2008, and we saw an example of that in Pucci et al. 14. Then some recent ideas, I guess I'll talk a little bit about like switchbacks, and what we think about that. So anyway, what about this jet and narrow CME connection? So we've seen this also with like polar region jets too, and that goes back to Yiming Wang's work et al.'s work in about 98 or so. But I'm going to talk about here, this is an active region, on disk, active region, jetting region. So you see all these things shooting off there like they're losing their mind. One of these large ones, I'd have to trace it, maybe it's that one, I don't know. But one of these we looked at in, this is core 1, core 2, I guess. One of the cores, that's core 1, I guess. So anyway, we see here that jet right there. We can follow it out right there. But then we go to core 2, and we can still follow it out, which is nice. This is, from stereo. So, but also, we can continue this. This again is at the same core 2 on the left, but then, so there it is in, let's see, where's that baby? Right there. But we can see it in high 1 also. So we may have to trace it down, but we can follow it out there. So they do get far away. And then, as I say, you et al. Have seen evidence in SME data for them to be very far away. Okay, switchbacks. We all know switchbacks from the Parker Solar Probe observations, and of course they're coming out from the sun, and the magnetic field is nutso for whatever reason. But, and probe goes through it and sees this switching of the field. So what I've talked about now is these jets being launched. Let me get to our picture again here of this. So I've talked here about this mini filament erupting out. Well, here there are circles around in this field that I've drawn of the mini filament. And that's because we suspect it often has twists. So the flux cancellation of non-potential field builds up a fluctuate. So this thing has twist, and we often see jets untwisting as they're lifting off. Well, this is from a Ron Moore-led paper, but when this thing lifts off carrying that twist, it can impart that twist onto a vertical flux tube that it reconnects with, according to an idea of Shibata and Uchida. So this upper field gets that twist, and that twist leaves out. Well, what happens when it continues to go out? Well, it's going to move out at about the Alfvén velocity. Well, what's that? Near the sun, it's about 1,000 kilometers per second in the corona. And out at Parker, it's about 100 kilometers per second. And so it must go down. This packet, this Alfvén packet is large. It is about a radius, solar radius. So this feels a slower Alfvén velocity than this down here, so it can scrunch up as it goes out. So this might contribute to making the switchbacks. So how about on smaller scales? If you just look at the jets, there aren't enough. You take Savcheva et al.'s 60 per day, multiply by the area of the sun, and you still get a few hundred. It's not going to do much. Can you explain all this solar wind and all this business and jetlets? Well, and switchbacks. Well, jetlets occur on smaller scale, and this is iris observation, but we can also see these jet-like things in AIA also, but you know, they're harder to see, they're small. They would evolve more rapidly. But from Panesar et al., Navdeep looked at the magnetic field of these, and there's cancellation going on with a handful of these that we could see well. Not all of them, but it's just hard to see them. So we think the same process may be going on. And I will say that Noor first found the jetlets under polar plumes, and Navdeep found that they're more general in the general solar network, edges of the networks. How about down to spicules? Well, this is wonderful observations from Samantha et al. From Big Bear, and they occur around the solar network. We've known that for a century. Well, with these observations, we were able to see that the roots of a lot of these seem to be where there's magnetic interactions going on, cancellation and or emergence. So the point is the same processes may be going on with some percentage of spicules. If we plot the rate here, if we plot the size of the erupting feature, the mini filament or filament, and we count the number on the sun, then large eruptions, if they're all the same thing, large eruptions have large filaments and very few of them per day or whatever. Jets, they're 10,000 kilometers wide, and there's a few hundred per day. We do not see mini filaments or microfilaments in spicules, but we speculate they might be there for this work. If they are, we guess what the size would be, about the size of a spicule, the width of a spicule. And we know the number of spicules because between H-alpha observations and satellites, people have nothing to do except count spicules. So there's this number, and you can plot this line, and it seems like it allows that some percentage of the spicules could be made by this mechanism, from a small percentage to almost 100%. But we don't know. There's a big range there, but it's plausible. Okay, and if all of these things are going on, they might contribute a lot to the solar wind, but again, that's speculation. So I think we're approaching a good understanding of coronal jets. At least many of them are like this small-scale eruptions. They can reach the this jet physics scales to different sizes, and they might be the source where PSP observes switchbacks and other things. And if you come to the SPD, I'll talk about some very, very small-scale outflows that seem to be from very inconspicuous jets. Thank you. Okay, that's that.
Alphonse. Our next speaker is the Parker Project scientist, Noor Rawafi of Johns Hopkins Applied Physics Laboratory. His title is Magnetic Reconnection and Jetlets as the Driver of the Solar Wind.
Thank you. So here I'll be reporting mainly about one, but there are two other papers, the Stuart Bales paper that appeared in Nature 2 or 3 weeks ago, And there is a paper that is on archives also by Jim Drake. We are basically arguing about the same thing, that is about magnetic field reconnection and what it does to thermodynamics of the plasma and the solar atmosphere. So the two big questions that we really want to answer, and Parker Solar Probe, that's probably central to its science objectives, are the heating of the plasma and also the acceleration of it. But if you think of it, this is the same problem. You cannot explain the heating independently from the acceleration and vice versa. You have to explain them in the same time with the same physical mechanisms. So the solar wind. This is iconic, and from Dave McComb's paper in 2008, we have the fast solar wind that during solar minimum at least is coming from the polar regions, and it is pretty steady. On the other hand, the slow solar wind that is around the equator, it's highly variable. They also have different composition, by the way. When you go to solar maximum, it's just chaos, and you have streams that are mixed all over the place. The nice thing about the fast solar wind, as I said, it's steady, it is alvenic, and we know where it's coming from. It's the open field regions that are coral holes. The slow solar wind, on the other hand, the source of it is not very clear. And when you look in the literature, people argue about the boundaries of coral holes, active regions, quiet sun, etc. But in reality, we don't really know. We are not, we didn't settle that question yet. So what I'm trying to address here today is what are the physical mechanisms that will get solar wind going in the first place. These are extremely important if you can figure them out. And the second thing also, what is the nature of the wind? We know when you measure it far away from the sun, it's like a continuous flow, physics completely. And answering this question is extremely important. The third question, obviously, which is the most important one, is how to get the plasma to escape the gravity of the sun. So here I'm reasoning by elimination, basically. When you look at solar maximum, you have, as you said, a mixture of streams higher up in the solar wind. And you look at the sun itself, you have active regions, you have quiet sun, sometimes you have coronal holes. But when you look at solar minimum, in particular at the periods where the sun is extremely quiet, we basically don't have active regions at all. But we still have the solar wind. So by elimination, that tells us that active regions are not the primary source of the solar wind. The main solar wind should be coming from elsewhere. I'm not saying that active regions do not contribute to the solar wind. They do, but they are not the primary source of it. So when you look around during these periods, what you see there is only small scale features. And by small scale, and Nikki and Alphonse did really an excellent job here. So when you look at the magnetic field, what you see lower down is I'm not sure what is the pointer here. You see the chromospheric network. You see the boundaries there of the supergranules, and that's basically what we see on the solar surface. At these boundaries, as Alphonse was describing earlier, you see quite a bit of activity there. And here I'm showing a movie of X-ray jets, just to put them in context. But we see a myriad of activities like spicules, like jets, jetlets, etc. And higher up, obviously, you will see plumes that Nikki talked about earlier that we see mainly during solar eclipses. They are so prominent at the poles during solar minimum. Now, I'm going to Parker Solar Probe here, and Parker Solar Probe gave us hints that we didn't have before, and that basically guides us toward the source of the solar wind, where it is coming from. One of the observations that have been talked about for the last 5 years, and by the way, we will be celebrating the 5th anniversary of the mission, thank you, in about a month from now, so it's going fast. So one of the main observations that Parker Solar Probe gave us is the switchbacks. And by the way, switchbacks have been observed back in the 60s. but they were so rare in the solar wind. What Parker Solar Probe did, Parker Solar Probe showed us a gazillion of them when you get close to the sun. But there is another property that is so important about them. They come in groups that we call them patches. And to me, the patchiness of the switchbacks is way more important than the switchbacks themselves. And what Anais Farjat and Stuart Pale found in 2021, that the scale size of the switchback patches is comparable to the scale size of the supergranulars, which is about 30 to 40 megameters. That basically gives us a hint. Probably the switchbacks they may not be coming from there, but at least the mechanism that is creating them is probably lower down there. There is another thing that Parker Solar Probe gave us. Most of the wind that we observed close to the sun is alvenic, whether it is fast, slow, extremely slow, most of it is alvenic. Obviously, when you go to 1 AU, most of the slow wind is not alvenic. But the hint that Parker Solar Probe is giving us is probably the physical mechanisms that are giving birth to the solar wind are the same, regardless whether it is fast or slow. That's why we have this alvenicity that is so dominant close to the sun. Now, I'm trying to think down what is happening in the solar corona, and this is an image from the Solar Dynamic Observatory. By the way, this is not a raw image. We still processed it a little bit. It's better than the raw image, but it's not processed deeply. But with what you can see off-limb here, now I'm ahead of myself, what you see off-limb here, we don't really see much at all. We don't see much dynamics. But the reality is revealed when you do deep processing of the images. And let me move forward to the next slide. And this is just a zoom of the previous movie, just on the solar poles. And you see the amount of dynamics you see off-limb here. This is jets, but they are very small. Alphonse talked about the big jets, the typical jets that I showed earlier as well. But these jetlets are very, very small. And when you look off-limb, you see them very clearly above the solar poles, but you see them elsewhere as well, in the closed field regions as well. And the funny thing about them is that when the sun rotates, you keep seeing the same thing all the time, meaning they are occurring everywhere at the base of the solar corona. The other nice thing about them, they don't care about the solar cycle. It's exactly like the solar wind. Solar wind is ubiquitous. Regardless of the solar cycle, we always have a solar wind. The other thing also, they are very hot. That's the heating part of it. So the other thing also, when we looked at this type of movies, the impression you get is that you are probably seeing a flow that is rising from the base of the solar corona. But there are issues there. We have to look into them, whether we have enough jetlets, whether they can provide the mass that is sufficient to power the solar wind. And the other thing also, whether they have energy to beat the solar gravity. So before going into the numbers, this is also going into the numbers. So what is the driver of this jetting? Alphonse earlier showed very clearly, and Nikki as well, that when you look at the big jets, they are driven by magnetic field reconnection. That's settled. We know that for probably a couple of decades now. But now the jetlets, they're exactly the same thing. And when you look at the magnetic field, but this is very, very high resolution. This is 0.2 arc second from the Goody Solar Telescope and the Big Bear Solar Observatory. And this field of view is about 70 by 70 arc seconds, and we had 90 minutes of continuous observation. Over this hour and a half, we had over 1,400 constellation events. About 60 of them are rooted in the network, like here, like this element here. And some of them, I think about a handful of them gave jetlets. Well, you can say 7 jetlets out of 1,400 is very small, yes, thank you. But that's actually, when we work out the numbers, is pretty good. So you work also the energy budget of the jetlets, which is the number there, 10 to the 22 ergs per second. Also, their how much particles they contribute, they put out there into the solar wind, which is about 10 to the 35 protons. Now, another piece of evidence that is supporting this jetting in the solar corona, and this is higher up, this is measurements of Parker Solar Probe. You take the encounters, and this is the speed that we measure during the encounters. And what you do, you draw basically a line tracing the minimum speed we measure around the encounter. And you do it for several of them, and after that you plot all the velocities as a function of distance. And what we found is that, this is from a paper that Stuart is working on now, that the baseline, the lower boundary is basically like a Parker wind. But above it, it's dominated by jetting. Jetting is so huge in the solar wind. Before going into that, into the numbers and whether we have enough jetlets to power the solar wind, the nice thing about this reconnection that is ubiquitous everywhere in the solar wind is they can give you basically mechanisms to explain whatever Parker Solar Probe is observing as far as the switchbacks are concerned. The interpretation of switchbacks, basically you can put them in two classes. One of them is they are originating from the corona, and that is mainly reconnection. And if we are token reconnection, the jetlets are the prime example of reconnection. So that's kind of, it's just common sense. But when you go higher up, there are 2 or 3 models that are arguing for in situ formation of the solar wind, and all of them, reconnection will provide the ingredients you need of them. If you take, for example, steepening of Alfvén waves, like Alphonse showed earlier, yeah, you have to have Alfvén waves coming from lower down. Then when they propagate higher up, they will steepen and they will give you the switchbacks. Bill yesterday talked about shears in the solar wind that will also create switchbacks. Yeah, the jetlets by nature, they are impulsive. They will give you shear in the solar wind. Same thing for what Alphonse argued earlier, and also the Nathan Schweder and Dave McComas. Now, let's work through the numbers. I mentioned earlier that we got 7 jetlets in 90 minutes from 70 by 70 arc second. You can extrapolate that to the whole solar surface, and what we found that we come to a rate of about 5,000 jetlets that are occurring at any given time on the whole solar surface. But when you work the energy budget for a given typical jetlet, that I showed the number earlier, you need only 2,000 jetlets that should be active at any given time to power the solar wind. So you may argue that, yeah, you have over 2 times what you need. That's not a bad thing. It's actually a very good thing, because not all the plasma will make it to the solar wind. There will be a selection effect. Some of the plasma has to fall down back to the sun. And I think Greg showed some of that higher up in the corona, but we should see it also lower down. So in terms of the number of the jetlets, in terms of their energy, and also the mass flux they provide to the solar wind, we have what we need to power the whole solar wind. Now, do we have enough speed to beat the solar gravity? That's actually the paper of Jim Drake. He said, yeah, when you have a jetlet, from the get-go, you start with a super Alfvénic flow. So you need very little energy to get it out. And that's actually probably is the key to explain the solar wind. Now, see, this is basically the takeaway from what I showed here, that the magnetic field reconnection is ubiquitous at the base of the solar corona, and it is the driver of the thermodynamics in that area. And it also provides the energy that will keep the solar wind going, and it keeps it hot in particular. But this is what we think. And this is going to be controversial. And it's what we think is everything is done at the base of the solar corona. What is happening higher up is basically just maintaining the wind going, keeping it hotter, keep additional heating, and also a little bit of acceleration just to keep it going. Now, how we got to this? Parker Solar Probe. I think without the observations of Parker Solar Probe, I'm done, yes. Without the observation from Parker Solar Probe, I don't think we would be at this point. But Parker Solar Probe basically guided us to what we are doing here. Thank you very much.
Session 5 this morning is Radoslav Buchik, who is of the Southwest Research Institute in San Antonio. His title is Narrow CMEs, Jets, as Progenitors of Impulsive Solar Energetic Particle Events.
Yes. So good morning. Particles from impulsive events and associated jets and narrow CMEs. So impulsive SEPs show very peculiar abundance. So this figure here show on the left side is the enhancement factor in impulsive events compared to corona or solar wind as a function of the mass for different ion species. So you could see that some ions like helium-4, carbon, nitrogen, oxygen are not enhanced compared to solar wind, but other show enhancements which increase with the mass of the ion. So this is understood in terms of mass to charge ratio. There are some theories which shows that species which lower mass to charge ratio are more enhanced compared to species which has a higher mass to charge ratio. There is a helium-3 which is enhanced by a factor up to 10,000 and doesn't fit these enhancements, and this is understood with this is explained there is a different mechanism possibly accelerating the helium-3. The source of these events is thought to be jets, are thought to be the jets, which this is a classical model of the jets from Shibata, where emerging loop interacts with the overlying field and produce turbulence which accelerate those particles, and the plasma together with the solar energetic particles escape to interplanetary space. However, we also see in impulsive events that the jets could be produced by emerging of the mini filaments. Since these events shows enhancements, tremendous enhancements of helium-3, they are also called helium-3 rich events. Impulsive SEP events have been associated with the small size flare, so the observations of CMEs in these events were a surprise. So this is an example of 4 impulsive events and the associated narrow CMEs. However, these CMEs are much narrow compared to CMEs associated with gradual SEP events, which are produced by large-scale shocks. So later, jets were observed in impulsive SEPs events together with these narrow CMEs. So this is impulsive events, very intense impulsive events, which start on May 1, 2000. This is particle intensities versus time associated Gauss X-ray flare, type T radio bursts, and energetic electron events. And this is EIT image showing the source of the narrow CME, and LASCO C2 and C3 image of the narrow CME. On the first slide, I show this enhancement factor. So the enhancement factor is defined as okay, doesn't work. Okay. So enhancement factor is defined as element X relative to oxygen in an impulsive event, and this is divided as element X relative to oxygen in the corona solar wind. And in the May 2001, May 1st, 2000 event, impulsive event, it is shown on the The pointer doesn't,
Just,
is not working.
you'll need to drag the pointer more towards your right. If you click the pointer, just drag it. Drag it more
Doesn't work.
while holding it.
Great. Anyway, this SCP-2 event is the May 2000 event. It's associated with narrow CME, speed of 1,360 kilometers per second, and this CME is fast enough to drive shock that could reaccelerate the suprathermals from earlier magnetary connection, as well as abundant ambient hydrogen, and cause this proton excess. So when we fit all the elements, those numbers show atomic number of the elements. When we fit the elements with power law, so we see that hydrogen shows some excess. On the left side, there are other impulsive events. Event 3 is impulsive event with no CME, and event 4 is impulsive event with the slow CME, and we see that in this case is the hydrogen fit lies on the feet on this feet. Okay. So later, narrow CMEs were also associated with the jets. So on the right side, there is a recurrent impulsive events. So you could see the helium-3 and iron intensities, and on the left side, there are corresponding recurrent jets from EIT and the LASCO narrow CMEs. Yeah. So, and I'm just going to present jets which are published. However, associated CME were not, so I tried to find associated CME with those jets. So this is an example of the Solar Orbital Impulsive SCP event on November 17, 2020. Solar Orbiter was at 0.93 astronomical unit, and on the right side there are several observations. So there is a mass versus time spectrogram which shows helium-3 track, which is typical seen in this event, and there were several ion injections. So I will focus on the ion injection, which is number 3. We could also calculate the ratio, helium-3 to helium-4 ratio was 1, which is typical for impulsive event, but it is almost 10,000 more than in the solar wind or corona. Iron to oxygen is also close to 1, typical in the event, which is typical in these events. So here we have a stereo image. Stereo was located, is marked by A, and the event longitude is marked by, you see the narrow 1 to 3 marked by the longitude of the injection 1 to 3. So we are focusing on the injection marked by number 3. So the source of this impulsive event is a jet. You could see in the top panel, this is stereo A image at the time of the type 3 radio burst. Down, you could see a radio spectrogram, either from the solar orbiter and from stereo A. And on the right side, you see the image from the SOHO LASCO coronagraph. I take the numbers from the catalog. So the first occurrence of the narrow CME was at 19. The CME is already narrow, 27 degrees, and quite slow. Yeah, you could see the very slow CME. You could see the now very narrow CME, which was associated with the jet. So this is another example of the impulsive event from Parker Solar Probe in 2019, April 20. I'm not going to show the intensity time profile of this event. On the left side, there is a histogram showing the helium-4 peak and also helium-3 peak, small helium-3 peak. This event, helium-3 to helium-4 ratio was quite small, but anyway, this was not, this is also, such a ratio is also observed because there is a huge range of the ratios in this helium-3 rich SCP events. Parker Solar Probe at that time was 0.46 astronomical unit. Associated type radio burst and also gauge flare is shown here. This event was associated with the helical jets. You could see these helical jets. May I ask to play on the movie on the left side? Okay, at first you see the narrow CME, and this is my lack of experience. This CME should be counterclockwise rotated maybe 10 degrees, so I did some error in the rotation. And then on the left side there is a movie. Yes, please. So, yeah, you could see the jet which is associated with this impulsive event. Oh, it's playing. Also, I was okay. This is example of ACE, impulsive event, in the 2015, August 24. This is the most intense high-energy helium-3 SCP event in solar cycle 24. High energy, we define high-energy event where helium-3 to helium-4 is greater than 1 at the energy 10 MeV per nuke. So these particles are really fast. They arrive in 1 hour from the sun to the L1 where ACE was located. So the event is shown down as there is a intensity time profiles. Dot shows helium-3 and curve show helium-4. You see they lies on top of each other, so the ratios are close to 1. And the event is associated with the 4 type 3 radio bursts, which are separated by 1 hour, less than 1 hour. So only last type 3 radio burst has a CME. The CME was very slow and was quite broad and was not very good observed because perhaps the source of this CME was near the central meridian. So this is sunspot, which was the source of this jet and impulsive event, and this is one of the most complex sunspot with the most complex beta gamma delta configuration, and was among the 10 large sunspots in the previous solar cycle. So yeah, you could see the CME is not very nicely seen. May I ask to play the movie on the left side? Yes. So you could see jet and the boundary of the big sunspot. First jet was not yes, and this one, and this last one with M-class flare was associated with this CME. This is another ACE impulsive event, 2011 February 18. This was the event with the highest helium-3 enrichment in the solar cycle. So we could see that during the event, sometimes the iron to oxygen ratio was around factor of 10. However, there is some background of the helium-4 before the event, so the real helium-3 to helium-4 ratio was much higher. And CME was not very spectacular either in this case. And may I ask also to play the movie on the left side? You could see there is a nice helical structure in this case. This is the impulsive event on the June 8, 2012. there is a intensity time profile showing associated type 3 radio burst and narrow CME. I will also ask to play, yeah. You could see nice jets at the boundary of the large sunspot. Okay, this is the last event I'm going to show. This is 2011, October 17. In this event, we couldn't see any jet. Yes, we just see brightening. And I also checked the stereo A, which was in Quadrature at the time, and couldn't see with stereo A any jet also. So, but of course, stereo A has a lower temporal resolution. But LASCO C2 sees some jet. So narrow CME. So conclusion, there are many papers on solar sources of impulsive SCPs using solar disk UV observations, but there are practically no studies using observations of the corona to examine CMEs associated with these events. This should be changed with a wealth of existing data from past missions and data from forthcoming missions to understand impulsive SCPs. Median CME width and speed from 6 strong presented events in this presentation is 60 degrees and 330 kilometers respectively, so quite slow. So we may ask, how do CMEs and impulsive SCP events affect the elemental composition and energy spectra of these events? Also, we may also ask, how do CMEs cause wide azimuthal distribution, which are observed in some impulsive events? Thank you.
Thank you. I'm going to turn it over to Heather Elliott to facilitate the mic.
Okay. All right. So if the speakers could
Panelist
go
speakers
up
come
on the-
forward.
yeah.
Yes. Say again? Nick? Microphone, of course. But I'm going to run.
No, there's some.
Yeah. Okay. Don't steal it from me, Alphonse. Right?
Yeah, and then there's switches at the bottom of each of these microphones. Okay, I'm going to start off with a popular comment by Craig. The comment was to Nikki. He said that the NIFI Nyquist frequency could maybe be finagled up to 3 to 4 millihertz by making use of the clear images. And I think he wants to talk to you about that, Nikki.
Yes. So mission scientist Nikki would never ask you to change the program for my personal science. But I think there's compelling reason within if we can make this work in a sensible way, I think that would be awesome if we could go after this, and make if we did 2-minute cadence and had a 4 millihertz Nyquist, that would be pretty awesome. We could catch that whole distribution.
So, am I on? The point of the comment was that our synoptic program will give you that, right?
Yeah,
With proper
awesome.
analysis.
Yeah, that's pretty cool.
Okay. Another popular question is for Noor. It's from Bill Matthews. He said, do you agree that the observed jetlets can be associated with any process that heats plasma in a spatial pattern associated with supergranulation?
That's a great question. So let me first say that supergranulation itself, all what it does, convection in general, concentrates the field in the network. It's the activity in the network that is really important. And having this small-scale reconnection everywhere, whether it is closed or open-closed, it's actually what keeps the plasma hot in the loops. So by nature, when the open-closed reconnection occurs, the plasma is already at coronal temperatures. You don't need any extra heating for it. That's why the jetlets by nature are hot.
Okay. Oh, okay. Tom's going to follow up. Okay, well, Tom is already in the middle, looks like.
Got it?
Yeah.
Okay.
I'll come back.
It's not just the network where we have small-scale field and reconnection. It happens inside of supergranules as well. It's everywhere.
That is actually the
And
closed,
the network is
closed,
just a
closed.
concentration, so you see more there.
Yeah, that's the closed connection.
Yeah, it's not like an empty field and then
Yes.
it's all in the network. It's
I agree.
everywhere. So.
I agree.
Yeah, okay, I'm going to go back to Bill.
Yeah, Nora, I just wanted to comment that I could take your words exactly and say turbulent processes can heat the loops, and that's all you need. I mean, it's just
That's
substitute turbulence for reconnection, and I agree with your statement.
No, I'm fine
But
with
I think to distinguish between the two, and this, my problem with the association of reconnection as the source of the solar wind in these papers that you're talking about, is that you haven't ruled out the competing theories that have been established for 20 years as likely candidates for exactly the same phenomena. So until you distinguish it from other things, I don't think you have a real case.
So, okay, unless turbulence can supply mass to the corona and the solar wind, unless turbulence can do that, which I don't see, the only mechanism we have that can supply mass and energy lower down is reconnection. You need to open the closed loops in order for the plasma to make it to the corona. Turbulence cannot do that. The only mechanism can do it is reconnection.
Okay. All right, I'm going to go to a recent question. It's from Ritesh, and it's to Nikki. Does the Fourier analysis tool you mentioned do any analysis of particular height or position?
Yeah, so when I was showing the histograms of WSPR and Core 2, we run that, the way we ran it was on we made slits of pixels that were 10 pixels tall and 1 pixel wide, and we ran it on every single slit of pixel in the whole image frame in one-day periods for the whole encounters. And that's how we built up our statistics to make the occurrence distribution. But the point is that tool can be run on anything. We've run it in the magnetosphere. We run it in situ in situ data. We've run it on the images. And so it's flexible and it can be run anywhere.
Okay, and that one's available already?
It's open source,
okay.
yeah. Yep.
Okay. Next, I'm going to go to another fairly popular question for Alphonse from Matthew West. It says, okay, yeah, that's the one. Have we connected any low-latitude jets with the in-situ measurements from stereo and Earth and confirmed the presence of an embedded flux rope structures?
So it sounds like a joke. What's the difference between a CME and a jet? And the thing is, we think they're basically the same things, okay? So you have an erupting flux rope. The flux rope is formed, either at the base or just, as it's making the flare and erupting out. So there's a flux rope that's erupting and then it's interacting with the open field. That can happen with a CME or with a jet. With a CME, the flux rope is so robust and big that the flux rope itself gets out and escapes and persists in the heliosphere. In a jet, at least in the ones we believe we've seen, the flux rope doesn't make it out. It gets totally eaten up by that reconnection. So all of the flux ropiness of it is lost with that reconnection. It gets transferred into this alphanic twist wave packet, assuming that the erupting mini filament has twist in it, and at least many of them do. Then that twist would get transferred to the open field and it would go out as a twist wave. So the flux rope would be gone by that time. So we would not expect there to be a correlation between jets and flux ropes. There are probably border cases, but in the general case, that's what we expect.
Oh, okay. I'm going to go to another question for Alphonse because it's kind of related. So it's from Ritesh, and it says, do these jets obey some sort of relationship between the size and the speed?
There have been some studies of that, none that come to my mind, so I'd have to look into that. I think some people have done some studies of that, but I don't have anything in mind about that now.
Okay. I'm going to go to another popular question by Joan Burkpile. and it says it's for NOR. Assuming jets produce the bulk of the solar wind, is that consistent with observed differences in plasma properties between the fast and slow wind?
Thank you, Joanne, for that question. It's really important. So one of the main differences, as Joanne said, between the slow and wind, they have different composition, and we have to explain that. And one way of explaining it is that the composition is set by the ponderative force that acts differently within the coronal holes than the quiet sun. So that's where the composition is set differently. But the mechanism is basically the same, except that in the loops, in the quiet sun, they have different composition because of this force.
Okay.
I think Marcia actually, in one of her older papers, related microstreams to the X-ray jets because of the alpha to proton ratio composition changes observed. And that was already at Ulysses. Yes.
Yeah. That's actually a really interesting paper too, because she also shows you can have like little compression regions over the poles.
Exactly.
Yeah.
And
Okay.
the other thing also, and this is by hand, it's really, I'm hand waving here, and I might be totally wrong. The reconnection in the coronal holes occurs very low down. It's really the small loops that are reconnecting with the open field. The reconnection in the quiet sun, actually the loops are higher up in the corona. That's probably why the composition is different.
Yeah. Okay. I'm going to go to a recent question that I think is related. It's for NOR, and it's by Deepankar. And so the question is, how do we explain the bimodal distribution of the solar wind, the slow and fast acceleration mechanism, need additional inputs? And it says jetties may not
Be enough or something.
efficient.
Yes.
Be enough.
So one of the ways to explain this is the super expansion of the magnetic field. When you have a funnel that expands super radially very fast, you can turn a fast wind into slow wind. That's one of the explanations. The other explanation is from the get-go, that in the quiet sun, the plasma by nature is denser. So you have the energy partition per particles is smaller than in the open field regions. So that's why you have one of them, the particles gets way more energy than the other.
Okay, I'm going to switch topics here for.
If I could just say something about that quickly, a question I have though is I don't know if we know where the source of the slow solar wind is. Is it really the quiet sun, or is it actually active regions, which has been talked about too?
Actually, I
Both?
do.
Yeah, it's
I
multiple.
do. It's actually the quiet sun.
Based on solar wind observation, it seems like there's multiple sources. Yeah. Okay, I'm going to go to. Things are jumping around. Yeah, I want to go to a question from Sarah Gibson for Radislav. It says, we heard about the self-similarity of jets from Alphonse. Is there also self-similarity in the impulsive SEP events?
So recent observations shows that very small jets or even very small brightening, we are not able to distinguish whether there is a jet. We see the composition is is an helium-3 to helium-4 ratio, for example, or iron to oxygen ratio is not so enhanced. So it is more coronal or solar wind-like. And in the events where we see very clear jets, so we see also the enhancement is very high. So, but I don't know if it is. If it is what what do you mean exactly by this self?
I think they mean that, the large eruptions and jets and maybe down the specule seem to be basically the same thing going on.
Switcher, yeah.
Is the questioner here? But I think they mean that the. Oh, yeah, go on.
Where I'm going with this is, this shower head that Nora's seeing, all these things merging into, we get the spectrum, right? We have the large event, we have this medium size, we have the very small, and you're saying you even get into the microfilaments, et cetera. And I don't, I mean, and maybe this, I don't know if this really applies for the impulsive SEPs, but do you have similar situations? I assume if the same mechanism is happening at different spatial scales, you might have something similar happening with the SEP, but just at different energies.
Yeah.
And do you end up with like some sort of continuous background that could be related to some sort of more micro event
I
type
can
thing?
comment on that. From Parker Solar Probe, we've seen events where you have a continuum from the high energy particles all the way to the thermal solar wind. And this occurs at different scales. There is a paper that is led by, what's his name, from SSL. His name escapes me, but it will be submitted probably the next couple of weeks. There is actually a follow-on paper that I will not mention who's writing it, but that one is going to be key to this thing.
Mm-hmm.
We see this small events producing basically all sorts of particles of different energies.
Okay. I want to follow up a little bit with Radoslav. Okay.
Just one comment. What we say that in jets with a helical structure, we see very high enrichments. So there is maybe this, and in jets with which are driven by the filament eruption, we also, which are mostly those events which shows helical structure. So I think this is maybe important for these jets.
Yeah, because I was going to try to help clarify a little, like, so Radoslav, are you seeing something with the size of the jet? Does it affect the intensity of the SCPs or the composition? Like, is it the size of the jet or no?
Okay, there are not so many observations, so we could, so we need more studies, but if we have a complex jets, we see very intense events. If the events are small, like as I mentioned, the brightening, as we last time see with the SDO, we just see a very small spot on the sun, but Parker Solar Orbiter were at the 0.3 astronomical unit, and we see very strong event. So we have to go close to the sun to see whether such small scale events, small jets, or just brightening could produce very intense events on the closer distance to the sun.
Okay. Next up, I'm going to go to one by Steve Kramer, which might spark a lot of debate again. It's tenor, and it says, yes, turbulence can supply mass to the solar wind by heating the plasma. You don't need some separate source of mass.
Yes and no. Go ahead, Steve, please. Go ahead.
I apologize for the comment, not a question, nature of that, but yeah, no, the Parker's original mechanism of accelerating the solar wind, even to higher speeds, can be accomplished by, along with super radial expansion and all the other bells and whistles, can be accomplished by just heating at a various range of heights. But yeah,
I agree with you on that if we limit ourselves to Parker's idea. But the solar wind we see is way more complex, is way more structured than Parker. So this structuring is key to what is going on there.
Turbulence is pretty structured too.
Turbulence is pretty structured too. Periodicities, though.
Yeah.
Yeah.
There you go.
Yep.
Yeah.
Yes.
Okay. He said, what creates the turbulence? And then people were saying stirring or something?
No, it's too slow for the dynamics we see lower down.
Okay,
it's
so
too slow.
Yeah.
Shuffling of field lines by photospheric motions has been looked at for a long time, and I think there's a lot of literature that you have to overcome to say that that doesn't work.
It's too slow for the dynamics we see right now. It's too slow.
On the granule scales, there are correlation times of order, 30 seconds to minutes that can drive some of that stuff.
If I can add something here, yesterday during the nice movies tracing the blobs in the solar wind by one of our good friends here, this is why I asked what percentage of the solar wind could that account for. So I wonder if there might be like if you want two components to the solar wind, this blobby component, which works well with jetlets and jets, and then a more background.
Turbulence is blobby because it's intermittent.
Okay, well, there you
But
go.
in fact, Alphonse, that is exactly what Working Group 1B is set to answer, is how much is turbulence, how much is evolving, how much is just a structure that came from the sun. That's literally what we're hoping to be able to answer.
Yeah. Okay. All right. So I'm going to move on to a question by Phil Hess for Nikki. He said he withdrew a previous comment, but he had another question. How far out into the punch FOV do you think you'll resolve these structures and periodicities?
Yeah, the 90-minute ones, in fact, we designed the requirements to catch those through the WIFI field of view. And I'm so excited for that because, in stereo high 1, we can see them in core 2. In high 1, we can see them about halfway through the field of view, and then they fall below the noise floor. As they expand and their density falls, they fall below the noise floor. So WIFI's going to be able to see them. Do you have more to say, Craig?
Yeah.
Just that we'll deliver full cadence out to the edge of what is now the high 1 field of view. And as you said, we'll have much lower noise. That's all.
Yeah. Okay, I'm going to go back to a popular question by Bill Matthews to Nikki. You mentioned P-mode frequencies. Are you in agreement with the ideas of Lanzarote and Thompson? They reported observations of many P-modes in the solar wind.
Yeah, Bill, I'm so glad you brought that up because this was a huge struggle for us as we were investigating, the 20-year problem, where do these come from? David Thompson's signal processing methods, we use a lot of the same techniques, they're excellent. His interpretation we disagreed with, and so we just struggled with that because he had this idea of P-modes maintaining their very precise periodicity and coming straight up through the chromosphere, coming out into the solar wind and just being there. And that was wrong. But yes, we were seeing those same periodicities in a general sense. And so, yeah, actually that was tough because we weren't quite sure how to put it all together. Anyway, I think we have a really nice story now where it's not just straight P-modes coming through. The P-modes do this complex thing to the jetlets. They mode convert. They become, transverse alphanic waves, and then reconnection periodically releases structures. It's a harder story to tell, but yeah, I think now with all the observations, we're starting to see how, the parts that were right about that.
Okay, I'm going to go to a question by Vadim Uritsky. How do we reconcile the super alphanic nature of the jetlets with the large-scale alphane zone around the sun? Can its inner boundary be formed by the jetlets? And I think this one's open to the panel. No takers on this one? Okay.
I can probably have a get. If we believe the theory by James Drake, and his paper is not archived, so it's, yes. So the wind is supraalphanic from the get-go. So we have an issue with this critical boundary, so to start with. But if we have another component that is continuous, like Steve was arguing earlier, then that might actually set up some boundary or zone or whatever it is. But we still have to figure that out.
I'm just thinking about the fact that this zone seems to be thick. So is the thickness of the zone somehow related to the spread of the speeds of the jetlets?
Could be. Could be.
And I think we just have time. I think we're getting close on the time, right? There's one quick comment here by Tom Berger. It says, comment to researchers, don't forget that the AIA data is 4K by 4K and 12-second resolution. In studying jets, you should make the effort to use those data.
Great.
I
have a movie that I can show, if I can share my screen, of such data, of a jetlet actually. Actually, it's a large jet, but I think you'll see, because I haven't seen anybody here yet show full resolution, full cadence AIA data, and it really does make a difference. So let me share this movie.
Okay. Okay, go ahead. Okay. Okay, well, we'll have that played during the break. And there's one quick announcement by Sarah before we go to break.
Yeah, sorry, I missed this one out earlier. We have a switch of talks in the order. And so Samantha Wallace's talk is going to be in the next session, and Don Schmidt's talk is going to be in the session after lunch. And this should be, I think, updated in the agenda, but I wanted to let you guys know.
Okay.
This is 4K by 4K data at 12-second cadence. So it's a pretty rare movie in my experience, but it's not that hard to make. So I think the people wanting to study kind of an analysis.
Okay, and we'll let this play some during the break if people want to.
What wavelength is this?
193.
So if you do 171, it will be even better than this.
Well, all of them.
Right on that.
So
Okay.
Heather, if you don't mind, one last comment. I should have mentioned in my talk, but I escaped. It's 30 seconds. There is one key thing from Punch that can help us figuring out the nature of the solar wind. Is really the structure, the filamentary structure of the solar wind. If we can figure out that within a certain depth, that whether the dominant solar wind is highly structured and basically small features, then that will probably settle the question that the Parker wind is minimal. If it is the other way around, then the Parker wind wins.
Okay, let's thank our speakers, and we're going to reconvene. We're reconvening at 10:30.
I'm chairing it with handle the beginning announcements and so forth, and Dan hopefully can deal with Slido and the questions. So our first speaker of this session is Sherry Lynn Morrow, Punch Outreach, Accomplishments, and Opportunities for Engagement.
Wonderful. Thank you. Well, welcome to the roller coaster. Could I ask, I see that others are parking cars or doing something, but I'd love for everybody in the room who's here to, and I went backwards, sorry, whoops. Oh, geez, what a rookie. Okay, I'm going back, I'm trying to go back. I'm not succeeding, okay, so let's try
button
again.
at the bottom.
Off to a great start, everyone. All right, there we go. Who's on the team? If your face is on there or not, come on, stand up, show them you're here. This is our first opportunity to integrate the outreach team with the science team. Yeah, and we're really, really pleased about that. This is an exceptional team, and during the lunch break, they'll be around with some of our products and activities. If you missed last night, take advantage of that, please. And if you were there last night, good on you, and I hope you enjoyed it. Great. Okay, so that team that just stood up are representatives of these institutions. They are a Four Corners kind of regional collaborative, and we have Native American partners there on the map at the right. You see that we have this Stone Soup Collaborative, which is really a powerful way to have everybody put in their strengths, and out comes something, a suite of products that no one institution could possibly do. And we have lots of new affiliates thanks to the partnerships of these institutions. So we're sharing partners, we're sharing our strengths and making an incredible suite of products. We don't have target audiences. We collaborate with historically marginalized populations, and we wind up with multicultural, multi-sensory products and events that are beneficial to everyone. Here are some of the populations we are focused on and collaborating with: Native American and Hispanic youth and families, blind and low vision learners, and specifically in the Native American world, learners at the Haku Academy at the Pueblo of Acoma, which is just about 60 miles to the west of Albuquerque, and girls in STEM. And you see Sarah there was one of the first team cards that we had. I just want to let you know that here's why we're here. The NASA Heliophysics Division basically said, okay, actually, let's say, Craig said, I want to do more with my mission than NASA communications. I want to be of societal benefit and light some kids up in the Southwest. And so both he and our project scientist, Sarah, have been extraordinarily welcoming, and I meet with them routinely along with our web developer. I hope you stood up, Don Kolinsky. You're part of what's making us proud out there with regard to your web development skills. So thank you so much and Sarah for sharing him. These are the operating principles that were in our proposal, and hopefully, yes, you got, I'll say more about the thematic outreach event or outreach approach. We're leveraging strengths and partnerships, learning from those we intend to benefit from the start. So here's the one slide deal of our thematic approach. Here is, David, I hope I get that 10-minute alert too. Yeah, okay, good. So we're not just punch specific, we have a great funded partnership with Parker Solar Probe, especially with regard to our Planetarium film development. We're portraying ancient sun watching as the foundation of NASA exploration of the sun, right? So NASA exploration of the sun is the extension, a natural extension of the humanity's long-lived proclivity to observe the rhythms and mysteries of sun, right? And so that's how we connect the ancient and modern, and then we also connect it to personal sun watching, whether that's the everyday sun watching, indirect or directly, sunrises and sunsets, or something exotic like the upcoming eclipses. So we do this to actually make NASA heliophysics more relevant to a greater diversity of learners, particularly in the Southwest, but Chaco is a World Heritage Site, so there is global interest in this as well, but really creating those personal and cultural connections with the sun. Here are the 5 types of outreach events that we are enacting and testing. Thank you. And live interaction planetarium film now will be post-eclipse. Solar observing, yes, observing events. Folks you think might not be interested in the eclipse are very interested in the multi-sensory dimension of eclipses. So blind and low vision learners, Girl Scouts, out of time patch events, and then these events, we've convened one of these now at the Pueblo of Acoma, the STEAM community events that integrate the arts. Also, Chaco interpretive events, and we're providing interpretive materials as part of this punch bowl. So this punch bowl of products that we're developing are feeding all of these different types of events. I guess there's some ambiguity, Barbara, right? But we can handle it, right? So there's an example of an event that happened at an annular eclipse for Chaco, and there will be another one of those on 14 October. There are many opportunities for scientists like you to be a lot of places. The New Mexico Museum of Natural History and Science has a whole list of places who would love to have subject matter experts, scientists to give talks. If you're one of those who is interested in being placed someplace or want to be someplace specific, New Mexico, if that's one of your places, this is your team to connect with. So we have this modeled approach where we're going to be the lead conveners, where we're sending people and resources, but somebody else is convening it, and where we're making resources available for training for use at an event, but no outreach team member is on the ground. Outreach team member includes our scientists and our broader heliophysics community. Everyone here would be a candidate to contribute if you're so inclined. And Sarah and Craig are very encouraging of that if you're so inclined. No pressure if you're not. So this is what I hope to really, that was my rapid intro to the whole of the program, and there are other resources on the website. We are advancing knowledge and interpretation of this so-called Chaco eclipse site. Chaco culture is in the Four Corners region here. You see it is the center of a vast network. 1,000 years ago, all those red dots were things that Chaco, great houses and so on, that Chaco was in the central place of, and that's the famous Pueblo Bonito, World Heritage Site Chaco. Give you a feeling of the place. Fajada Butte, how many have heard of the Sun Dagger? That's on top of Fajada Butte. That's what Chaco is about. And you see Fajada Butte on the right, and you see Triangle Rock on the left. And the sun watching site that we're focused on is actually, there's Triangle Rock in the upper right here. And you see it's just across the way from Fajada Butte. And it turns out that this sun watching site has a lot of marvelous attributes, including what we call this eclipse petroglyph, eclipse in quotes. We can never be sure, but we're supporting, we are exploring and pushing the envelope about the sun watching events that occur on each facet of this rock complex, to the west in the winter solstice time, and to the east near the summer solstice time. The ravens supervise in Chaco, and you see them in their nest above. And then this, which is part of this button, right? Everybody recognizes the petroglyph, right? Our theme. So here are ways that we're advancing knowledge of the site. Our research permitted photo documentation is corrected and elaborated on previously published data about how that horizon calendar on the right, on the east side, and the light and shadow on spiral phenomena are working. And I want to just share, we're also done complete photogrammetry of this site, so we're going to have a model that shows how the horizon event related to this triangle rock is related to the way the shadow plays on this spiral petroglyph on the eastern face of that site. So this is being developed by Planetarium, but multiple institutions contributed to securing the photography. So turns out that on 3 June or 9 July, the tip of that shadow goes straight through the center of the spiral. I'll play a little video, I hope. That was time-lapse video that I recorded on a cell phone. and you watch the apex of this shadow pass directly through that spiral center. That's when the sun, of course, is coming right out of the top. Yeah, and I got my eyes on that. And this sun's disk basically spurts out of each side of the petroglyph. We're also doing some research-permitted study of pottery with the sun-themed designs, and we're unveiling motifs in pottery that look like the petroglyph, and that's a really new development the last 30 days. And we have a 3D printable model of the petroglyph based on Thor, I believe that's RTI, right? So reflectance, yes. Talked with the students, some of you last night, who are the creators of those things. So we've become students of an active solar corona, and we need your help, right? We're comparing the curlicue designs of an ancient pottery bowl to the Chaco petroglyph. I put these captions in here for the record, because I knew I would be pressed for time, but this was found by accident. It currently cannot be found in the archive, though we've been in there to search, but there are other pots that have this kind of motif. Notice that both of these are hand-sized. Both the petroglyph and this bowl are about 8 inches across the span of your hand. This is, on the right there, is it is a 3D print of an exaggerated relief of this petroglyph. And if this motif predates, that this just kind of connotes sun, so that this is sun and not enlarged prominences or any other kinks and curls. This feature that became more evident once the students created this 3D model using that special photography becomes interesting, and we're interested in what you think about its interpretation. So here are some ideas about that. Sarah has let us know about the longest ray and Annie Maunder, and also been reading some papers here by Druckmüller et al. About these tethered prominences. So if anyone has anything to say more about that, I'd be very interested. And this next section, most of you have experienced. How many were there last night? Yes, many of you. Thank you for coming. We appreciate that so much. And you have experienced these, the team cards, and you'll see at lunch, you have some of them out there on the table. You have the punch, 3-hole punch, pause, pinhole projector. I won't say everybody now, class, I won't do that. But if you pause after 3-hole punch, you get the pun and you can say it. 3-hole punch, pinhole projector. And this is taking the universe of our outreach colleagues across the country by storm, right? So we just printed 100,000 of them and are disseminating them to people who are known to us and who have events in which they will facilitate this. And there's extraordinary resources on the web related to this. And so our evaluator, Dr. Sandlin Buxner, is here raising her hand in the back. She is going to be following up with you about opportunities. We want to know where you are going to be for the solar eclipses, right? And, or want to be. And we also need to know when you do something, whether it's pre-eclipse or on the eclipse, to let us know. And we want to make that dead easy for you, but it really helps us to report to Peg Lucci in the back, you know, if we understand what our broader community and team is doing, especially if it involves our resources. We're very happy to send you some of these to support your outreach events. Yep. And so please let us know. It's also turnkey on the website. To print these, there's a direct connection to the printer. They know exactly what to do, and all you got to do is order your number of them. Okay? So making that very easy for folks. Check out on the website now, under the Outreach tab, select Outreach products. You'll see facilitator guides and lots of resources to support these activities. So if you're interested in making use of them, you know, please have a look. In the interest of time, I think time up, right? So I want to mention Citizen Kate, which has provided a beautiful glue between punch science and the eclipses, because Amir Caspi back there in the left corner of the room, because he's the director of the Kate, you're going to do polarized light observations all along the eclipse path in April of 2024. And so that creates a lovely sort of glue. That data will be worked by Dan Seaton and others to create 3D reconstruction of what's going on in the low corona, right? And so that's very kindred with punch science. So again, encouraging you to get involved. We got most of the outreach team here. Please do connect with us and go to the tables and talk with the people who have been part of creating these marvelous suite of activities. Thank you.
Thank you. Okay, our next talk is on STEAM, which is the Student Thermal Energetic Activity Module. You can read the rest of the title. Gabriela Galarraga. Thank you.
How do we click the thing? Just go, this thing. So hi, I'm Gabriella, and I'm with the STEAM team, which is the Student Thermal Energetic Activity Module. It is a student-led mission that will be on the Punch NIFI spacecraft. This was your slide. Oh, oopsies. Okay, so a little bit about our science objectives is we plan to explore the enhancement of the low FIP elements in the solar corona and see how it connects to the solar coronal plasma. And overall, since we are a student mission that is hosted on Punch, we want to support our parent mission to the best of our abilities. And we are also a do no harm instrument.
So a little bit of background about magnetic reconnection and plasma heating. We have this diagram here detailing it, but you'll see oppositely oriented field lines coming up off of the sun, and they will cancel, rearrange themselves into a lower energy state, which ends up sort of pinching in the middle and releasing that explosion of energy, which releases heat and energy into the corona. So the low FIP elements that Gabriella mentioned earlier are enhanced by a factor of approximately 4 in the corona over their chromospheric values. So we'll be looking specifically at those low FIP elements that have a different enhancement factor to sort of infer the origin of plasma for flares in active regions. So we're flying 2 detectors. Both are X-ray detectors. One is a soft X-ray detector, the other is a hard X-ray detector. Soft X-rays are used because they provide the most direct signatures for hot plasma, and hard X-ray will be used to get a more comprehensive look at the plasma evolution as it comes from the chromosphere into the photosphere. From the photosphere into the corona. And by using both of these, we'll get coverage of thermal plasma temperature and composition. So this is just a wavelength log temperature spectrum of the low FIP spectral lines that we'll be looking at. You can see circled in blue, and says STEAM, are the low FIP elements that we're concentrating on. This is building off of previous missions such as MINX. We'll be looking at these low FIP spectral lines with a greater resolution than instruments before us. So STEAM consists of, as I mentioned before, a soft X-ray detector and a hard X-ray detector. We are using 2 off-the-shelf detectors. The first is a silicon drift detector for our soft X-rays, and that will look between 1 to 7 keV. And the second would be a cadmium telluride detector for the hard X-ray, which is 7 to 20 keV. So this is a rendering of the STEAM instrument. It's about this big. It's the size of a little tissue box. You can hold it in your hands. And so you can see the baffles sticking off the end there are where the detector heads are placed, and they are designed to take in solar spectra and look at the range that we specified. And then shown below that is just one of our spectrometer board stacks with a flex cable to show you the size of the detector head, which is about the size of the boards are about the size of a pack of cards, and the detector head is like pretty small. It's about the size of a dime. So this is a video. I don't know how to play it.
I think you have to click it.
Okay.
Yeah.
Thanks. So you can see here, this is how our spectra are built up. We have individual histograms from 10-second integration times, taking in data from our spectrometers and then analyzing it. So the 10-second integration times are shown in red here, and they will be summed to create an overall spectrum, which is shown in white. So if we, oh, never mind. Go for it. So one of the main things that the science team for STEAM has been working on is spectrometer calibration. And this is essentially just a schematic of if this were an emission line from one of our radioisotopes, this is what we would use to calibrate our detector. So the centroid energy gives us the energy scale, full width half max would be the resolution, and the spectral response is determined by the height of the peak. So we've been doing this calibration on the ground in-house with radioactive isotopes. So we have results for our flight spectrometers. These are just the the hard X-ray calibration curves, so the CAD-TEL detector that I mentioned earlier. But our calibration curve is shown on the, sorry, this is backwards for me. I guess it's on your right.
Oh, yeah.
Oh, is there?
Oh, there
yeah,
it is.
that one.
Would you wanna point it?
So that's our calibration curve. It's okay, you can turn it off. You can see we've used 5 isotopes to calibrate our hard X-ray detector, and this correlates channel to energy. We see that we cover the full range of energy that we specified in our requirements here, and shown next to it are the residuals, which essentially just shows how much error we have. You can see the largest one is on our americium source, which was the noisiest source, so it makes sense that it has the largest residual.
So here's a little bit about how we plan to achieve our science goals. So one of our main goals is to measure temperature and elemental abundances in solar flares by observing the X-rays that Sam had mentioned and their respective energies. So when we can model the energies by using the appropriate physics, I guess. So when we build the spectra for the flares, where the continuum regions will be associated with free bound radiation and free radiation, or the Bremsstrahlung radiation, and then the emission lines will be associated with bound radiation. So for the analysis of the spectra, the shape of the continuum and the intensities of the emission lines will allow us to fit temperatures and abundances to the spectrum and each flare and active region. So as this kind of diagram shows, we'll be using forward modeling, using chi-squared minimization, and alongside the Bremsstrahlung and atomic emission databases to derive our observables. So here's an example of our expected data, which is courtesy of previous missions, Minx and Ressi. And this is very similar to what we expect to see and do with STEAM. So as you can see with the 2 soft X-rays, or the 1 soft X-ray and 1 hard X-ray, we're able to get a less noisier line, I guess, and then that kind of, I can do this, this gray box right here is what's going to be outside of our energy range for our hard X-ray. So while we will be seeing these photons, it's so noisy that we're just going to kind of block it off. And so we will utilize the emission models to plot each colored dotted line, which will represent one thermal component of the distribution, and that fits well, and then that can help us fit the rest of it. So and what we plan to do is to take all of these colored lines and make a line of best fit, which would be represented in a brown line that is very hard to see, but it does kind of go along that red line. It's kind of hiding behind it. And then through our forward modeling, we can find that optimal combination and for that line of best fit for the whole spectrum and tell us what temperatures and element abundances that the data represents. So, yeah. And then this is our tentative data pipeline. We are currently working on that right now, but once we get the data from from STEAM. It's going to be raw, binary. We're not going to be able to read it very well, so we will convert it to something that's a little bit more readable, like FITS, and then take it through that entire process before of that modeling to kind of go from this, which is just kind of the data that we would just plot, to what we saw before on the other slide to get that kind of line of best fit there. And so this is our connection to Punch, because once again, they are a parent mission. We want to support their science as much as possible. So we are going to be focusing on the flares and active regions, and kind of building off of that temperature of low FIP elements to kind of understand the origin of heated plasma, to eventually connect the corona and the inner heliosphere, which Punch is doing as well with, but more with solar wind and CMEs and all a bunch of other cool stuff.
So this last slide is basically just covering what we're doing right now to finish up the build of our flight model. Right now, everything is working towards being fully assembled and heat cured and ready for environmental testing. So we're working to get those done, and we've fully calibrated both of our FM spectrometers, so we know what gain and offset we're going to program into the spectrometer, and we have those fits that we showed earlier to compare them between environmental tests, and finally for our full comprehensive test, just to make sure that we fully understand what we expect to see from our spectrometers once we get data back from them. And so that's our current work on the FM, and our future work would be to finish the environmental tests and complete for the science team our full comprehensive testing of both of our spectrometers, make sure that we are covering the correct energy range, how we want to see it, and that we know what we're going to see from our spectrometers. Our final delivery date currently is August 11th, so we are pushing towards that.
Yeah. So thank you. You did it.
Next talk is characterizing the L1 in situ observed solar wind originating from the differing source regions identified by ADAPT WSA. Samantha Wallace.
Okay, thank you. I'm going to be talking about the ambient solar wind, so outside of large-scale events. And pertinent to this work are these definitions. So this ambient wind originates from three types of chronomagnetic field. You have the continuously open magnetic field from coronal holes at the bottom here. That's where the fast wind comes from. And then you also have the field that's intermittently open that is at the magnetic open-close boundary, which is outlined here. And that's where the closed field plasma can reconnect with the open field and escape out into the solar wind. This can also happen where the closed field pinches off the tops of helmet streamers, all still at the open-close boundary. But breaking that boundary down, you really have these two types of field, the background quiet sun and the more magnetically active regions. And so I just want to share two things with you about why this is important, and there's more in Vialemborowski 2020, but it's important to break down these source regions in this way for the type of work I'm doing, because these are really the building blocks of all the other language that we use about where the solar wind originates from, whether it be jetlets or coronal streamers. Really, you can break those structures down into these types of coronal field at its source. And the second thing is that each of these sources has unique elemental compositional signatures, and also that plasma undergoes differing amounts of heating. So the coronal holes would produce the coldest solar wind, quiet sun a little warmer, and the active regions the hottest solar wind. So without using, defining the source regions in this way, we're kind of missing those details. But of course, in order to, you can't just know this by looking at in situ data alone. You really need a coronal model to identify the source regions to this degree of specificity. So that's basically what I do. I use ADAPT WSA to do so. So normally I would really explain this for several minutes or something, but I'm just gonna highlight a couple things about ADAPT WSA that are really important that we can't just do with a potential field model for the type of work I'm doing. One is that we're using ADAPT, so this allows us to represent the photosphere and derive the corona at one moment in time versus a time history of over 27 days of a rotation. This allows us to have more accuracy in our results. And the second thing, among other things, is the fact that we're not back mapping the solar wind. What we're actually doing is propagating individual solar wind parcels outward based on this empirical velocity relationship. And this gives us another level of validation for sort of determining the model accuracy, but also because WSA does this in this way, it retains all this sort of quantified information about the source region that you can then use to compare with in situ data, such as how far the solar wind originated from the heliosphere current sheet, from the magnetic open close boundary, the expansion factor along those field lines, et cetera, et cetera. And of course, I didn't mention this, but ADAPT is an ensemble model that statistically represents things that we can't fully observe, like supergranulation and random flux emergence. So it allows us to produce a solution of 12 realizations for the coronal field, and we can then select the best realization from there. And so for this type of work, we are sort of like, we basically use a very tight window in order to use events in our study. So the model drives solar wind speed, and that produced by the model have to be within a 12-hour arrival time window. So there's several periods that ADAPT WSA would produce that we just don't use because we are trying to just provide a preponderance of evidence that we are connected to one of these three sources. So for this study, this is the questions we're trying to answer. What are the defining in situ properties of solar wind originating from coronal holes, quiet sun, or active region? And sort of what falls naturally out of this is, are there even defining properties? There's been several studies, Stack et al. And several others, where they're trying to characterize in situ observations just based on maybe one particular observable, such as solar wind speed or FIP, which is kind of like a proxy for source region, open or closed field, et cetera. But we're actually trying to do this with these, really teasing out the different sources at the open-closed boundary, quiet sun and active region. Also, this begs the question, is solar wind formation driven more by these source regions or by the larger structure it originated from? So for example, do we expect differing in situ properties between helmet streamers and pseudostreamers, or is it more dependent on what's going on in the underlying field? So these are the kind of things we're trying to get to the bottom of. And then also, of course, what do these in situ properties mean about how the solar wind is released and heated and accelerated? So just quickly through our methodology, we're using ADAPT WSA to run several rotations, primarily focusing on 2003 to 11, where we have FIP observations from ACE. So just to start off with, we have 2 Carrington rotations, one in lower activity, one in higher activity. We want to add a couple more before publishing an event study and then doing a larger statistical analysis. But how we're defining source region is based on the model determined distance from the open-closed boundary and the photospheric field strength. So the photospheric field strength at that source region allows us to determine quiet sun from active region, and then how near to or far from the boundary allows us to separate coronal hole from boundary wind. So I'm just showing here the more quiet period, the connectivity derived by WSA, revealing the sources of the solar wind, and then throughout this talk I'll actually focus more on the higher activity period. So I'm just going to step through some results. The next few slides will show a very similar plot to this one. So what you're seeing here, you'll always see solar wind on the x-axis and some other in situ observable on the y. Each circle is 1 hour of data from ACE in situ. And the colors just represent different source regions. So red is active region, Q is quiet sun, or orange is quiet sun, and blue is coronal hole. What else? And so how we kind of do this is, for example, say WSA says we're connected to an active region for this 2-day period. We then go and grab the ACE data at an hourly cadence for that source region and plot every hourly point here. So what we're showing here is that the average composition or FIP enhancement is strongly linked to source region. You can see that just in the averages. You have like the highest FIP originating from active region, then quiet sun, then coronal hole. But really, when you look at the standard deviation and the range of variance you can infer from the max and min values, you can actually see that sort of the widest range of expected values comes from active region, then quiet sun, then coronal hole. And this is kind of what we expect because the FIP enhancement is set lower down than, say, the charge state, so like in the chromosphere. So we expect it to retain more of its signature of its source region in this data. Okay, so this is the charge state ratios. I'm showing 07 to 06 on the left and C6, C5 on the right. I also did C6, C4, but they were pretty much the same general results. I'm just gonna show C6, C5 here, but again, the charge state ratio is strongly linked to source region, but just from my interpretation, I think the distinction more lies between the open-closed boundary and the continuously open field. And you can see, like in the averages, that this is also a proxy for temperature. So the hottest solar wind coming from an active region, then quiet sun, then coronal hole. But when you look at these standard deviations for active region versus quiet sun and the min and max range, they're relatively similar. And this could be because there's actually, something there, like it's just really more dependent on being from the boundary, or it could be that these charge state ratios are set higher up in the corona, so there could just be more time for evolution. Still trying to interpret this. I show this plot with extreme agitation, but basically this is alpha to proton ratio against solar wind speed. And due to the availability of data, I'm only showing one of the two rotations here. So we plan to grab the wind data for this and also add more rotations. But at least from these preliminary results, like it's possible that alpha to proton ratio and variation is independent of source region. Because what we're seeing is that the entire range of abundances we expect from like 1 to 5% is exhibited at all speeds and from all source regions. However, like when you try to compare, we can talk about this more in the discussion, but when you compare this to other work, it's kind of really challenging because we're really breaking it down to hourly levels and one rotation or another, but a lot of the other work on this subject is for much longer timescales, solar cycles, and much more heavier averaging of looking at patterns in the slow and the fast winds. So it's hard to really compare apples to apples there. So we want to add more rotations before we're like, infer some conclusions. But just wanted to say something really quick. We're plotting solar wind speed, not because we need to, because we're using a model, we don't need solar wind speed to differentiate between populations of wind, but it's really to compare with other studies because that's what a lot of other studies do. So just for a second, I want to zoom even farther into like, individual days and things in this study. So this is April to May 2011. And so one of the things we want to do next is make these kind of plots for pseudostreamer versus Helmut streamer. Thank you. But just to let's just look at one pseudostreamer for a second here. Now I haven't really defined a lot here. I'm trying to cover a lot, but this is like a unipolar coronal structure that's releasing solar wind. And so what you're seeing, it's working. Oh gosh. Okay, I'm not doing that. So in the photospheric field connectivity and the coronal field at the bottom in C, basically for this one period we're connected to unipolar field and this large pseudostreamer structure. You can actually see it in EUV movies from Proba 2 SWAP. We're connected to quiet sun, then an active region, then back to quiet sun, all in the same pseudostreamer. And when you look at the in situ observations of FIP, charge state, and solar wind, these green lines are just showing when the connectivity changes. So we're actually seeing in the middle of the green bars that the hottest solar wind, the slowest solar wind, comes from this active region, all within this larger scale structure. And then also we see changes in FIP enhancement as we connect from quiet sun to active region back to quiet sun. So these are basically some evidence that it really does matter what the underlying field is, even in these streamers. This is just another representation of what we're getting at from WSA, is showing the connectivity, the L1 connectivity, as the spacecraft kind of cuts through the structure, quiet sun, active region, quiet sun in the red, and then crosses the heliospheric current sheet shown by the red and blue. So transitioning a little bit, I just want to advertise this, that the SWEB is now a standard output product of the WSA model. I led the development on this earlier this year, along with tons of support from the WSA development team, including Daniel De Silva, who's here today, and also the SWEB guru, Lade Higginson. But basically now, through contacting our team or soon through runs on request at the CCMC, you can now derive these maps of the SWEB, much like other groups in the community. So this reveals the locations of the open-closed boundary in the heliosphere. So you can see that there's a lot more structure than just what you would see in the bottom right of just the coronal field showing the heliosphere current sheet. This is just a zoom in of that same plot, and this is all the same period I've been showing, April, May 2011. So what's unique about doing this with WSA is it's now the only community tool that can quantify the value of Q, which is how we derive the SWEB, related to in situ measurements. So we can actually make time series of Q and compare that to in situ data. So you can see this example here where ACE is crossing through regions of high Q, and that's what forms these arcs in this image, and that's where we really expect structured solar wind to come from. That's formed from magnetic reconnection. So this is just that same time period, but looking in situ. Everything in color is WSA model output, so indicated in red and blue with polarity. So in the top two panels, what you're seeing is that the model drive polarity and solar wind speed agree well with observations, which gives us confidence in the model results. The bottom three panels are composition and charge state, and in the middle is the model drive squashing factor, which tells you when that value is high is when you're at the open-closed boundary. And so I've just highlighted in yellow here all the instances where the Q is high. And what we're seeing is that the slowest, hottest solar wind and the most enhancement in charge state and FIP are really when the wind is originating from this boundary. And these two first yellow regions on the left, this would not be possible to tease out from in situ observations alone because these are from pseudostreamers and there's no polarity inversion in situ. So this is one way this tool is really helpful. I'm basically out of time, so I wanted to talk more about this, but basically, AdaptWSA can help Punch interpret inner heliosphere observations and corresponding in situ measurements based on us deriving the model drive low corona magnetic field and using the SWEB. And I'd love to talk more in the discussion about other tools that the Punch data users would like to see us. We can potentially work on projecting the SWEB onto the Punch data, and so it's not so much to connect with in situ, but yes, lots more that we can do. So thank you.
Thank you. Very interesting. Next talk, final talk of this session is on Punch remote sensing to in situ connections. Heather Elliott.
Okay, so we've been putting actions to different missions. So Dave and Nikki and Anna have been helping with this. So one of the big things is can we leverage the Heliophysics System Observatory? There are lots of heliospheric and solar missions, more than ever before. So we need to find as many ways as possible to take advantage of that. And one key thing is when spacecraft alignments occur, we can get different viewpoints and combine data at different distances. So I'll talk some more about that. And then there's a potential to combine data sets to improve results. And then we can also use in situ to test how well some of the algorithms are working. And then even though we don't have a space weather mandate for the Punch mission, having the capabilities of being able to get the speed and density of the solar wind all along the route means that we have opportunities to at least test and demonstrate some space weather capabilities. Okay, so some of the main type observations that we could collaborate with. We are keeping a bigger master list than this, but these are some of the key ones. Obviously, we have stereo observations. Stereo A is still working and will be moving around on the side. And according to Bernie, you could even be somewhat behind, but as long as you still have a little bit of a side view, he still gets improvements. And then there's SOHO and GOES and Parker Solar Probe and Solar Orbiter. And these are all have EUV. A lot of them have EUV coronagraphs and some heliospheric imaging. And then for in situ, there's a plethora of observations at L1 and near Earth. The IMAP mission is going to be launched kind of around the same time as the Punch mission, which is heavily has like a ton of in situ observations. ACE, wind, SWIFO L1 is going to have another coronagraph, but it also has a solar wind instrument, a magnetometer, and I think some composition. And then, so there's lots of solar wind, IMF, and SCPs at various energies, and solar wind composition from all these instruments. There's more in situ observations now as well, because there are some on a Parker Solar Probe and Solar Orbiter, Bepi Colombo, and also on stereo. The radial alignments are very interesting, but also the algorithms, when we get like speeds, we can compare it to in situ at multiple locations. And we can also look at the radial level evolution in situ and in Punch. And so that's going to be a kind of a first time for that kind of work. And then there are some ground-based observations and other types of observations. So there's IPS, which Bernie has done a lot of work on, and he can do tomography on with IPS in addition to with the heliospheric imaging. And then magnetographs, which are critical for things like WSA, which she just showed you, which also can give speed estimates. And then there's radio burst information, which really shows the shock propagation, which like Radoslav showed some examples of that. And then there's ground-based coronagraphs as well. So I pulled an example of an interesting alignment that would happen in September of 2026. So not too long after, in our first year of observations. With stereo A looking from the side, so that would be coronagraph, and HI imaging from the side, where Punch would be looking from the front. And then at this time also, Solar Orbiter and Earth are aligned, and Solar Orbiter has composition, and then there are composition measurements from in situ at Earth, and also energetic particles at both locations. So there's lots of different things about various alignments, different combinations from different spacecraft. There'll be some times, I think, when like Orbiter and Probe are a little off on the side as well. So I'm going to go through kind of a list of some things that we can do, specific things that we can do, and then I will try to show some as many examples as I have time for. So one big thing is we can not only track CMEs, we should be able to track parts of CMEs, distinguishing between different aspects of the sheath, like the original pileup, and then kind of a part of the sheath that's connected, and then also the ejecta, and maybe even parts of the ejecta on the backside. And so now with all these measurements, we'll also have composition from in situ, which also will give information, more detailed information about possible source regions and energetics from that plasma when it left the corona. And then we can, as I think the previous talk showed, you can understand more about the background solar wind, because we do a lot now already with things like WSA, trying to match with the background. But as she showed, there's still a lot of detailed work to be done. Different coronal holes have produced different speeds based on their size and whether you're on the edge or the interior of them. And then there's still a lot, as several people have already talked about today, like Noor and I think Nikki, the slow wind, is believed to have multiple sources, and there's a lot of detailed analysis that we haven't been able to match up with the previous observations. But if we can do this detailed tracking all the way to the sun, it opens us up a lot. Then there's also this kind of moderately fast wind, which is also interesting, and I'll show some examples of that. And then a key thing that is missing from space weather right now is the longer term forecasts, the multi-day forecasts are are often using solar observations, but from that you don't get a direct measure of how much the solar wind has evolved en route by the dynamic interaction. So this is a unique thing that Punch can do, that a unique set of measurements of being able to measure that amount of interaction that happens and alters the solar wind parameters on the way to Earth is a critical thing. And so we have the opportunity to look at how the shocks develop for the CMEs, and even sometimes the fast wind can be so fast you can get some shocks happening at the CIRs. And then if we can really estimate the shock speed and the strength of the shock, we can start to look at the enhancement of the SEPs at the leading edge of the shocks. Another interesting thing are the comet tails. There are a lot of sun-grazing comets, and Craig has looked at some of the comets in the stereo data, but these tails can be really long. We found some definitive tail crossings that were very distant, like between like 1 to 3 AU, but there's even been a couple that have been 6 AU long, where we found what we believe are tail signatures, and the alignment makes sense. But so if we can look at the length of these tails using the heliospheric imaging, it offers the opportunity to find when another spacecraft might be crossing the tail. And these signatures, if you're only looking in situ, sometimes the signatures are kind of maybe not even noticeable. There have been times where it's been 6 years later, somebody went through the data again and finally found, oh yeah, there was a comet tail crossing. There's a lot of statistical relationships between various solar wind parameters, especially the solar wind speed, and like the solar wind speed and the temperature, and the solar wind speed also correlates with the density, and it correlates with the magnetic field strength, and it correlates with geomagnetic indices and a lot of other phenomena that happen in the magnetosphere and the ionosphere. But we can use these statistical relationships to potentially maybe improve the algorithms to process the punch data, and then also to then work on doing some space weather forecasting. So some critical things, we can look at the size and the arrival time of the CMEs and the shock fronts, which is necessary for a lot of space weather work. And then we can use, if we know the speed really well, we can estimate the density and the temperature and the field strength. And then Bertie mentioned too that you can also use the Faraday rotation to look at the magnetic field strength. And then if we know the shock speed and the strength of the shocks, we can look at how much the SEPs are enhanced at the shock. And then the KP index correlates very well with the solar wind speed, but it also correlates with the density. And then as Nikki had brought up, the UFL magnetospheric waves are driven by the density structure. But basically, there's a bunch of things that we can do on space weather. If we can get the prime part of Punch mission done, it opens up an avenue of using these imagers to do space weather work. There's the edges of the coronal holes produce kind of a more intermediate speed wind, and then also the smaller ones tend to be slower. And so we really do need the detailed mapping to really look at this fine resolution. But also, as I mentioned before, that the solar wind evolves a lot en route. And so some aspects of what you see at L1 near Earth reflect the source properties of the solar wind coming out of the corona, but also how much it interacts on its journey to Earth. And so here's a nice example that shows that you can get on these polar coronal extensions, you get this really super fast wind, and then and that's on one side of the sun with the red outward polarity. And on the other side of the sun, if you have these smaller coronal holes, you can get wind speeds that are kind of a more modest fast wind. And then, but whenever you have different speed parcels of wind. If you have a fast parcel going behind a slow parcel, you'll get a compression. And so that's essentially what a CIR is. And this is like like 27 events. So whenever you get this boundary between, going from the slow to fast wind, you get enhancement in the density and the field strength and enhancement in the temperature. But there are also differences that the slow wind is not as hot, but it's more dense than the fast wind. So by the time you get to one of you, it's a combination of the properties. And so I looked at it like looking at the rising and falling and times in the speed profile, and then you can see that you're systematically hot and dense. And so here, doing that separating by whether it's rising or falling, you can see looking at the density as a function of distance, you separate the rising times from the falling times, but that actually starts to separate in the range where Punch is going to be looking at, so you can really see the evolution en route. And as I mentioned before, the solar wind speed correlates with the density, and it's also, some of the spread in that is related to whether it's, you have something fast running into something slow, or something fast running away from something slow. And so that's what some of the spread is. There's some long-term trends in the magnetic field strength. If you divide that out, then, like as I showed you, the rise in the speed correlated with where the field strength increased. There's a nice relationship that we can use to estimate field strength. And this is just showing that the KP index, which is the color on here, versus the density on the y-axis, and on the x-axis, the solar wind speed. We can estimate KP as long as we can get speed and then an estimate of the density, either directly from Punch or from using the relationship between the speed and the density. This is what Craig did on tracking parts of a CME. And then he went and compared and matched the timing up to the parts, to regions in the in situ observations. And in this, we didn't add the composition, but we need to add the composition because there are distinct composition changes in the CMEs. But this is the kind of detailed work we can do. And then this is an example of what the composition is different in the CMEs versus the background wind. And then this is just showing how at the shocks you can get SCP enhancements. And so if we can get an estimate of the shock speed and how enhanced it is, we can estimate how much more the energetic particles increase in that. And then this is just an example of the comet tails, but I'm out of time, so I'm going to wrap it up and just leave my summary here of the kinds of things we can do.
Thank you. Go to the discussion. So if these speakers could come up on the platform. And Dan's going to handle the Slido, I think.
All right. Thanks, speakers. Great session. I guess I'll just start with a comment from, or a question from Craig that's been upvoted a lot about team cards. Craig, do you want to?
Sure. I'll just read my question. Sherilyn, are you still soliciting involvement for the Gen 2 team cards? And if so, how should people express interest?
Yes, thank you for that question. In fact, we have a collection of our first 18, the deck out on the table there, and a very informal sign-up sheet, but nevertheless one that we're willing. So the phase 2, we're willing to have up to about 50 of these, a full deck. We're very happy with our first 18, but please, if you feel called to be represented on the card and to be used in service to young people, to show them what it takes and the humanity and the skills that it takes to make Punch, a mission like Punch, successful. We would love, if you just feel an inkling, come talk to us and we'll set you up.
Quick follow-up. This is not a vanity project. Do not feel embarrassed about putting your face on a card. We are trying to model the behavior and appearance of scientists for young people, and it is very effective. So please consider signing up.
Absolutely. Thank you.
Let's stay with Sherilyn for just 1 second. Sarah has a really interesting comment.
Yeah, this is something for everybody in the room. It's I realized, yeah, she put up the Annie Maunder longest ray, which was a sketch that she made, Annie Maunder made from observing a solar eclipse. We have that original image. We also have the original butterfly diagram in this building. So I encourage all of you to go upstairs and take a look at it. It's, if you go upstairs to the 3rd floor and follow the signs to 3131 or 3150, outreach folks, this is where you've been breaking out. The all-gender bathrooms are right in between those two, and if you stand with your back to the bathrooms, you will see the original with some very cool history there. It was basically gifted to HAO.
And that's where our outreach breakout room is, everyone. So let's make sure we see it. Yeah.
Yeah, definitely make sure you check that out. I think that's really cool. Let's jump to, excuse me, a couple of questions for the STEAM students. I think I saw John Keller here.
To the right.
Where are you? Sorry, there you are. Okay. Here, let me give you the mic and you can ask your question.
Yeah, I was just curious about the number of students and how long students have stayed aboard with the STEAM development and what the plans are post-launch.
On. Okay. There's been about 40 students. I did push the button. The green light is on. Is it working? Okay. There's been about 40 students on the STEAM team in total. Because it's a student team, people graduate, people move on. So the average involvement is about a year and a half. Some people stay on the team longer. Gabrielle and I have both been on the team for 3 years. But average involvement is about a year, 40 students total. Post-launch, we are likely going to still have an avionics team and a science team to analyze the data that comes in from Punch.
Let's stay with STEAM for a minute. There's a couple of questions about the STEAM data. Craig, do you want to take your question about the SDAC?
I'm just poking you. Are you planning to archive the data at the SDAC with everything else?
Yes. Yeah, we plan to make it all publicly available, just like you guys. Just like, so, yeah, we follow your example. And I do think there's another question about our data, so I don't know.
Yeah, I was going to go to that one next. Ritesh.
It was just regarding the data, like how soon will it be available, like processed and different levels?
Well, we first have to launch, and then once that happens, I think it's going to be within a year because we're already working on the data analysis code. So once that is complete, which we will be working on, that's what the science team is still around for after post-launch, the turnaround time should be relatively quick.
So the data will be available with the Punch data, and we will upload a data pipeline, essentially.
So I would be remiss as the Punch SOC lead if I didn't encourage you guys to talk to our SOC team, Marcus and Ritesh, and who else is back there? I can't see you all. Chris Louder. We want to integrate your pipeline into our processing pipeline and make sure the data come out really quickly and get publicly available. So let's, sometime maybe at lunch or something, we can chat. Okay, since we're already with Ritesh back there, you want to ask your other question, Ritesh?
It's for Heather. Like you mentioned one alignment of 2nd September 26, and solar orbiter is very much in line with the Sun Earth. So you mentioned that you can have a comparison between the solar orbiter and L1, but I believe it will already be leaving ecliptic. So how?
Okay, yeah, I didn't look at how far out of the ecliptic it will be that, and I don't know that orbit well enough to know offhand like what that is. It could put us in a different regime, like a different type, different structure, but I have to look at that. But yeah, but definitely we can use those we definitely can use different measurements at different points to at least test the output of the tomography.
Thank you.
Okay, let's shift. We got a couple of questions for Samantha. Let me get, Barbara, do you want to ask your question? I know you're busy managing our Slido.
You surprised me. Yeah, so I was really excited to see how you were able to do that study, but when we were trying to do it, we had trouble. The models, some said it was AR, some said it was quiet sun. Is it much better now at discriminating definitively whether it's an AR source or it's a quiet sun source?
There's a couple of things there. So basically, we're choosing thresholds to do that. So we're using the photospheric field at the foot point to say we're in quiet sun and we're active region. We've played around with that a little, and the numbers we've chose seem to work well. What else? If you're using ADAPT also improves the prediction. There are some, I didn't get into this, but it's in my backup slides. There are cases where the model will always connect, this type of model will always connect you to open field, even if it's at the boundary. So it just means that, the closed field's still getting out, but we can only connect to open field lines. And so what winds up happening is that sometimes you have a large helmet streamer that you're connected to at the boundary, but embedded within that, at like the ecliptic, is a network of active regions. And so we've tried to account for that. I didn't get into that too much, but the connectivity will say quiet sun, but when you really look at the bigger picture of all the output, you see there's a lot of activity, like active regions embedded within that. And then I changed the classification to an active region, which really is only possible for a case study. Like I can't run my automated code and then do all that. So there is that limitation, but we're trying to account for that. So.
Let me just jump right over to a live question in the back of the room. Here you go, Lika.
So this is related to the talk that was on connecting remote sensing in situ observations, focusing in situ. There was a slide on the kind of data that would be utilized. Mm-hmm. And so is the goal here that you're using only sort of NASA heliophysics supported missions, or is there more? Because there are, Aditya L1 is going to launch soon. Australia has incredible radio observations. I think that would be awesome, kind of fed into this. So I was just curious how you are accumulating this information.
Oh, yeah. We're not necessarily going to limit ourselves to only NASA missions, and we're just getting going, and we need to establish the connections with specific people. And so we need to present this, at other meetings where we can try to get more engagement. But yeah, we're not limiting ourselves to only certain groups or anything like that.
Okay. This follow-up?
Yeah, just to say, in January, we had a telecon where we specifically invited folks from all sorts of missions, including Aditya and others, and it was really, really cool. And we had just sort of a conversation with a lot of different people, and that's something we're definitely pursuing. And also this afternoon, we have a talk by Deepankar Banerjee, and he's going to talk a little bit more about the international connections.
Okay, I want to mix it up. It's very rare for the panel to ask a question of the audience, but Sherilyn has a question for the audience about their perspectives. You want to take that, Sherilyn?
Is that a rookie? Okay, so I'm curious if anyone has any speculation. I mean, we can never know for certain, but that tail-like feature in the lower right quadrant of the eclipse petroglyph, there are a lot of contextual reasons to give it a solar-esque interpretation. And the curly key motif might be, representative of the sun more generally, and we're using some pottery. But we want to represent this well in planetarium films, a kiosk model, and online lessons, right, about the site that teach basic science of the sun's motions and so on. And so really interested for this group to weigh in on what is that long tail-like features that undergraduate students at CU helped us to even see by making that 3D model.
Go for it.
I could. Yes, that's very interesting there. Ed Cliver and I studied 100 years of eclipse observations and found CMEs in them, maybe at the 10% level. And some recent eclipses have also had CMEs where you had good time coverage. You could actually see them moving out in a couple frames. So yeah, I would interpret it as a potential coronal mass ejection, but obviously we'll never know for sure.
Right.
But there is literature that supports that, Eddie. at total eclipses.
Craig, you want to weigh in?
I just want to ask a question. I'm no archaeologist. I don't know of any in the room, maybe the GB. But is the marking intentional? Do we know that it was actually pecked in the rock versus just being a blemish?
Yeah, this site has been very closely inspected by rock art specialists associated with Chaco Culture Park. And you can see that the pecking is similar. It just had faded, right, and eroded. And when the students made the 3D model and exaggerated the depth, right, this emerged. And I've been back recently to say, wow, is that really there? It hadn't been perceived so easily. But it really, it's genuine. I'm very persuaded, yeah.
Alphonse has a question or a comment?
Yeah, I'd have to see again the curly cube business, but there are these cavities that form below the CMEs that Dave was just talking about that erupt out, and Sarah Gibson has done a lot of work on those. And at least in picture or two that I have, I can see such cavities before the eruption. So I don't know if they're actually visible that way during the eclipse, because who can remember that exactly? But that might be there too. So that might be another possibility.
Interesting.
Let's go over to Lika here.
So I had a question too. So I think we know roughly the date, right, of the petroglyph. Can we go back and establish, what phase of the solar cycle this was happening? And the other would be, that just increases probability, right? It doesn't mean if it was in a lower phase that we couldn't have had this. So we heard about CME, but it could also be, CMEs are so faint, is harder to observe with naked eyes, but it could have been tethered long prominence that are really visible. So who knows?
So to address one point you're making, there has been independent means by Vaquero and Malville in a 2014 paper that has researched what the solar cycle might have been, and the best estimate for maximum is 1098. This eclipse occurred in 1097. So if it is a representation of a total solar eclipse at a time of high solar activity, which we also have coming up, right, in 2024, right, time of high solar activity, total solar eclipse. But yeah, you can determine that it was a time of solar maximum when that eclipse they could not have missed did occur. 1097 is also a time of high human activity in the canyon, the time of high Chaco culture.
There are many other examples of ecliptic representations in both Europe and...
Could you speak up just a little bit, please?
In both Europe and China and other places, even in Africa. Do any of these other representations have similar morphology?
Right, and naked eye, right? These folks are not using, any kind of magnification, right? Could that really? And we know in the 1860 eclipse, right, the hand drawings of 1860, that Temple perceived what we now know is a CME, right? You look at the Argentinian 2020 data, and there's that ovular feature that he perceived with his naked eye in 1860. So, so it becomes very interesting. Thank you for that comment.
Let's stay with the outreach stuff, but sort of shift gears for a minute. I'm going to put Amir on the spot to answer another question from the panel to the audience.
Do you want to ask the question?
It's there. So can you comment on Citizen Kate?
Sure. Thanks, Sherilyn. The check's in the mail. Sherilyn alluded to Kate. Kate is it's a community participant project where we will be deploying 35 or more telescopes, cameras, and other equipment to communities along the eclipse path in April 2024. And the special thing about those cameras is they're going to be making measurements in 4 angles of polarization. So we'll be able to get all 3 linear Stokes parameters with that measurement over the course of about an hour. Unfortunately, Punch won't be up at the time, but Kate will be observing from about the solar surface out to about 3.5 solar radii, depending on how you're measuring on the detector. And we're going to be measuring very similarly to what Punch will do. So we're hoping to be able to resolve 3D structure. We're hoping to be able to look at flows and other dynamics. And it will serve as a nice test bed of data for future Punch simulations, for example, because Kate is looking at the source regions of what will then eventually flow out into the Punch field of view. And I think it'll be really interesting to see how Kate in future eclipses or similar measurements at future eclipses can support Punch once it's up. And of course, it's a huge outreach program, so it's doing outreach in a different way than Punch. It's leveraging different kinds of community connections, but it gives people a chance who would not otherwise be doing quality scientific work to participate in a scientific endeavor in this way.
Thanks, Amir. Let's stay on a sort of thematically related question. I'm going to hand the mic to John again.
So just was hoping you could share more about the outside collaborations beyond just the core collaborator that we've been working towards growing with this Punch outreach mission.
Yes, John, thank you for that prompt. It's very important to us to radiate our goodness beyond the region, and our Stone Soup Collaborative will benefit all of those institutions I showed you on the map and the people in the region, but the intention very much is to have a series of dissemination partners. For example, the Astronomical Society of the Pacific, the American Astronomical Society Eclipse Task Force. We've been working closely with them. There are also NASA-sponsored science activation projects. John is the PI of one of them, which Science Through Shadows, for example, where we have synergy with projects already funded by NASA. So we are in several wonderful handshakes. Another one is the SciAC, the Infiniscope effort at Arizona State University. That's going to, we hope, we just put a proposal in to be one of their flagship projects using the photogrammetry data on the solar observing site that I featured there with the eclipse petroglyph. And they're very interested to make that one of the NASA flagships. So we have a lot of good handshakes. Also NASA communications. The NASA TV folks are coming next week. I just got an email about how to interview us in order to put our ancient and modern sun watching theme on the annular eclipse broadcast in Albuquerque. So they'll be broadcasting from the Balloon Festival in Albuquerque, and we will have a 2-minute spot, and we hope Nikki Weil will also be our spokesperson for Punch and Punch Outreach and heliophysics probably in general. And looking for others to contribute to the wealth of opportunities in New Mexico. Thanks for that question.
Thanks. Let's, oh good, more questions are appearing. Let me go to a question that's been up here for a little while from Craig to Samantha.
Oh, this is just me throwing a chair in the ring to make things more exciting. Heather and several other people and your slides have all talked about the high-low speed distinction maybe not being the right way to cut with the Aristotelian knife. Do you have any ideas on better nomenclature for the types of wind we see?
Yeah, so I think, what you're referring to is like these, long-standing papers, mostly out of Michigan, that are where charge state is inversely related to speed, and FIP at one point was also thought to be the same, but now is more like there's a bimodal distribution of FIP versus a more continuum. So I would say that those things are still true on the scales that they are, averaging on, like solar cycles and things, and that's kind of really. You need to do things on those large scales initially in any field, and now we're, in the era of the details with Parker Solar Probe, Solar Orbiter, and all these new tools. So like we're kind of digging into it more. I would say that it's more of a casual way of describing it, and it doesn't really get at the why. It's not like the wind is fast, therefore like causality. There's no causality between the speed and the charge state, but I do think there is a better way of describing solar wind. I think Nikki's the Violin-Borowski paper tries to get at that. Like if we can really talk about source region using all the same language, like active region, quiet sun, coronal hole, open closed boundary versus continuously open. If we can all start kind of using that language, it might be less confusing, especially for those coming up in the field who are learning all this for the first time, and then we're telling them, no, don't do that. So, yeah.
Yeah, I'd like to comment a little bit. I think this is an area where combining the data sets will help, get some of the fine detail that we haven't been able to resolve. And so like we have the current mapping techniques, but the tracking also can provide some of that detailed alignment information. And then we can also look at the composition to see, like, is it lining, does the composition boundaries line up with the boundaries that we're seeing in either the WSA source surface type mapping or the tracking.
Yeah, I just want to follow up a little bit, because you're right, and there's all these different ways we talk about it, and I think what it comes down to is which physics question you're asking. And that's what Joe and I tried to pull apart. Whether you want to know, did it come from an active region, that has certain physical consequences in terms of the type of solar wind it makes. And the speed that it reaches is just one of many physical things that happens to that solar wind. And so that last phase acceleration that makes it either a fast wind or a slow wind is just one of the things that we're interested in. And now that we have the details, and with Punch we're really going to have a lot of details, you can ask different physical questions about, the type of turbulence or the type of structure or the type of all the things.
Yeah, I just want to add that, like, didn't have a lot of time to do this, but we're not done. So, like, we want to compare source region and density and alphanicity and all these things. So stay tuned for other summer meetings, I guess.
You don't want to add anything else to that? Okay, John.
This is just following up on the same conversation, right? Like in the planetary science world, how you define a planet, whether you're a dynamicist versus a geologist, is part of the ethereal debate we deal in planetariums all the time about Pluto. It's interesting just to think about, like, you need different names for different types of physics and science you're trying to do, and I think I really appreciate being open to the both and multiple ways of description, as opposed to getting locked into just one definition.
Yeah, I think with this new way of describing the solar wind, it's like we're really trying to get at the physics and not just defining something on an observational, definition.
Anybody else want to follow up on that? Okay, we've got let's see. We've got a couple more questions here. Is Sandlin in the room? Let me give you the mic, hang on.
Okay, Sherilyn, this is for you. If you could talk about a little bit about more engagement that people can do right now all the way to the eclipse. I think we focus a lot on the eclipse, but there are things that collaborators and team members can be engaged in right now, and just to tell people about that.
Well, yes, and I'm going to throw it back at you a little bit to talk about some of the new opportunities you informed me about this morning regarding the need for heliophysicists to be out there. We are always interested in your input and feedback on our products. If you go online and see something that intrigues you, you don't have to look at all of them, but if something is of interest, please feedback to us on that. Also, this conversation that I hope will be ongoing, I'd love to get your paper, David, and regarding the interpretation of a site, it's going to show up in a lot of products, and we want to make sure that we're saying things that are consistent with current scientific understanding and not speculating too broadly beyond that. And also, Sandlin, let me ask you to say something about the I think there are two opportunities with the Astronomical Society's Pacific Eclipse Ambassador program and also Andy Fracknoy's effort. Please go ahead.
Yeah, so there is a NASA-funded SACT award for what they say off the path, and it's not asking you to be off the path on the day of the eclipse, but the Astronomical Society of the Pacific is looking for everyone, so undergraduates, and beyond to help engage different audiences. So we'll send out a statement of interest, but they will give you materials. The other one was funded by the Moore Foundation. It's run by Andy Fracknoy, who is very big in the outreach world, and they are looking for people to support libraries. Again, it does not need to be the day of. We're talking about the next couple months all the way, so we'll send both of those out so you can be engaged.
Thank you.
Okay, Sherilyn continues to break the paradigm. We've got a panel-to-panel question now.
Yes, so at one point we talked with Mary Hansen in the proposal stages when she was the STEAM program manager, and now she's at SWRI, or Southwest Research Institute, and we know there's a turnover. But we also know that near-peer interaction between, young undergraduates, it's closer in time, right, to the K-12 realm, and so just wondering if there's any activity or interest in that kind of synergy. We could come over with a load of toys and have a little training and stimulate your outreach effort for Punch if you so wished.
Yeah. So we're with the Colorado Space Grant Consortium, and they do a lot of things for outreach. A lot of people come to our building or floor to do things, and I do know that a lot of us do outreach through the University of Colorado, since that's our home institution. But yeah, yes, that's the answer.
So I guess that's just a let's talk, Mary. I'm sorry, I broke the paradigm again, Dan.
I was just going to say also that Space Grant does a lot of work with community colleges in the area. So if that's something that you're interested in getting outreach to, that could definitely be a conversation with the STEAM team and also Space Grant as a whole.
Mm-hmm. Yeah, we'll be going to the American Association of Physics Teacher Conference with our pinhole, 3-hole design on the pinhole projector, and doing a lot of indoor demos as well as outdoor with them. And so community college level is definitely relevant as well.
All right, the clock is starting to run out on this session. We could probably take one more question from the room if there are any. Otherwise, I will just draw everybody's attention to Barbara's comment up here that the questions are going to reopen. People can engage online. If you ask something and you want to follow up, you can reply. And I guess the speakers can also check the questions and follow up on their own responses. So Craig or Sarah, anybody, you want to make concluding remarks?
Thank you for this wonderful session, and we reconvene at 1 o'clock after lunch for the poster session.
All right, thanks everybody.
Okay. Okay. I just want to let everybody know that we were able to get a session that's related to punch for AGU. And so our session title is Interpreting Remote Sensing and In-Situ Observations to Build Global View of the Corona and the Solar Wind. And so we'll be sending out all the regular advertisements like SPA and such for the session. Okay? Oh, yes, yeah. Submit your abstracts.
Good afternoon. Can you hear me properly? Okay. So welcome to section 7, Punch Connections, and I've lost my, oh, there it is. We have 3 invited talks and 1 contributed talk. The first one will be given by Elena Provornikova from Johns Hopkins, and the title is Advancements in Modeling the Global Inner Heliosphere and Interplanetary CMEs in Preparation for the Punch Mission.
Well, this is my summary slide. Okay, that's my first slide. And let me just go in. So you all saw this graphic. So as we discussed in many previous excellent talks, the 2 main punch science objectives are to understand how coronal structures become solar wind in the inner heliosphere, and also understand evolution of transients like CMEs and associated shocks in the inner heliosphere. So to get an idea what we will see with punch in the inner heliosphere, we can use models of the inner heliosphere with propagating CMEs and see different scenarios, how CMEs with different characteristics propagate through the inner heliosphere solar wind, which is structured by itself. So how models are helping to prepare for punch? We produce MHD simulation cubes that can be used to generate synthetic total brightness and polarized brightness data to develop SOC data products. We can provide input for flow tracking algorithms together with the ground truth data, and also provide synthetic data for tomography techniques, and also to test methods to determine chirality of the CME flux ropes. So how will punch data help us to advance models? Punch will provide constraints for CME properties, including magnetic properties near the sun, and also punch will provide velocity maps to validate models, of course, density structures and shock properties, and many more. So now let me go briefly through the methodology and assumptions which we use when doing simulations of the inner heliosphere. Inner heliosphere typically refers to a region between 20 our sun and up to 1 or 2 AU. So we are beyond alpha zone, meaning that in the model all information propagates out, nothing propagates in. Inner heliosphere models require, of course, boundary conditions at 20 our sun to drive the solar wind, and those can come from either full MHD models of the solar corona or semi-empirical model of the solar corona. And yeah, I have a couple examples here: the MHD corona from PSI group, and semi-empirical Wang-Shili RG model. So both typically use the photospheric magnetic field maps at the sun to reconstruct the magnetic structure of the corona. And so here on the right side, this is an example of the inner heliosphere simulation driven by output from the WSA coronal model. And of course, the inner heliosphere simulations can be steady state, meaning that the solar wind is driven by one rotating map at 20 hour sun, or time dependent, meaning that those maps are changing in time. So when we model propagation of coronal mass ejections in the inner heliosphere, so first we simulate the solar wind background in the inner heliosphere, and then we have to use some CME model. And of course, depending on the science questions that we want to answer, different CME models can be used. And typically, it could be a CME model, which is hydrodynamic. So it's basically the enhancement in velocity and density and pressure that drives the CME through the inner heliosphere. Or it could be CME model that accounts for internal magnetic field. And so here I have a couple of examples. On the left, of course, Enlil plus cone CME model. In the middle, it's our own Gamera inner heliosphere plus Gibson low CME. Which accounts for internal magnetic field. And also, example on the right is the European Euphoria model with a sphere-max CME. And yeah, so this slide shows a little bit more details in how we simulate propagation of coronal mass ejection in the inner heliosphere with Gamera and Gibson low CME model. As I said, first we generate the global structure of the solar wind in the inner heliosphere between 20 hour sun and 1 AU. And then we start emerging the CME with internal magnetic field flux rope, which is described by the Gibson and low CME model. If we want to model the particular CME event, then we can utilize the CME white light imaging observations and get some constraints on parameters of the Gibson low CME model. For example, the angular width, how fast CME moves, and what's the orientation of the flux rope. So on the right, you see the example of such simulation in 3 dimensions. Gibson low model is really wonderful. It gives you a 3-dimensional analytical solution, which is quite easy to implement and couple with inner heliosphere model. And also, it has a stretching parameter, which enables simulating different magnetic topologies of CMEs. And also, it has a number of other parameters that we can change and see how CMEs with different properties propagate through the inner heliosphere. And as Annie showed yesterday, we used these coupled models, Gamera and Gibson low, and we did a few simulations for the CME Challenge version 2.0. So this is one of the examples of such simulation. You can see the CME right here propagating out. So this is radial speed, normalized density, and normalized magnetic field. So those simulations were done with our so-called default resolution, which is 256 in radial direction, 128 in polar, and 256 in azimuthal. And with this resolution, we can resolve the kind of global structure of the CME, global geometry and shape, and also the you can distinguish the sheath and the large-scale structure of the shock. But as Phil showed in many other previous talks, with recent observations from Whisper and Parker Solar Probe and also Solar High from a Solar Orbiter, we see that those observations reveal a lot of structures in CMEs and also structures associated with CMEs interacting with the background solar wind. And those structures persist at a few tens of solar radii from the sun, so at quite large distances. So this motivates us to do more detailed simulations with Gamera. And Nikki discussed this in detail earlier today. Punch will characterize mesoscale structures Punch will determine how much and what types of mesoscale structures propagate from the sun out to the inner heliosphere and what types are developing en route. And I just want to clarify, when we say mesoscale structures, we refer to structures with scales about 10 to the 4, 10 to the 6 kilometers. And to model development and evolution of mesoscale structures in the solar wind, or those associated when CME interacts with the solar wind, require high-resolution simulations. And one of the questions that we posed is what types of mesoscale structures can develop as CMEs propagate in steady-state solar wind background. And so I'm going to show you a couple of high-resolution simulations. So the first one is with a resolution 1,000 by 500 by 1,000. So it's 4 times finer than simulations that we provided for the Punch CME challenge. So with this resolution, we're entering the inertial range. So resolving structures with scales around 10 to the 5. And in this particular simulation, those plots on the right show you boundary conditions that we use to drive the solar wind. So this is a 20-hour sun, latitude, longitude maps. So the top plot is radial magnetic field, then radial velocity, density, and temperature. So those are used to drive the solar wind in the background. And for CME, we used the simplest possible magnetic configuration in Gibson Low model. So we used the SphereMag, and it was emerged around here with velocity 900 kilometers per second at the front of the CME. And yeah, so you can see this movie. So what quite amazing is, so again, let me orient ourselves. So here's the radial speed. This is equatorial slice through the 3-dimensional solution. This is speed, density, temperature, and radial component of the magnetic field. You can see how strongly this spherical SphereMag CME is distorted as it propagates in the also very structured solar wind background, because we really resolve those. You can see those kind of Parker spiral, a lot of Parker spiral-like structures in solar wind streams. And so this image on the left shows the snapshot when the CME approaches 1 AU. And you can see that nothing is pretty much left from that nice spherical SphereMag. The structure of the CME-driven shock is quite complicated. It's and you also can kind of see that the shock strength varies across the surface of the shock. The sheath also has different width, and it has all sorts of different structures in it. Also behind the CME, when the solar wind kind of pushes against the CME, we see the compressions form, and also this faint shock. And next slide shows the same simulation, but we're looking in the meridional slice through the 3-dimensional solution. So here's our CME. And so yeah, as I said, the structure that we emerged is completely destroyed. You can see that, you can kind of see right from the beginning that the front of the CME looks like a lot of fingers in the front of this. Thanks, Nikki. So we think that the irregular structure of the CME front, which is probably the sheath, it traces the interaction with the fast and slow solar wind streams in the background. You can see it right away as it emerges into the solar wind. You see those like fingers forming at the front of the CME. So one of the interesting questions that we could look in the future is how does this distorted CME and all those mesoscale structures that form in the interaction, how they look like in polarized brightness image. And so the resolution 1,000 by 500 by 1,000, it's not prohibitively expensive. And we went ahead and doubled it in each direction. And this is the super high resolution, let's call it this way, which resolves spatial scales on the order of 7 to 10 to the 4 kilometers. And again, you can see that the spherical CME get distorted quite significantly by the background solar wind streams. You can kind of spot the shock here at the front. It's very faint because in this case, the velocity of the CME at the front is comparable to the velocity of the fast streams in the background solar wind. And also behind the CME, when solar wind pushes against it, there is a number of discontinuities that we can see forming behind the CME. So this is quite exciting. We just obtained those results, and we are looking forward to analyze them more and identify types of structures that form in the interaction of the CME with the background solar wind. And I just conclude my talk. So Gamera plus Gibson law integration provides physics-based simulation of ICMEs for punch analysis and to mimic the future data products. Newly developed integration is efficiently parallelized and scalable, which enables us to run high-resolution simulations of CMEs in the heliosphere. And we see plenty of structures that form around the CME-driven shock in the sheath and behind the CME. And in the future, we could provide, it's up, yeah. In the future, we could provide solutions to track flows in the solar wind with ICMEs to a flow tracking team. And also, it would be interesting to see how those mesoscale structures look in total brightness and polarized brightness images. Thank you. And go punch.
So the next presentation will be given by Donald Schmidt at the University of Colorado, titled The NOAA Quick Punch Project. Is also an invited talk.
Okay. Employee of the University of Colorado, the Cooperative Institute for Research on Environmental Science, and so I'm kind of sharing this presentation with my co-authors. So we're talking about kind of a NOAA-funded project here. CERES is a cooperative institute, and so just kind of standard disclaimer here. I am not speaking for NOAA, but this is what my impression is of everything that's going on at NOAA. So I think it's kind of useful for context to understand a little bit how NOAA is organized. I think when people think about space weather in NOAA, they typically think of the Space Weather Prediction Center. In fact, there are 6 different line branch offices of NOAA, the Weather Service being one of them. The other one that's kind of important for the context of Quick Punch here is NESDIS. And so kind of they have kind of very different mission statements and how they kind of affect things within NOAA's space weather apparatus. And so the Space Weather Prediction Center, what do? They produce space weather forecasts and they develop forecasting tools primarily. The side that I work for is the National Center for Environmental Information, and our large-scale role is to develop and maintain the data pipelines for NOAA assets like GOES or the upcoming SWIFO mission. So we deal with primarily calibration and trending. We also do some validation and verification work. In the context of the Quick Punch project, I'll be talking about OPA is another thing to keep in mind, and so this OPA is now becoming the Space Weather Office, and they're actually the group that kind of oversees and manages studies that have to do with NOAA's capabilities going into the future. So NOAA currently is very reliant on a NASA asset for doing CME identification and tracking, and that'd be LASCO, both C2 and C3. And for many years, it's been, SWPC has been relying on this data set for CME identification purposes for many years, and it's been known for the past decade that we shouldn't be relying on this anymore, that SOHO was launched in 1995. It's it's going to die at some point, so we have to be prepared for that future. And I think the last I had heard is that that's currently planned is December of 2025, so the end is nigh, right? So since 2018, NOAA has been moving forward, commissioning their first set of their own coronagraphs. These are called the UCAR instruments, and so there's 2 of these instruments being built at NRL and provided to NOAA. The first one is going to be flying on GOES-U, and that's supposed to launch in April of 2024. And the second will be on the SWIFO mission, which is ride sharing with IMAP later in 2024, 2025. Okay, so those 2 coronagraphs are kind of the primary way that NOAA is planning for life beyond SOHO. I will also say that, so NOAA in 2019 funded an internal study where they tried to identify critical gaps within their space weather forecasting apparatus. And so part of that study came out, so what other methods could we possibly use to detect CMEs? And so one thing that's been used and has been pretty interesting is the use of the SUVI instrument, which is part of the GOES-R suite of instruments. And this is an EV telescope. You can off-point up to 5 arc minutes and record the essentially CMEs in the extreme ultraviolet. And it's kind of surprising that this works, but it's actually been produced a very interesting set of science papers led by Dan Seaton. And, but yeah, so that is one mitigation strategy that's ongoing. NOAA has also considered the idea of using other NASA assets to address this gap. One would be stereo A. Of course, that's only for short gaps in time where the stereo A is on the Sun-Earth line. And PUNCH would be the other NASA asset that would theoretically be useful for this kind of CME identification. There's also interest in working with coronagraph data from Aditya and also funding a coronagraph to go on ESA Vigil, which I believe is moving forward now. Okay, so what is Quick Punch? So Quick Punch is this a study which is being funded to produce a kind of a proof of concept deliverables. And so kind of the short, the kind of short and to the point synopsis of what Quick Punch is supposed to do is really a test of whether SWIRI can deliver data to SWIPSI that meets operational requirements. And so you can kind of break those requirements into kind of a group of 4 different things. One would be processing latency, one would be data reliability, one would be the calibration quality, and then the 4th would be the compatibility with SWIPSI tools. And so I will say that this is kind of a preliminary study meant to show that the punch data can actually attain these qualities. And if punch were to be relied upon to be an operational asset, the bigger issue that has to be overcome is this idea that there's a bottleneck at the downlink schedule. And if SWIPSI actually needed to rely on punch data, can we actually get data at the schedule that SWIPSI requires? So as part of this study, we've laid out the basic specifications for what the Quick Punch data will be. The NIFI data is essentially being provided as is. We've reduced the resolution to 1024 by 1024 pixels. NOAA's asking that it be provided at a 4-minute cadence, and we're just using the unpolarized data products. We're also asking, so that'd be the primary data product, which is essentially replace LASCO C3 for forecasting. We are also interested in getting a WIFI mosaic product, which would go out to 80 RS, again, downsampled to 1,000 pixels on this per side. That would be provided at 8-minute cadence and again be total brightness only. So both these data products would be produced by the Punch Data Center. Essentially the latency requirement that we currently have would be that there's 2 hours from when the data arrives at a ground station to when it's being provided to NOAA. I will also point out that this data would not be proprietary to NOAA. Anybody could use this data. NOAA is funding it to be produced, but this is open source. And so just to kind of give a broader context here, this is again not my area of expertise. I'm within the calibration wing of NOAA. But so how is this corona data actually used at SWIPSI? So the basic way things are used is that a stack of images is converted into a fixed difference movie using the CAT tool, the CME analysis tool. That tool, I'll show you a picture of kind of what the user interface looks like, but that tool allows a forecaster to fit the shape of a CME to a propagating, or to a linearly propagating and expanding cone. That expansion rate of the cone is then turned into a velocity. So taking a stack of images, doing this running difference thing, and fitting a bunch of different cones to the data, the output winds up being an eruption start time, the longitude and latitude of the CME base, the expansion angle of the CME, and its velocity. So those CME parameters are then fed into a heliospheric model, a WSA-NLIL joint model, and then essentially that CME is then propagated out into the heliosphere, and the ultimate decision is, or the ultimate data product is the decision about whether or not an impact is expected at Earth. And these heliospheric models are updated every 2 hours and propagated 10 days into the future. And so just to give you a quick look at what the tool currently looks like, this was written in IDL, I believe, but you can see in the lower right-hand side, essentially the linear fit to velocity. In the upper panel, we're looking at LASCO C2 data and then stereo data from a point. This is a CME that was viewed in quadrature, and so the tool does have the ability to take in multiple perspectives. We expect that this will be useful for the upcoming Vigil L5 mission. So this is my last slide, and it's really just kind of conceptually where do we go from here. And again, I'm not my CME science is not my forte, so these are kind of what I think are the open questions that really might impact the ability to be forecasting with punch data. So one, I think WIFI data is very interesting, and it's the idea of a much wider field of view. None of the forecasting tools currently have been tuned to work in this wider field of view, and so I guess the question is there significant value added from incorporating WIFI data into forecasts? Can the polarization information that's available to Punch be used for forecasting? Matt West, I know, is PIing a research to operations proposal on this topic, and I think that's very exciting. And then in terms of on the modeling side, I guess I think right now the observations actually have a significantly more detail than it's being incorporated into the models, and so it's an important question of figuring out which exact detail is going to be the most value, or is the most important to incorporate into these forecasting models in the future. So yeah, that's my talk. Thank you.
Okay, so the third talk is also given by Matthew West of Southwest Research Institute.
Hi, everyone. Can you hear me okay? Fantastic. Right, so I'm going to be defining a whole region in 15, and that's, you might want to play this back at slow speed afterwards. So I'm going to be talking about connecting the middle corona to what we're going to be observing with punch. And, it's not going forward. There we go. Nope. Okay, there we go. So I thought I'd begin with a very quick what and where is the middle corona. The term has been thrown around a lot in the last few years, but I'm sure that not everyone in the room is going to be fully aware of what it is and what it encompasses. So before I go into the middle corona and how we observe that, we've got to define how we observe the inner and the outer corona. And so with the inner corona, we generally observe this through EUV and X-ray observations. And the outer corona, we typically observe with coronagraphic, visible light, and ground-based eclipse observations. And here you can see one of our kind of more traditional composite observations where I've combined a swap EUV observation in the center with a LASCO C2 coronagraph observation around the edge. And I just want to make a point here. We like to combine these two sets of observations, EUV and visible light observations, but they capture different physical characteristics of when you're going to be tracking structure. Observations capture emission measure within a specific temperature range, whereas visible light observations capture more of a temperature-independent electron density. So this is worth bearing in mind when you are tracking structures from one to the other. Sometimes things don't tend to line up. So the middle corona is this region which extends from 1.5 to 6 solar radii, and it crosses both of these regimes. And it's this region that encompasses almost all of the influential physical transitions and processes that govern the behavior of coronal outflow into the heliosphere. This includes the solar wind, eruptions, and flows, all the things that Punch is going to be observing. And let's begin with solar wind speed. It's within the middle corona where observations tend to indicate that we see the velocities increasing, both for the fast and slow solar wind components. And this height is largely dictated by the interplay between the open and closed magnetic fields, their origins and boundaries, and the open flux corridors, which leads me into the first kind of major transition that we see within the middle corona. And that's this transition from the predominantly closed magnetic field structures of the inner corona to the mainly open structures that we see extending out through the outer corona and the heliosphere. Related to this, we have our derived plasma beta properties, which vary in different regions, but I want to focus on the quiet sun regions, which vary from low to high throughout the middle corona. It's the region where we see peak CME acceleration. I'll show this a little bit more in a second. And semi-related to that, we have eruptive flare reconnection occurring throughout the region as well. Density structures and blobs are generated, released, and outflow from here. And in certain areas, we see the subsonic to supersonic solar wind outflow transition as well. So how do all of these things actually relate to what we're going to see with Punch? Here, with this dashed line, I've overlaid the inner field of view of Punch, the UNify field of view, which is going to be around 5.4 solar radii, and it's going to capture just the outer edge of the middle corona. And this is going to extend all the way out to 180 solar radii. And the thing I want you to take away from this, all of the structures we're going to see passing through Punch are going to be in some way influenced by what's happening within the middle corona. So it's important to connect these two regions. So let's focus a little bit more on the flows and the eruptions that are going to be passing through this region and into the Punch field of view. Now, Noah did a fantastic introduction to this in the morning session, so I can whiz through this quite quickly. We generally like to split our solar wind streams into fast and slow solar wind streams, and at solar minimum, it's a little bit easier because we generally have the fast solar wind streams extending from the higher latitudes and the slow solar winds from the lower latitudes in the streamer belt regions. Within the fast solar wind streams, we see velocities exceeding 500 kilometers per second. The flows are less variable, and they generally have these photospheric compositions. The slow solar wind's a little bit more complicated. It's more variable, it's more structured, and we see coronal compositions. And this speaks towards perhaps there being more initiation mechanisms within the lower and middle corona regions. So what are the sources? This is something which, as we learned this morning in the morning session, there's still a lot of discussion about this, but people like Pradeep Cheetah have been working on this, and he kindly allowed me to use this slide he put together for a previous presentation, and it just kind of outlines a selection of potential sources of slow solar wind source regions. And these include interchange reconnection related to streamers and pseudo-streamers, closed loop reconnection, MHD wave turbulence along open fields, and superradial expansion of open fields. And this is something that Pradeep, and I know he's been working extensively with Dan Seaton, who's in the room, to actually look at the persistent emergence of solar wind streams. And what they've been focusing on is the coronal web, and the emergence of slow solar wind sources in the inner and middle coronal regions. And they've been doing this through wide field of view SUVI EUV observations merged with LASCO visible light observations. And what they've been able to do is they've been able to look at the sources lower down and connect them with the flows that we actually see passing through the visible through the LASCO field of view. And this video, yes, plain, excellent, is one such example where if you focus on the bottom box and we see a zoom in at the top, shows an example of plasma jets escaping from the inner edge of the middle corona regions. And what Pradeep found was that these jets emerged within the middle corona regions when pairs of coronal web structures actually interact and reconnect. And what they found was that these processes produced these semi-continuous outflow signatures. Pradeep and co-authors also looked at from the stereo perspective as well, and he provided this rather nice composite movie which is connecting EUVI observations from the stereo perspective with core observations. And I want you to pay attention to these consistent outflows that we see emerging from the inner and middle coronal regions. It also highlights nicely for a little bit later in the talk how we have this kind of gap between our EUV and visible light observations. Also in this movie, you will see eruptions popping out, which leads me on to eruptions and the middle corona. So beyond their impulsive drivers, eruptions are mainly influenced by the background corona and solar wind. And this is more so in the inner and middle corona regions where we have more denser plasmas. And I've taken this rather nice representative plot from Bernatel 2010, which shows a CME that was tracked from close to the sun all the way out through the heliosphere. And what we can take away from this is most of the acceleration is occurring in the middle coronal regions. But it's not just acceleration. It's also in this region where CMEs can become deflected. And it's also where the kinematics and the width of the eruptions are actually set out and dictated. And this will influence what we see passing through the punch field of view. Now, I've chosen this movie on purpose here. And this is like another composite SWAP and LASCO composite movie. And I've chosen this on purpose. It was a special campaign where SWAP, the EUV imager, was offset so that the outer edge of the field of view lined up with the inner edge of the LASCO field of view. And we were able to track this eruption all the way from the solar surface out into the outer corona. But I want you to pay attention. Yes, we can track it, but it's very hard to track individual structures in there. Again, you're moving from one observational regime into another. And we've got to pay attention to this. And this actually speaks towards the next generation of observations where we're going to be overlapping EUV and visible light observations to get density characteristics and thermal characteristics. Not going to spend too much time on this because there's a boring table in the middle of a presentation, but I encourage people to go to the paper which I've linked here, and it's just highlighting plasma parameters that change from the bottom of the middle corona to the top of the middle corona. The second and the third columns show the bottom of the middle corona, the fourth and the fifth, the top. And just to highlight, what we find is we see the density change through this region. We see this drop. We see various temperatures for protons and electrons varying throughout the region. We see the solar wind speed increasing as well. And this impacts our derived parameters as well, our sound speeds and alpha velocities and plasma betas, which we find increase and can decrease. And they change dramatically through this region. And I just highlight this because all of the flows we're going to see in punch and everything that's coming out from the sun are going to pass through this region, and they're going to be influenced by what's happening here. So how are we currently observing the region, and how are we going to observe the region and connect it to what punch is going to be observing? So I've shown this many times now. EUV observations in the center, visible light around the edge, and I've also highlighted the gap. We're doing our best to kind of mitigate this gap, and Dan Seaton has been working on this extensively with the SUVI team. Switch, there we go, where he's been performing these off-point campaigns. And I believe he did this one for NERA last year. This is from 2022. And what we're able to see is through these off-pointed SUVI EUV observations, EV structures extending out to several solar radii. And originally, we didn't actually think we'd see anything out here, but this just highlights that we can. The full-sun imager on Solar Orbiter has been making similar observations. And at various points within their orbit, they've had views of even further out, and they've been able to track eruptions out to 5 or 6 solar radii. And the next generation of observations, of instruments will be continuously observing further out. What about on the visible light side of things? We've got a couple of missions. We currently use LASCO and stereo core coronagraphs, but the next generation are going to be bringing the visible light observations closer to the solar disk. So we've got the VELC coming up, and we've also got Proba 3 aspects, and they're going to be bringing visible light observations down towards one solar radii. They're going to be making polarimetric observations, and more importantly, they're going to be overlapping the visible light and the EUV observations. So these are going to be great for understanding what we're seeing in the middle corona. On the ground, we've also got, obviously, eclipse campaigns set up, especially for next year, but we've also got dedicated suites of instruments like the Cosmo suite, which some of these instruments are operational, some are in preparation, and they're going to be making chronographic observations, including polarimetric observations and unique magnetic diagnostics. We've got Sunset, which is currently in the work, which is this CubeSat, which is going to be making these large field of view observations out to nearly 5.5 solar radii, launched in 2025, I think, so possibly overlapping with Punch, I hope so. And we've got the proposed Echo Imager and Spectrograph, which also could provide unique observations of the middle corona region. I just want to make a special call out to the radio observatories. I don't have time to go into all of the observations they make. I encourage you to go to the review paper. And that's because the radio observatories, they're capable of imaging as well now, but I want to point out that they make unique observations of the underlying plasma properties. We're able to get density and temperature information. And these are really useful for our event studies and understanding what's happening in the middle corona. So, conclusion, middle corona, what and where is it? It's this region of transitions between 1.5 and 6 solar radii. It's important to punch because everything that passes through there is going to pass into the punch field of view. How do we study it? We currently study it with EUV and visible light observations, and the next generation of instruments are only going to improve these observations. I just want to make a special call out to a publication that a whole bunch of people worked on. There's several people in this audience right now. We worked on putting together this definitional paper which defines everything about the middle corona. And you can access it through this rather catchy link, or you can scan this QR code. You can reach out to me directly, or if you want to get involved with the middle corona community, we have a working group. We kind of get together about once per month, but in the summer months is a bit more iffy. But reach out to us, join in, get involved. Thanks for inviting me. Go Punch, and thank you.
Okay, so the last talk is by Tongjiang Wang from Catholic University and Goddard. The talk is titled Reconstruction of 3D Electron Density of the Global Corona by Tomography from Multi-Vantage Observations.
Okay. So how to back to the beginning? Okay, thank you. Thank you. My name is Tongjiang Wang from Catholic University of Maryland, working at the Goddard Center. So I would like to thank my co-author Sheila Jones and Nick Argy. They provide a lot of good idea to help this work. And also thank the meeting organizer to give me the chance to talk about my recent work. So just now, Matt gave a very nice talk to introduce the importance of middle corona. So today I will demonstrate how we can reconstruct the middle corona based on the stereo core 1 and LASCO C2 data. So briefly review the importance that is related to, first we can use this 3D density structure to constrain to understand the 3D magnetic field model and also understand the short and long-term variation of inner corona. and also the solar wind origin that is mentioned a lot. So that also provides important constraint on inner boundary of solar wind models to help improve the space weather prediction. And also that provides the corona background model to understand the origin of shock and radio burst caused by CMEs. So my work mainly today I will show our progress of recent work on reconstruction from multiple voltage PV observation. And in the future, in Connect to Punch, we plan to extend to the LASCO C3, stereo C2, and combined with UNify Punch, UNify field PV observations. So this is different from yesterday Bernie's talk about tomography. That is, my introduce is a traditional tomograph, just like X-ray, CT scan. So from the observation of corona in different directions, we can invert the 3D density. So how it is work? So by discretize the density in given point as a linear combination of density at each grid point in Cartesian or spherical grid. So we can convert this integral problem into the linear problem. So typically, we solve as a minimization problem. That's because this problem is very often is underdetermined. So we have not enough observation. So we need a regularization term to have the solution stable and unique, and also reduce the noise. So here I demonstrate, compare the pioneer work by Richard Friesen and Maxim Kramer. We did some improvement. For example, we want to look at the more fine structures to reduce, to voice the over-smoothing of a high-density structure near the inner corona boundary. So we add a weighting to the regularization term. And here I can show, can you play the movie? So we found that can significantly remove the smoothing and also have a solution quite stable. And this is a comparison with MHD modeling by PSI. We can see the density structure is most concentrated near the neutral line. And the left, what's the, is no pointing? So the left figure shows the average radial density profile. So we can see the white is from tomograph. We can see they're consistent with the model very well. And at the outer boundary, that is because the enhancement because we have a limited field of view. So you can see their direct comparisons. So we will take use of this correspondence between density and magnetic neutral line to constrain the magnetic field model. Here I show we also test zero the regularization to have a minimum smoothing effect. We can see when we add the radial weight, it's the solution is quite stable, and we can recover the main structure. And we found the evolution of dynamic structure is limited the spatial resolution to recover the dense structure. For those structures evolve very quick, then the timing we used to construct the data will smooth out. So this is this example shows from single, I forgot mentioned, from the single spacecraft we need to collect data over 2 weeks. That means what we obtained is a mean structure stable, relatively stable in 2 weeks. But if it extend to, therefore all the structure evolve faster than this time scale will smooth out. This is still from single spacecraft, but we shift the time window 1 week before and after. We can see the structure is involved. That suggests we need to reduce the time window, add more spacecraft. For example, for 3 spacecraft is an optimal separation angle that can reduce to 4 to 5 days to reconstruction. So this is a cross-validation method demonstrate how we can determine the regularization parameter and also the estimate of error for the density reconstruction. This method is frequently used machine learning to train the model. So by randomly sampling 10 to 20% of the data, we use remaining data to reconstruct the solution, then use extracted data to test the model. So when you have a small regularization parameter, you overfit the model, so the error increase. But when you have a larger parameter, that is over smooth the model, so you have also increase the error. Therefore, we can find the best regularization parameters. Then we do multiple fold sampling, we can get the standard deviation. So here I demonstrate reconstruction when the stereo A, B, and LASCO separate about 60 degrees. Therefore, we can reduce observation to 5 days. The left shows sorry. It cannot reverse, right? Oh, okay. So this is demonstrated. We construct the density model in Cartesian and sphere grid. You can see they are consistent very well. The cross-validated the model is stable. Our code is stable. So this is compared the reconstruction from 3 satellites and from the one from the single spacecraft, CO1b. We can see the left show construction from first half and second half across current rotation. You can see when you compare with from 3 spacecraft, you see they're different. So that suggests we can provide more accurate density constructions. And I already mentioned the lack of a fine structure because the smooth out of quick evolute structure. So this should demonstrate how we useful of this density structure. This is the upper one show CESO 2019. Okay, they construct the synoptic PV map and try to use this model to constrain the solar wind model. And we can see with the density structure, we can well get this curved structure to give a better constraints. And also Sheila June developed this backbone metric that is given an evaluation of how we can use the density model to constrain the solar wind model. So the idea is they recognize the peak position of density structure, then calculate the minimum angle between current sheet and density structures. When you have a small angle, that given your larger metric value, suggests the agreement is better. This demonstrates when you include the backside emerging activity, we found the improvement of agreement between solar wind model and density models. Here we demonstrated when applied to the solar maximum case, when the space A and B and the separation from the Earth by 120 degrees. So it's equivalent to 60 degrees, give optimal separation angles. We only need about 4 days to reconstruction. But it is very challenging. It is near solar maximum. We can see, can you play the movie? There's a solar corona structure is very dynamic. There's a lot of CMEs happen during the every day. So we need carefully, can you play this tool to show how dynamic? It involves very quick. So we need to carefully check the data to remove all those. Here I show I construct 4 solar rotations. Okay. So the vertical line shows the sampling data locations. So you can see there's a lot of vertical strips. That is a CME. Fortunately, they only last several hours, most of them. Therefore, we can avoid the CMEs to still construct reasonable, the strong, large structures. LASCO has a limited observation, so in the future, the punch UNify can give more good combination. So here I show the result for polarimeter is 100. So when you give the best regression parameters, you can refine the structure, give more structures. Then we can compare with the thermodynamic steady solution from PSI. They give 2 heating models. They are very similar. So we can compare side by side. We can see the right side is the circle is from WSA model. The PSI and the WSA both based on the synoptic boundary. Therefore, you can see the contour is neutralized. They are very similar. But when we compare with observations, they are clearly different. So therefore, we may generate more models to, this is last one. I suggest this is a WSA based on the adapter GON input. That means they consider flux transport. But due to the uncertainty of super granular motions, they generate 12 realizations. So by compare those different models from the direct from observations, we may constrain and find which is the best one. Therefore, that may help improve the solar wind predictions. So this is my plan. So in the future, we can generate the archive to for those 2012 solar maximum and 2009 minimum situations. And also we can extend to the LASCO C3 and stereo C2, CO2 field view. And in the future, we can combine with punch and codecs. The most of the difficulty is F corner and also cross calibration. Also, but for the last, it's not an issue. But in the future, I mean, if we have more spacecraft, we can reduce to short time. This is a summary. Okay. Thank you.
Yeah, perfect. So now we're going to, speakers, come be panelists, please. Oh, they're up there. Here they are. Where's Don? Okay. Can I take his questions? Okay. Well, we won't take Don's questions then. Pardon? Yeah, okay.
I think that we might be able to answer some of these
Yeah, yeah,
questions because
yeah.
we've got members of the team here,
Right.
so we can do
Yes.
this.
No, we'll leave them up there. We'll just, we won't kick off with those.
Well, I asked the top question, and I kind of know the answer. So.
Okay. Well, we won't go with panelists asking themselves questions just yet. Let's start then with Dave's questions for Elena. Did you want to ask Dave your question? Dave, did you want to ask Elena your question?
Just wondered, in the
It is.
in the Gamera data, can you identify current sheets or structures trailing the Gibson low flux rope?
Yeah, we certainly can. So the reason you did not see current sheet in simulations I showed because that was a Sfermac CME, but we've done many different simulations with different magnetic topologies, and for those topologies which are this tethered Sfermac, as it propagates in a heliosphere, so basically behind the CME you have just radial magnetic field with different polarity, and there is a current sheet there, yes. So it's certainly resolved.
That'd be interesting with punch to see how far out we can see those things.
Yeah.
All right. Let's see. Let's see. Chicho, do you want to ask your question? And I don't know who that's to. Maybe it's to everybody.
Yesterday, we were talking about subalvenic wind and I think Noor pointed out that it's been observed in the latest PSP crossings that behind the CME, like in the trailing region, the solar wind is subalvenic. Do you recover this feature in simulation, like at all, always, sometimes?
It's a really good question. So we do see subalfenic flows in simulations, and there are two things that contribute to this. First is that there is the magnitude of the field in a CME is larger than in the ambient field, so you have higher alphenic speed. And also, as the density, there is a higher density in the CME and then lower density in the background, so you're forming basically a rarefaction region behind the CME. So low density also creates higher alphenic speed, so we are creating subalphenic flows, but that's a problem for us, right? Because our boundary conditions are set assuming that flows are superalphenic. So if we see subalphenic flows at the boundary, we stop that simulation. It's basically, it requires to revisit boundary conditions to allow information not just go out, but also propagate in, yeah.
All right, let's go to Matt. Did you want to ask yourself the question?
No, just pointing out that Punch is going to be making these polarimetric observations and therefore able to make line-of-sight distance and velocity measurements, which hopefully NOAA will be using in the future for their forecasts. So that was it. Yeah.
Craig, would you like to ask Tongjiang your question?
Oh, sure. Your inversions are pretty compelling. That was pretty neat. I wondered if you had thought about incorporating dynamics, or if this is really just you're relying on stationary rotation.
If you can turn on your mic, please.
Okay. So, I mean, as a time-dependent regulation, I think there's someone already did this work. So, but I'm not sure in that case how it can, I mean, for the solar maxima case is very quick. So I'm not sure only based on the regression term it can relax this problem. So most importantly, I see in the future we have a complete mission. We have 5 or 10 spacecraft that can give more real constructions, I think. But I demonstrated even we have 3 in the solar maximum case, we still can get some reasonable structure. Because previous that I never see those papers. Why they have this kind of tools? They didn't try the to the maximum case. That's why I developed my code. I want to test myself. The code is not public for others, right? I planning to answer the question. In future, I haven't finished the paper. I plan to release my code. That is Fortran 1990 is quite quick. Only tens of minutes can finish.
That's perfect, Hong Jung, because that was Marcus's question, which is, will your tomography code be public? And if so, where can he find it?
Yeah, and if I hope when released, the people can, based on this code, to improve it.
Great, perfect. Yes, Sarah.
Yeah, I'm just going to do a quick shout out for Hugh Morgan's 2021 paper, which looks at the slow time variation in a tomographic. So just sort of putting that into the record there.
I mean, Megan's stuff is time dependent a little bit too. I don't know if Megan's here. Yeah, Megan, your stuff is time dependent. Yeah.
As difficult is for this time-dependent reconstruction, how we can validate those solutions. There's no way, because we don't know it is real or not.
Did you want to say something about that?
No, I mean, for those time-dependent tomograph, how we justify.
How do you know that it's
a true solutions?
Oh, how do you know? How can you validate the time dependence? How can you validate the time dependence? You have time dependent. I keep talking. You have time dependent tomography that you do with Whisper. And so Tong Jung says, well, how do you know that the time dependence is accurate?
Well, for our case, we're working with spacecraft moving so fast past these structures that we assume that there's no, that the evolution of these structures is kind of negligible. So that's how we're able to kind of isolate the motion in the images as apparent motion due to the spacecraft's motion alone. Yeah, I think it's just a different problem, right?
Nikki, just say the mic that Hugh uses Parker.
And Hugh also uses Parker, yep. Okay, let's see. Elena, do you have this is from Anonymous. Elena, do you have ideas how we can assimilate punch data into simulations such as Gamera to produce Kalman models rather than simply driving the boundary?
This is an excellent question, and honestly, I've been thinking about it for. I don't have a good answer to this. I can maybe think out loud and say that we could maybe incorporate updates on CME properties as they propagate in the inner heliosphere, and update our simulations using probably ensemble models or something like that. That's the thoughts I have. But that's a good question to open to the audience. And if you have any thoughts, please speak up. I think Bernie had a comment.
I had another question for you, Elena, that actually is Dusan's. We were listening outside, and we were collaborating. Anyway, how do you know that there's not some instability in the Gamera analyses at the interface that might cause the sort of fingers that you see going out? I was wondering.
Yeah, this is a really good question, which requires additional analysis for us to look at. There is a paper by Parisa Mustafavi, I believe it was last year. She looked at the possibility of Kelvin-Helmholtz instability at the stream interaction regions between fast and slow streams. I think her conclusion was that the Kelvin-Helmholtz instability, so in radial shears, the Kelvin-Helmholtz instability is stabilized by the magnetic field. The Kelvin-Helmholtz instability can happen in tangential velocity shears, but we need to run higher resolution simulations to actually see it, which we did now. So we increased resolution by a factor of 2 since then, but we need to do additional analysis. So it's certainly something we will look at. Yeah.
All right, let's see, Matt. Barbara, did you want to ask Matt your question? You want me to read it?
Phil Hess has a similar one. I know when I actually saw the mid-corona and that connectivity, it looked a lot more extreme than most of the models would show. And I think Phil also had something similar, saying how well can you reliably constrain the magnetic field. So do you think the models are getting a lot of that right, or do you think that there has to be something modified? And if so, what do you think the models are lacking?
Well, I think that one thing that the models are lacking is information and boundary conditions, and in particular, I'm going to point to the polar regions. It's all connected, and we're lacking that information. So that's the first thing on the large-scale structures. In terms of how we can reliably constrain the observations, new instrumentation, such as Hanley effect coronagraphs and instruments like that, and what's the name of the new instrument proposed for the Cosmos suites? I think they will possibly be making. Yes.
UComp is operating now as 20 centimeter aperture, and the large chronograph will be a similar instrument, but collect a lot more photons.
Yeah. So these kind of instruments will actually help.
Yeah, and get the Zeeman line of sight field strength.
Exactly. So they will help constrain our models. I think Dan would like to jump in here.
Sorry to make you run all the way across the room. Matt alluded to this already, but one of the things that studies by predictive science with their magnetohydrodynamics on a sphere model have shown is that the middle corona magnetic field in particular is really sensitive to very small regions of polarity at the poles, which we currently cannot measure. And really small changes in the poles completely reshapes the middle corona, and especially all those non-radial things you're talking about. So one thing that would really help would be a mission that could get out of the ecliptic and really observe what's happening in the magnetic field of the poles. So a Solaris or a Firefly or something would be really beneficial. And then, yeah, you pointed out the Hanley effect chronograph. I know folks at HAO have been working on concepts for this. Amir has a white paper that talks about a mission called Complete that would make these kinds of measurements that I would also really help constrain the magnetic field in the middle corona. You can check that out. So you can find it on the archive, I think, right? Yeah, okay.
And then Lauren is having a baby on Tuesday, so that's probably why Dawn has bailed. Maybe, I don't know, sometimes you have to do things to get ready for babies. So that's why he's not here. But Matt or Dan, did you want to take some of Dawn's questions since they're up there?
I think between us we can have a go.
Yeah.
Start at the top. What do we got? Dawn, a quick comment on visual. The HI instrument is considered a key instrument, so why? Whoop, it's gone. Oh. I have no idea. It's gone somewhere.
On Vigil, the high instrument is considered a key instrument. So wide field tools would be needed for that, and they could be adapted to Wi-Fi.
Yeah, I think they're talking about perhaps unifying the tools that we're going to use for perhaps looking at punch data with those that are going to be used with the heliographic image or whatever it's called on Vigil. I did actually have a question for James, who I don't know if he's got any way of responding through. Oh, he's responded? Because I asked him the question whether it can make polarimetric observations. It cannot. Okay, so we're going to be kind of unique on that one. But yeah, so making tools. And I will say with the punch sock, we're building our tools. Ritesh is building a polarization resolver and things like that. We're trying to make the tools as universal as possible. Obviously, they're designed for punch, but we're building them so that they can, with appropriate meta information, ingest other data sets and hopefully be useful to the community.
Okay. Let's see. And why? Well, Matt, you already answered your own question. Let's
a good
see.
one.
And then Craig says, Dawn, you no doubt know, but punch latency can be greatly reduced by simply scheduling more passes should it become necessary? Yes.
It's true, and we're discussing that with NOAA. We'll see what happens, but the latency is entirely driven by passes, and I think the overhead to actually make the data and deliver it once it reaches the ground is negligible.
Yeah.
This is Michael Knölker, ATO. In listening to these presentations, given my longer historical view on how this developed, I'm intrigued by seeing B.C. Lowe's beautiful mathematical solution that is sort of the startup of this simulation. I remember his excitement when he had found this mathematical solution. However, I think what we are still missing is that in the quiet phase of such a structure, we need instrumentation that really can map the magnetic field structure. And that can be done with Cosmo, and then you would have much more foundation of the various propagations that end in chaos, more or less. The other comment I wanted to make is about the tomography, the 3D tomography. That is something that Dick Fisher, in pushing stereo at NASA, wanted to do for a long time, and to now see the first steps of that tomography happening is certainly very exciting. However, you lost me a little bit when you then said, oh, avoid CMEs. We can't avoid CMEs. This is what we are after. I think you need to find constraints in the version that allow you to attack CMEs in some way.
Responses?
Just want to say thank you for the comment about the CME magnetic structure. It's definitely one of the biggest unknowns in our model, especially when we model a particular CME event. We have to make assumptions about magnetic structure and consider different topologies and see which one agrees better with observations. That's the way we're currently doing it.
If I may, see in simulations of MHD processes as they appear in the lower atmosphere of the sun, it was clear for some years that we were at a point where we needed resolution in observations that would really allow to constrain the model calculations that had run away from the observational capabilities. And with EKIST, that part of our community has now this tool. And similarly, these high-flying plans for space observations of coronal processes need high-resolution polarimetric observations from the ground, and therefore Cosmos should have a similar priority.
All right, Vadim, you have a question for Elena.
Yeah, I have a quick question about the velocity profile for a CME in Gamera. We saw another plot from observations earlier today. So how does it compare with what people saw from in-situ observations? Where does it happen, like mostly? At what radial distances?
So for the radial velocity profile, we use Gibson law solution for the velocity, which is self-similar expansion. So that means that inside the CME bubble, velocity decreases linearly from front to the end. So that's the
propagation of the structure as a whole. So are you talking about the velocity, it's like in the reference frame of the CME itself, right?
Inside the CME,
what about
yes.
the CME, like in the lab reference frame? Where is it actually accelerated the most? Near the sun or farther away?
So that the acceleration or deceleration depends on CME speed and on the background. We see deceleration of CMEs quite a lot, and that probably related to the fact that if we start from the fast CME, velocity decreases inside the CME because that's the conditions we use, and then there is slower solar wind carrying it kind of from behind. So we see deceleration of CMEs quite a lot. So we did comparison with in situ data as CME gets to Earth, and for one particular event, and the profile of velocity looked quite similar. The thing to do would be also to maybe plot the profile of CME velocity and compare to white light, what white light is seeing, how the profile looks like.
It's a quick follow-up. So is the erosion of the leading edge of the CME does it have anything to do with the propagation speed? Did you notice any deceleration correlated with the complex structure of the leading edge?
Not yet, because both simulations were done with the same speed. So that would require to run a couple of simulations with different speed. And yeah, there was a previous suggestion from Noor also on doing CMEs with different speeds. That's something that we're planning to do, definitely. Yep.
I have a quick follow-up to Michael's comment, which is, first of all, we were all blown away by these simulations, right, which showed much more detail than we see in typical observations, and that's an inversion of the usual way of things. Gorgeous work, really amazing. It highlights that, Punch is part of a balanced breakfast, right? It's not a standalone mission. We really intend to work as part of the HSO. And the fact that there are projects like Kate that are here, right, where people go to extreme lengths to get just a little more resolution in the corona, implies, yeah, we really do need things like Cosmo. We need things like DKIST to round out the entire suite. So I think it's a really good point you made. That's all.
And is that your question? How soon can we have forward models, Elena?
Right, how soon can we have those?
We need to do some work with the actual files, because this is parallel simulation and you have 500 files as output for different chunks of the simulation. So we need to do some work to prepare the file for a forward model to run on it.
And then Sarah, did you want to ask Tongjiang?
Yeah, this question for Tongjiang, and you partly answered it earlier, I think, but how high up in the corona have you done your tomography, or can you do your tomography? Because of course Punch starts at about 5.5 our sun.
Yeah, so far my tests are all based on the Stereo CO1 and LASCO C2. That is previous I use a Cartesian coordinate code. That is already very well tested. Then recently I developed the the code in the sphere grid, that is towards this large field view, because you need a high grid. So the sphere can, because those structures are expanding. So, and one go to the very high location, the structure become very thin. So they need a very high resolution. Therefore, spherical grid can well catch that. The next step I will test with LASCO C3 and the same field view as NIFI.
And can I ask, will you consider non-parallel lines of sight in the way you do your construction as you get into wider fields?
Yeah, already in my code is already considers this not parallel. Is already consider this elongation angles. Yeah.
Cool. And sorry, one last comment. Sorry, now have it. I just was going to comment that tomography is such an interesting complement to what we're doing with the polarization, trying to 3D locate. And we've heard different kinds of tomography too. I mean, you're doing rotational tomography. Megan is doing the tomography that's enabled by a spacecraft flying through stuff. And then of course, Bernie is doing a kinematic tomography where instead of the rotation, he's using the actual velocity of the solar wind to allow the sampling of multiple lines of sight. So we have all these different approaches. And then in a completely different thing, the polarization localization. So being able to compare these is going to be really powerful when we don't have the ground truth of simulations like GAMRA to test our methods. So I just wanted to make a comment about that.
Great. Let's see. Ritesh, did you want to ask Don a question? Matt and Dan.
So, Don, since you mentioned Punch and UCAR as an alternative for Sun-Earth line in CAT tool, any plans other than Vigil, because Vigil is like about 7 or 8 years down the line and 5 years extra, to launch something similar like stereo when stereo is say 30 or 40 degrees apart or at worst, I don't know.
Some kind of mission, like a complete mission or something like that, maybe?
Small mission that can have a coronagraph launched in stereo orbit or something like that.
I personally don't know of any plans, but Amir, why don't you speak up and tell us about a potential idea to fill this void?
Thanks, Matt. The check's in the mail. So Dan mentioned it earlier. We have a mission that was part of the decadal survey, which would have a Lyman alpha chronograph that is something being developed here at HAO, actually, to do coronography, but also measure the magnetic field, which touches on Phil's question, which is right there. So plans is not something I can say because it depends on the 8 layers of the decadal survey recommendations. But there have been suggestions for it.
I don't want to put anybody on the spot, but I think one of the designers of the CAT tool is in the room and maybe wants to comment on this. Vic?
Oh, Mihir has the other microphone. Mihir, can you walk over and give him the microphone?
There really aren't any alternatives. I mean, we can do the CAT tool. I mean, we can. It exists and it works fine as it is, but it's limited by the observations, which are mainly near the sun. We hope to incorporate observations using HI further on as to sort of a mid-course correction would be what the next thing would actually try to do. But you're very limited. I mean, there will be, NOAA is building some spacecraft coming up, but it's like number of years out yet before they have anything. And so we're pretty limited in observations away from Earth, basically.
Would there be a way of combining some of these line-of-sight polarimetric measurements with plane of sky?
I don't know. I'm kind of skeptical.
Okay.
All right, we have like 1 minute left. Phil, did we answer your question? Okay, so I guess we could take, if there are any last burning questions in the room, or if the panel wants to ask themselves more questions.
So actually, I can help answer the question to the Matt. So as I know, Max Kram working in Hawaii, he developed this, his PhD, since PhD, he's working on the tomography of magnetic field, coronal magnetic field reconstruction, based on Stokes observations. Now he working in Hawaii with DCAST to do this work. There's some paper you can check.
Yeah, yeah, great. All right, then, Vic, did you have a final word?
Yeah, yeah, just stay there, yeah. This is a question regarding the modeling that we saw with gamma and these other models. Remember, you're starting at 25 solar radii and all that. But, and I know you have a problem with, when it comes to intense magnetic clouds, you mentioned that, you can't really do that problem. But you need to remember that the intense magnetic clouds at 1AU exist. They've been measured, seen very, very many times. And their behavior is going to be quite different than weak magnetic clouds, which are very susceptible to getting distorted in the background. And so don't draw too many conclusions, as I'm trying to say. But remember, like the strong ones, the alpha gain speed is so high inside that if you like poke it in, like from the side or something, it will come right back out. I mean, it just distributes any little disturbance like that. So it maintains its shape a lot better than what we see in those plots.
Could you talk a little bit about numbers that you mean? The strong fields, what's the...
Well, at 1AU, you see up to like something like 70 nanotesla. And it's very, and density inside those things is very low. So the alpha gain speed is really high. It can be, like 400 or 500 kilometers a second.
So those would be about 1,000 nanotesla around 0.1 AU, I guess.
Yeah, I mean.
Yeah, so we're yes, the maximum we went is 400 nanotesla CMEs.
Yeah, and there aren't many, I mean, that's part of a spectrum. I mean, most of them are weaker than that. But you do see those that strong at 1AU.
Well, that's certainly motivation for improving boundary conditions and being able to handle those.
All right, we are at 3:31, so I think it's time to call it and say thank you to all of our panelists. And we reconvene at 4.
I don't think this, yes, now it's on. Okay, welcome everybody. As we get started, I just want to bring this back because Heather put it up at the beginning of the last session, but I'm not sure everybody saw it. We want to make sure that everybody here is aware. Session, very connecting punch to every other place's relevant session as well at the AGU. And the abstracts are due, I believe, August the 2nd. In situ observations to build a global view of the corona and solar wind. So please, we invite you to consider that as you submit your AGU abstracts. All right, I'm going to go ahead, and I think we can go ahead and load up the next talk now, Kelvin. Our next speaker is Larry Kepko. And Craig has told me that I don't really need to go hobbling up and down the stage, so I'm going to introduce from here. So Larry's going to talk to us about the ISTP Next and Heliophysics Great Observatories.
All right, thanks. My pleasure to be here. Yeah, so I'll talk about the ISTP Next program in quotes, because it's not a real program, although we can make it real if we want. And the concept of Heliophysics Great Observatories, this has been under development for about 3 years now. Started with the Coast Guard Task Group on establishing an International Geospace Systems Program, or IGSP, which was primarily magnetospheric. And then last year at TESS, actually, it was last year or the year before, whenever TESS was, we realized that there was synergies between solar interheliosphere, ITM, and magnetosphere, and so we joined forces and put in a white paper, unified white paper to the decadal, and then did all this stuff. So let's see, how do I go forward? Oh, okay, I hit something. So this is a very condensed version of a much longer talk that I give, and many of you have probably seen me give this longer talk. It's very useful to think of heliophysics, or solar and space physics, if you will, divided into 4 primary eras. The 5th era is being defined right now, whether you know it or not, it is being defined right now. So we have the discovery era, where every launch was a discovery. You know, you go to a new place, the new instrument, you discover something new. And then once we discovered all these regions, we wanted to discover the dynamics of those regions. So we launched a series of multi-spacecraft missions, ICE, ANTI, Helios, Dynamic Explorer, and so on. And then once we had these localized regions understood, we decided we needed to understand the system, at least at a rough scale. And that led to the ISTP program that I'm going to talk about in more detail in a few minutes. And then having defined the global interactions, we realized there was fundamental physics we were missing. And so we entered the era of the microscales. MMS, Van Allen probes, Parker Solar Probe, missions like that that looked at fundamental plasma physics. And now it's time to pull back out again. Oh, wrong way. There we go. So I want to talk a little bit about the ISTP era in more detail, because in my mind, this is really a golden era of solar terrestrial physics, an era that I grew up in. So my idea of doing science really comes from the ISTP era, which is really quite special. It actually originally started back in 1980 with the OPEN program, the Origin of Plasmas in Near-Earth Neighborhood. That was actually a funded program, and then it was descoped and the awardees were rescinded. Eventually became just wind and polar. It turned into something called the Global Geospace Science Program. And then international contributions turned it into ISTP. So ISS contributed GeoTail, Equator was descoped, Equator S was launched by Germany and unfortunately only lasted a few months. And then SOHO, as you all know, is an extremely important mission. I think Craig likes to say that SOHO really rescued the solar community. The joint ESA-NASA mission that of course is still operating today. Cluster was originally part of ISTP, but of course the launch failure became Cluster 2. And all these other satellites participated in a very coordinated, organized fashion. The core science program was endorsed by something called the Interagency Consultative Group, or IACG. And ISTP really unified the entire worldwide space physics community under this common scientific objective of understanding the transfer of mass, momentum, and energy through the sun through geospace. And it's really that unified science vision that enables us to all come together as a worldwide community. But importantly, ISTP was much more than spacecraft. And being NASA people, we often get focused on spacecraft, but science is way more than just the spacecraft. It had a theory modeling component that was funded directly from ISTP and led to the first global models. Ground-based had a ground-based component. In fact, the first funding for SuperDARN came from NASA. NASA will fund ground observations when needed. And there were international data standards and the spirit of data sharing that continues today. We all know it's CDAL-Web, where we get our data from. That grew out of the ISTP era, the CDF format. ISTP standards. That was all because people realized you need to have open data to do open science. So here's where we are today. We had the ISTP era from about 1990 to 2005. look at the large scale, sort of systems observations, but a very coarse scale because you only had a few data points. And then over the last 20 years, we've looked at the micro scales, the small scales, MMS, Van Allen probes, and so on. And now we're all kind of realizing that we need to couple these two scales, couple the micro to the macro, macro to micro. And they couple through the mesoscales. And you heard in these last 2 days a lot of talk about mesoscales. Because mesoscales are where micro and macro meet, and a lot of interesting things happen within that region. So I'm suggesting that the fifth era should really focus on system of systems, I'll get to in a minute, with a key goal of observing mesoscale resolution and connecting across all three scales. So everything we study is a system of systems. The sun, as you know, is a very classic system of systems, right? And I'll talk about that more in a few minutes. Earth's magnetosphere is another system of systems, and often for practical reasons of really cost and complexity, we study individual regions with single spacecraft, right? Because you can't launch 10 spacecraft at once to study, say, the polar regions, or the tail, the day side, and the inner magnetosphere all at once. You do one at a time. Same thing with solar regions, right? You study this wavelength of this region one at a time. And that's really not a great way to do science, given where we are today. Because today we want to talk about linkages and how these different regions link together. So this is a slide that I think Nikki helped put together for ICP Next. And the real difficulty is connecting these layers of the system of systems can really cross discipline boundaries and observational techniques. So I like the photo on the left here showing a sunspot going up into an active region. At the bottom with sunspots, we actually have microscale observations. We can really observe the photosphere in really microscale resolution. And then as you go up to the chromosphere, I feel silly telling you all about this, but I'm going to talk about it a little bit. As you go up to the chromosphere, it's optically thick. And that is a completely different observational technique and interpretation technique. And how do you link something like that to something below an optically thin photosphere? And then, of course, you get up into the corona, which is very hot, optically thin, observed in the UV and the X-rays. And so if you go from top to bottom, you go from an optically thin, hot corona through an optically thick chromosphere back down to a microscale photosphere. And we're trying to couple all that together. It becomes really difficult because there are different observations, different numerical models, different people, different groups, different techniques. It's not easy to do, which is why it's not done very often. So the current observational approach with the heliophysics, quote, system observatory is simply inadequate for the kind of science that we want to do because it wasn't designed for this. It's really an ad hoc system. And the reason it's ad hoc, as you all know, is because every mission has to do their own science, right? Punch has its own level 1 requirements it has to meet. Doesn't matter what everybody else is doing, Craig has to meet those level 1s or he's a failure, right? The mission fails. Every mission has to do that. And if you try to do extra stuff, you don't get brownie points for that. You're still going to meet your level 1s, right? So if you look at something like this, if you think about the sparse measurements we have, when we talk about trying to coordinate sparse measurements, well, sparse measurements, even if coordinated, are simply inadequate to fully capture the system. So this picture on the left is stereo and SDO from just a few weeks ago. Well, they're coordinated, right? They're on the same grid, but you're missing the backside entirely. You're actually missing the poles as well. So you can coordinate all you want. If you don't have the observations, you don't have the observations. Earth's magnetosphere is a great case of sparse measurements, even if you coordinate, simply don't capture the mesoscales. So here's a simulation of Earth's magnetosphere from the APL group, showing lots of little flows, mesoscale flows. You might think of these as mesoscale things coming from the solar wind. And we might, at best case, have MMS, Themis, and Arase, which is a Japanese mission. And there's no way you can look at that and say we are capturing the mesoscale dynamics. We just simply impossible without multiple observations. So this fifth era that we're entering of cross-scale, cross-system science requires a new approach because the current system was not designed for it. And every 20 years, you just have to learn from your approaches and then refocus yourself. We need a new and very intentional forward-thinking coordination mechanism and a new worldwide effort. And we have to resolve cross-scale coupling simultaneously across the system of systems. And the sun, that's resolving from the photosphere to the chromosphere through the different layers of the corona out into the solar wind, right? You need to monitor the state variables. And we talk a lot about this in the context of NASA doesn't monitor state variables, NASA does science. NOAA monitors the state variables. We've become accustomed to certain measurements that we will always have. L1, for example, EUV imagery. I would love to have some auroral imagery. We haven't had space-based auroral imagery in 15 years or so. It's a real loss. Radiation belt content. You can think of all these state variables that we're used to having that we really need to specify the vital signs of the connectivity. And if we don't have them, it really makes our job more difficult. But unfortunately, there's no program or money in the system to actually give us our state variables. And I'm hoping that Decadal has something to say about that. We need to make advances in the next generation numerical modeling. The models we have today will not be the models we have in 20 years, but you can't do a model on the GI grant or an SR grant, right? You need to have real strong investments on the scale of, say, a mission of opportunity, tens of millions of dollars over several years. And we need to organize the ground and space-based communities around programs and not missions. I'll tell you why in a minute. And we need to embrace and utilize big data, AI, ML techniques, and universal standards. And that stuff doesn't happen by itself. There's lots of people working behind the scenes to make sure this stuff happens, but only if we tell them what we want. Right now, they're designing the systems with perhaps only a little bit of input from us, but we need to give them input. And we globally coordinate, work together to study these systems of systems holistically at the scale size we know are driving the overall dynamics. And really, I'm saying a next generation ISTP type program. So this led to the concept of the great observatories. These great observatories, 3 of them, ITM Great Observatory, Magnetosphere, and then Solar Inner Heliosphere Great Observatories, there's 3 of them, all have this similar structure. You pull in space-based missions, ground-based measurements, simulations of theory, and standing rockets, balloons, and CubeSats, which didn't exist in the original ISTP, and we can be smarter about how we use them. You pull in advanced analysis techniques, which didn't exist also 25 years ago, and then a future research infrastructure that's being designed today into a comprehensive coordinated science that extends beyond the mission that you're focused on. So in terms of the 3 groups, SIH has many assets today with more coming online over the next 3 or 4 years, Punch, Muse, and so on. So they have a strong need we'll talk about in a second. ITM Great Observatory, we're looking at GDC and Dynamic as an opportunity to make that Great Observatory happen, and so we can design it today from the ground up and make it the observatory we want. Magnetosphere is a little weak right now. We can kind of skip them for now. So this is how a typical NASA mission operates. This is how Punch operates. You have your primary mission, GDC and Dynamic in this case, or it could be Punch. And then if you need ground data for, say, CalVal, you pull in a coordinator to get your CalVal data. And if you have a model that you need, you have a model that's part of your mission. And with those, you produce your science that is focused on science from your mission, your level 1 requirements. Well, that's fine, but it ignores everything else that's out there. And so in the ITM world, we have a lot of measurements that are just simply not coordinated. But if you coordinate them all together, you end up with much more science than you are actually if you just did them separately. And you call this, all these resources working together as a great observatory. This is the Solar Inner Heliosphere Great Observatory. I know at the last Punch meeting in January, you came up with the same idea, actually, which is why we're working together now. And actually, Angelos put this slide together with your space-based missions crossing in situ to remote, and then some missing observations, ground-based measurements, simulations theory, and sounding rockets and balloons. Pulling all these together gives you comprehensive coordinated solar inner heliospheric science, which I know is something that Punch wants to do. But we can use the Great Observatory moniker, I guess, to make that happen. So about, I don't know, a month or 2 ago, we had the ISTP Next workshop at Johns Hopkins. NASA was kind enough to provide some funding for this through their grants. And we had sessions based on all these little boxes. We had a simulation and theory box, advanced analysis techniques box, 3 observatories. We had breakouts on ground ASI comparisons, heliophysics branding, like how do we define ourselves, which has been a great big topic of interest, issues affecting the community, and then SIH coordination. We had 202 attendees, 85 in person, 117 remote. Nikki Fox jiggled her schedule a little bit so she can attend in person, because she really grew up in ISTP, understands the value of this. And of course, Peg was there as well. There's Peg. Was there as well, providing her support. The workshop is available. Workshop report is available. It's no longer a draft. It is a real workshop report. It's 30, actually, I think it's 35 pages now. This link will get you there. The QR code will get you there. If you're interested, take a read. That document did go to headquarters, and we are talking back and forth about some of the low-hanging fruit we can do today, that NASA can do today to help implement this, that does not step on the work of the decadal survey, because the decadal survey does not address all of these things that we're talking about here. So I like to say the best way to predict the future is to create it. Don't let others define it for us. One important thing I didn't talk about much here is that we are all heliophysicists. In this room where you actually are heliophysics scientists, it's a little easier. But when I go to the ITM and Magnetosphere, they often feel left out because of the name. So we're working on that. And I think we're making a lot of progress in all becoming heliophysics scientists. If this large-scale coordination like ISTP Next is something that we want, we can make it happen. We do not have to wait for the decadal survey because this is just simply organizing ourselves as a community. We can do it today. Maybe we need some resources. We can go beg headquarters for some resources or NSF or whomever, but we can make it happen today. And in fact, with GDC and Dynamic, we certainly are. And then I think with SIH, things are happening as well. I didn't talk about this in this particular talk, but we need to resist the trance of scarcity. That's the feeling you get when you don't have enough time, you don't have enough money, you don't have enough resources, and because of that, you feel the pressure to not share, to not collaborate, to not coordinate. We've all felt that. Our community as a whole has felt that. And over the next few years, as budgets may tighten, we need to be really cognizant of this trance of scarcity that can really be damaging for our field. And finally, I encourage you all to advocate for our community. Not just your particular mission, your observation, but for the future health and vibrancy of our unified field. I guess it was Spiro who said 20 years ago we unified in name with heliophysics, and it's only now that we're trying to unify in science. And that's what we're trying to do in the next couple of years. It's important to speak with a common community voice, heliophysics. That's who we are, we just have to accept it. System of systems, mesoscales, whatever term we use, we have to use it uniformly. Also speak in solidarity. This internecine warfare, where everybody loses, can have impacts beyond our community. I often hear from our people in ESA that they heard about some meeting in the United States where somebody said something bad about Magnetosphere, ITM, or solar, and it gets to them. And it goes up to ESA, and ESA says, why should we even bother? They can't even get their act together. Stuff matters that we say, and we need to be a team. Because as Nikki has always says, we are all on team science, not team punch, team MS, we're on team science. Thank you.
Is Deepankar. Hello, Deepankar, coming to us from India. Deepankar is going to, in particular, the Aditya mission. Take it away, Deepankar.
Yeah, just to confirm that my screen is visible.
Yes, we're so far seeing the PowerPoint. Yeah, go ahead.
Right.
Perfect.
Thank you very much. Thanks to the chairs first to give me this opportunity to join remotely. Just not the two chairs, but also all the members of the Punch team, the Matt, Dan, Amir, and so on. So I'm going to just give you an update on the Aditya L1 mission and possible coordinated observation from this mission. This is a mission from India, entirely conceptualized and built at different academic and ISRO centers. So this is our first mission of its kind. This is multi-payload observatory class mission and also multi-wavelength, covering different wavelength region, all the way from optical, infrared to X-ray. That will cover different layers. So it's a combination of 4 remote sensing and 3 in-situ observations, because we are also going all the way to Lagrangian 1 point for the first time from Indian platform. So it will have a connection between the source and the in-situ. So the capability to address many scientific problems in solar as well as space research aspect. In this particular talk, I will probably focus a little bit on the main instrument, which is the coronagraph, which is taking the maximum asset in the top tech of this, about 180 kg of a spectrograph. And at the adjacent, you see the near UV imager, which is sitting next to it. All the instruments have been delivered to ISRO, and most of the tests, namely the thermovac and the vibration tests, are all over. I understand that it is all getting integrated in the satellite. We have many science missions now, and particularly the Chandrayaan-3. This is the moon mission from ISRO, which is expected to launch next weekend. So I hope that after the Chandrayaan-3 successful launch, of course, it has its first attempt, rather second attempt to land on the moon. So there are certain, moments ahead of us. And after that, by the end of August, I was told that we are in the queue. As I mentioned, it has a combination of 4 remote sensing and 3 in-situ instruments. We are going to Lagrangian 1 point, so we have a long cruise phase, about a little more than 3 months, and then the insertion phase. Again, I will not be covering all the science major objectives, because when you look at the list of the instruments, you yourself will realize that how much potential is there. So this is the VELC, the coronagraph instrument, which was delivered to ISRO a few months back, and this is the near UV imager, which was built at UCAR, which was also pictured here before it was handed over several months back. So I will just give a very quick update on the detailed instruments. So this is the coronagraph, which has 3 visible and 1 infrared channel. Amongst the 3 visible channel, one is in the continuum, which will look at 1.05 to 3 solar radii, and the infrared channel also has the capability of doing spectropolarimetry. So we'll have a possibility of estimating the magnetic field for the first time in the corona from the space platform. This is the near UV imager, going to work at 200 to 400 nanometer. Again, probably for the first time, a continuous monitoring of spectral irradiance and some of the spectral lines from space platform. We have 2 particle detector working in 100 eV to 20 keV range, and another one called PAPA, which is going to look at the electron and ion distributions, which is going to work at 0.01 to 3 keV. We have 2 X-ray spectrometers. This is going to look at sun as a star. One is going to operate at 1 keV to 30 keV, called SOLEX, primarily for low energy X-ray flares, and the Helios is going to look at the high energy X-ray flares. This is a perfect complement for the student instrument, which is there on the punch. I guess a lot of studies can be done by joint science operations as well. And finally, we have the magnetometer, which has capabilities of measuring up to a few nanotesla. Just to highlight that this coronagraph is again an internally occulted coronagraph, very similar to LASCO C1, but with a traditional internal mirror. And the pixel resolution is something which I like to highlight here, which is much better than the existing ones. And the other thing to be noted here is the aperture size. This is almost a 20 centimeter primary mirror, capable of collecting a lot more photons as compared to the existing other optical coronagraphs. I'm again highlighting, this is the missing area where I think we all agree, which connects the source and the heliosphere. You heard about middle corona, but we are going to focus with this coronagraph instrument primarily into this dark region through this instrument, which has a capability of doing a continuum imaging from 1.05 to 3 solar radii. But in addition, it has the first time a multi-slit experiment from space. It will have 4 slits, and we will be using the red and the green line, and also the 10747 infrared line to do spectroscopy and spectropolarimetry. So that you understand whatever the missing link which we are talking about during the last 2 days almost, in terms of characterizing and diagnosing the plasma parameters of the sources and interconnection between the sun and the heliosphere. I think this is the missing area, and we are going to focus on that. We'll have plenty of opportunity of playing around with the exposures and the cadence and so on. Of course, we are going to Lagrangian 1. We'll have limitations in terms of a telemetry, but with it's a completely a proposal mode driven observatory, so we'll have to have lots of observation. So in that regard, I think it is important to have coordinated observing campaign from different space platform. And in this context, I'm just going to highlight a few on the possibilities with Punch. As you can see here, Punch and Lagrangian 1 location will be a perfect fit. So these are the coordinating science things with NIFI and WIFI, but we are going to be connecting the internal portion, 1.05 to 3 solar radii, just a little portion inside, but I think the physics all originates from there, and that will provide you a very, very good platform. Again, highlighting the importance of that inner corona connecting with the heliosphere. So I think it has huge potential. Again, I have borrowed these slides from Dan. In fact, Ritesh has prepared a few slides for me to make this connection more visible as well. So you see all these things are happening very close to the sun, and with a combination of SUVI and SUIT, that's one area we can focus. And then SUVI and VELC covers all these regions where the initial acceleration and the motions are happening. Of course, I should mention also about Proba 3. In fact, Aspects has exactly the same field of view, but of course, Aspects will have a small duty cycle. So I think combination of Aspects and VLC can really make a big difference in coordinated observing campaign. So this is, again, connecting the source to the heliosphere, highlighting in this slide the real small portion, but tracking the flows, the transients all the way is the key for our better understanding. I will also point out a few conjunction possibilities. This again, Ritesh has kindly produced this perfect conjunction possibilities. These are the two options which we see with the solar orbiter, which is crossing the Sun-Earth line. We can already start planning and note down how it can really complement, as you see, the field of view of VLC, which is going much closer to the sun as compared to METIS at that point. And then the SOOT and FSI and SUVI will even give the disk information. So this is really great opportunities coming up for the next generation. Coordinated again, future conjunction, September 2025. This would be ideal if just after Punch's launch, and multi-wavelength study of flows and transients from inner corona to all the way to heliosphere with possible connection with remote sensing and in situ observation. Another opportunity of conjunction, Solar Orbiter, October 25. And again, I think we should start planning from this so that we can, really be well prepared. I would also like to highlight that, again, there could be huge coordinated observation with PSP as well. Here you see a good example of that, the telescope 1, as it is indicated here, has a very good overlap with our field of view here. And that way, the coordinate observation will really get significant new avenues. Some possible outcome, enhanced understanding of kinematics of large transients from inner corona to the heliosphere, as I indicated. Then the possibility of how the anti-sunward moving structure is really accelerating and exactly where it is accelerating. I think last 1.5 days, we have been talking about many more motions which are now detected with PSP as well in the heliosphere. But then, following these clumps and their sources are so very important. And the coronagraph with the spectroscopic capability will really make a big difference. This influence what we will be talking about. And as I indicated, that spectroscopy allows you to do a proper thermodynamical studies of the transients and the solar wind flows. Just the imager alone will not provide you the complete insight. So combination of imaging and in situ of transient as well as background can help constrain the space weather forecasting models as well. Improving the understanding of the coupling of the substructure, as we have been seeing for last 1.5 days, that with the better instrument, with the better spatial and temporal resolutions, we are able to get much better substructures. You have seen how much discussions we were talking about the CME core and then this multi-thread structures and so on. So if we are able to get a spectroscopic measurements on those multi-thermal finer structures, I think it will really open up a new avenue. So origin and evolution of the small ones against the large ones is only possible when we have different scales of observation possible within our limitations. So what we're doing otherwise, as you know, India is a very growing country with a lot of youngsters. So we built this support cell at Aries, where I am now, and we are conducting several workshops. These are the young people in the master's program at different universities. So I'm going around and making, very regular lectures. You can see here's another part of the coastal India. And finally, we get one Ritesh out of these several workshops. And I think, our aim is now to make several Riteshes through these campaigns. So this is a recent workshop which happened in Varanasi. Probably some of you are aware of Dr. Srivastava, who is leading that group as well.
3 minutes, Dipankar, 3 minutes.
I'm almost there. So this is the third workshop we had, very recently. So again, thank you for this opportunity, and I'm looking forward to, really participate in joint observations from most of the space platforms and really comparable instruments and which can really combine to get a better understanding of the heliophysics and the solar physics connection. This is a picture taken from the observatory, which I am now leading from India. So all of you are most welcome to come, and maybe, we can have the next Punch science meeting in one of the locations so that you can enjoy the Himalayas. Thank you very much for your attention.
Thank you so much. Thank you, Deepankar, and definitely stick around because we're going to have a panel discussion in just a few minutes. But now let's go on, and we're going to have Barbara Thompson, who is going to be talking about Punch Open Science.
Hi, everyone. Thanks for sticking around. Team, and I'm also on the NASA Open Science team. So I want to do a brief introduction to what Punch's open science journey and why we would want to undertake it before I go into some of the more detailed principles of what open science is. Having an open science plan and acting on it allows you to achieve a lot of very important goals. You can create a welcoming, open, and collaborative atmosphere. You can advance your mission science through open collaboration. You can improve your data products and software. You build public trust, and through open sharing of work and community engagement. And I want to praise the flow tracking team for already doing this. Also, open science guards against negative influences through registries, citable results, and collaboration and conduct rules. And as the world gets more and more small and also more interactive, it's important that we safeguard against some even either intentional or unintentional misinterpretations or misleading things about the science. And finally, this is everyone here, I think, is committed to telling the story of the Punch mission to the wider community and the public. So what is open science? 2023 was declared to be a year of open science, and many organizations and federal agencies have adopted federal open science initiatives. The Year of Open Science has 4 goals: establish strategic approaches for advancing open science, promote equitable participation in open science through transparency, integrity, and equity of reviews, account for open science activities in evaluations and incentives to reward people who do promote open science and open sharing, and finally, engaging underrepresented communities in the advancements of open science and research, so in the long term, our science gets even better and better. NASA's Open Science program is a 5-year program, and it's called TOPS, Transform to Open Science. And I've said open science many times. Let's go into what that really means. There are 3 general areas that people tend to class open science in, and it has to do with accessibility, reproducibility, and inclusiveness. Open science is the principle and practice of making research products and processes available to all, while respecting diverse cultures, maintaining security and privacy, fostering collaborations, reproducibility, and equity. So I think I covered this a little bit in the in our Open Punch journey, but this is part of the principles of open science. As science gets better, we get more efficient, we get more robust and valid, and if that's not enough for you, we don't have a choice. They mandate it. So, those 3 general areas really have to do with improving the access to our data and software and tools. Through that, the reproducibility, the ability to validate and verify results and have other and have the community have access to that means that we have more reliable results, we have better science. And finally, inclusiveness, again, it just means that we have excellent scientists, we get a broader community of excellent scientists, and other viewpoints that will help us become even better. So NASA, the TOPS initiative, recommends that individuals complete 5 training modules. There's one that's ready, and over the next year or so, and again, TOPS is a 5-year project, there will be 5 areas where people can obtain and get badges for these open science principles. The first one is just the ethos of open science, and you just got a 3-slide tour of that, so good job, people. The next one is open tools and resources. There's open data, open software, and open results. There are, of course, other aspects about it. These focus on the deliverables of science and the way we do science. There are not anything right now available for the inclusiveness and equity, but I think that's a value that NASA it really tries to incorporate overall, and I hope that will continue to make progress and show commitment to that as well. So that's for individuals, but what does it mean for team organization to become to become fully compliant with open science? TOPS has 3 supplemental open science guides for their individuals, teams, and organizations. But so far, there are no guidelines specific to an open mission, and I cannot think of a better organization or mission to become the first one than Punch. How does a mission incorporate open science principles? Well, it starts with making it possible through infrastructure, tools, and processes. I can say that for those of us who've been with Punch on the beginning, the PI and the project scientist have very much wanted to see Punch become a community mission and make that possible. The next one is making it easy. I think you've seen from the SOC team and also some of the science teams, we're not launching for a while, but we're already trying very much to get the way we do Punch science to be something that is integrated and compatible with the way we do science in other areas. Finally, it's to bring it to the mainstream. You want to keep on building on that. You want to reward and reinforce the progress that people are making in adopting open science, and then finally you make it required. Those are the 4 stages of adoption. I think I think this team really has rewarded a lot of the team members who have been committed to it, and so to making Punch open and accessible to a broad community. And so the next one is just requiring it, and hopefully won't have to because you guys all want to do it anyways. Here are some guidelines. We have an open source expert and a team. Rebecca Ringett was the one who really went through with me and helped to audit and understand missions in development and what it would mean to do open science. And so this is long, but this is for conversation's sake. I am presenting these aspects. I'm not going to go through them, but I'm doing this because I want you guys to know that we have these, and I want this to become the basis that we follow up on as a team. And finally, so we go through, I guess I should say, so you start with engage, tell us why it's good, start trying it, and then really bring it home by rewarding the people who make this possible. By taking those extra steps to embrace open science and make things accessible, it's well known that it's harder, it takes more time, and it doesn't always feed back and really benefit the people who do it directly. We can make that happen by recognizing that and rewarding them and really rewarding them for that essential thing that they do for this mission. All right. So in this, it wasn't really an audit, but they went through pretty well, looked at the way we did our science. And so these are the kudos for Punch, based on Rebecca Ringett and the other NASA's open science leaders. No special access for COIs. Data and tools are publicly available as soon as possible. And that's good for the community. It's also, nothing improves a data system that's not working well than nobody can gripe like COIs, right? And so if we have to use the same lousy system as the public, that system improves very rapidly. And so that's a good way to do it. The punch sock and data pipeline, the punch bowl, punch pipe, that has always been planned as open source. That is always something, and also the fact that it's not just open source, but there's the possibility of, the engagement of the community to help to facilitate the production of data products to be incorporated and supported by Punch. Also, there are efforts to prioritize compatibility with user infrastructure. So you don't have to just do something completely different with Punch. We want as much as possible to just say, here's another instrument, here's all the stuff I use. Let's, make it bring it to the user as much as possible. Another kudo for Punch, the website is one of the best in development mission websites that people say they've seen, They usually focus on mission. Punch has put a lot of effort into providing information that's accessible and relevant to the public, and not just taking, not just filling things up so that somebody has something to click on. Another wonderful thing about Punch, the very aggressive and innovative public outreach program, which is looking to really do something more than just reinforce the status quo. They are trying to, they are providing resources and making it possible to do something really significant. Finally, important things for Punch, pre-launch major scientific community engagement activities. The Flow Tracking Initiative has, I'm just so happy to see so many people here who've joined the Punch team because they were interested in flow tracking. That is very exciting. There are team members. It's not, the synthetic data is not just to test your analysis tools and test the way you would use Punch data. This synthetic data and model data is helping us to also start to address Punch science and develop tools for analysis and advanced testing of methods before the launch. And finally, this meeting is a good example. Our special sessions and things, those are very good for Punch. All right, I think you guys know what's coming next, right? I'll call them recommendations. Anyway, so that's not bad. To be a really leader in mission open science, we should have a clear open science statement and an action plan. Us co-Is, the team members, top certification is not difficult, even if you do not plan to, for example, share software or use a Knowledge Commons licensing or something like that. It's still good for you to understand the principles behind them and understand how our team members are making aspects of what they do compatible with open science. It's not very hard. I would like to be able to say that all of our co-Is have done this. Another recommendation for Punch, the website is good, but it can be improved. For one example, it's not so clear which things are for the team and where we can say, come on in. Let's, you can join in on this. Currently the Get Involved section has nothing about getting involved in it. Shame on you. But this meeting, for example, could be in the Get Involved section and things. Thank you. We need, this is in production, so I couldn't say, but more clear, by having clear data use guidelines and contact information, it really says that we intend for you to use our data. We intend for the users, people not on the team, to be the majority of the people accessing the data. And that is what we're ready for. So Raphael Atier is, and we've been working on a flow tracking page for the public, for people who want to participate and understand what we're doing to make that possible and be a model of saying, this is what is public, this is what is open, come help us. And finally, there's a couple terms that aren't defined very well. Another recommendation for Punch, we talked about this a little bit with the SOC, but the SOC is going to answer more and more questions from the public, and rather than answering them in terms of in the form of just an email or one by one, it's good for everyone if there's information on Punch for users to understand it better, for it to be an openly accessible resource that also has archivable information and retrievable information. Helionauts is an excellent example. If you're not on Helionauts, please talk to me or Raphael. It's wonderful. It costs nothing, and it's very beneficial. GitHub is also a commonplace GitHub discussion where, again, if one person knows it, you can share it with others. There are ways that we can expand, in addition to just providing open source code and tools, to make it make them more understandable and peer reviewed to make sure that they're robust. The resources can be more interactive so that you can learn by doing. And finally, have some team members and some methods to interact with the community and make so that we can keep our open science at the forefront. But moving forward, congratulations. This has been a tremendous source of just pride and happiness for me to be part of this. Punch was designed from the beginning to be a model open science mission, even before we knew that there was going to be a year of open science. And team members have adapted to community requests. They've created collaboration opportunities to allow Punch to far exceed the baseline scientific goals. So let's build on this, make it official, and make Punch a model for other missions. And I really want to thank the members of the broader community, because without your participation, without your making requests of us and having us have to engage you and also helping us do this, we could not have done this without you.
Thank you so much, Barbara. And our final talk, closing us out, we have Peg Luce, who's going to be talking about NASA heliophysics connections.
Thank you. And I'm from headquarters, and I really am here to help. I asked me to come and join you for this meeting, and I have a feeling it was as much as anything to show you off, which has been successful. I have really, really been impressed in these 2 days, and just want to congratulate you all. I'm going to make a few comments, but I think mission accomplished, Craig. So I'm going to start with just a couple of things. So as you know, Nikki Fox is now our AA. I'm the acting division director. Nikki Rail is the associate director for flight, and Teresa Moretto Jorgensen has joined us recently as the acting deputy division director. We are a great team. We are looking forward to having a fabulous new division director be selected. The ad closed last week. So that process always, as you know, takes a little while, but I'm looking forward to continuing with this great team and the rest of our folks moving forward while we're in this transition time. We have some new folks, and I just want to quickly mention the newest members of our team: Janine Fisher, Kelly Korek, Janet Kazira, and Rainer Friedel, all scientists. Elizabeth Esther is one of 3 new program execs that we've selected, and we're actually in the midst right now of hiring additional program scientists. We've really been in need at headquarters of putting more arms and legs in place so we can do the work that supports what you all want to do. I want to mention Lika is here. She's your program scientist, and David Cheney has been on the line. I think he's the program exec. Lika also is the domain lead for the inner heliosphere, and that's something that Nikki Fox decided to sort of create that organizational construct. We have program execs who all have a lot of, have their individual responsibilities, but Nikki thought it would be useful to have a program scientist who was looking at the connections along the lines of what you're talking about. And so Lika is also the domain lead for the solar and inner heliosphere. John McCormick is the ITM domain lead. Rainer is the magnetosphere domain lead, and Susanna Finn is the outer heliosphere domain lead. This is our fleet, and it has, in orange, are all the missions that are in implementation, which is a good number, and that's something we've been very busy with in the recent years, is following the decadal survey recommendation to increase the cadence of our competitively selected opportunities for missions, and Punch being one of those. I thought about trying to show connections on here to Punch, but I think there are so many, it's not worth it. This is for you all to create. And I think Heather's presentation about the missions that you are looking at to connect with as you do your work was something I really resonated with. I know Nikki and Heather have been working on that. So I wanted to just mention that coming up, we have 10 launches in the next couple of years, starting with in November of this year. And as you can see, while we're in the Helio big year right now, we're also going to have a really big year in 2025 with lots of launches. But these are the new missions that, again, are representing the growth of the fleet that we have, our Heliophysics System Observatory. So I wanted to just compliment you for being from the very beginning, as you've been talking about, an open and inclusive mission in so many ways. The open data and open science, I think that Punch is really poised to be a leader and a shining example of open science and open data. I loved hearing from the SOC, all the work that you're doing that will knit this all together, and the fact that you are already talking about developing tools and making them available to others for various other uses. So I feel like Punch is all about connections. You know, we're here to talk about connections in this last session, and I think that's comes through in a great way. You're going to look to advanced space weather. So all the aspects of what we want to do are represented here. And my bottom line is you're inviting discussion of the importance of Punch in the larger context. How Punch science fits in the overall quest of heliophysics, how to best take full advantage of Punch in the spirit of the great observatories, as Larry so well described. And I want to acknowledge that these questions go way beyond the responsibility of a SMEX team. This is something that the whole community needs to get around. We need to think about how to organize, how to facilitate that type of big picture accomplishment that we really want to move into in the next era. So I give you all credit for inviting the discussion of what is good for everyone how to work together, and for how headquarters can help. So I invite you really to identify and share your concerns. There are going to be roadblocks. There are going to be things that need to be done to cross the boundaries of all the types of science and capabilities and organization and tools and things that you need to do your work. And I think we've been so busy with working on getting these missions selected, but now we are looking forward to the decadal survey. The decadal survey, the last one, recommended the drive centers, the drive science centers, another type of construct to enable team science and bigger picture science. There's still time to make recommendations. Are there more things that we would really like to hear from the decadal survey when we get the report next year? And I thought I wanted to say, finally, the commitment to meaningful outreach that has been apparent from the beginning of this team is just been so wonderful to experience while I've been here. Punch is really poised to be such a key contributor to the Helio Big Year, with our 2 eclipses coming, Parker reaching its closest approach, the solar cycle ramping up. So thank you for the contributions that you are making to that. as you know, we look forward to being there and here are ways that you can get in touch with us. So that's it for now until I want to hear from you. I want to hear what you think we can do now or in the future. Thank you.
Very much, Peg. That was terrific. For closing us out, we are going to, if you don't mind, Peg, we'd like you back up for a panel discussion. Okay. If people who spoke could come up for a panel discussion, we'll take questions as in the other sessions. Have a brief discussion to close out the day. So I think this is where I have to stand up and start running. Thank you. Let's see, we'll go to the Slido. Punker on? Not quite yet.
There's only one question in Slido, and it's yours, Craig.
Oh, excellent. Well, there's a comment from Barbara. Come join us at Helionauts. Dipankar, I had a question, which is, will Aditya be accepting observing proposals? And I think you answered it, but maybe you'd like to answer it here.
Sure. So as I indicated, this is our first mission. So after the insertion, of course, one by one instruments will be turned on, and we have a verification phase. So those would be again another 3 to 5 months. These are the sort of a little flexible at this point of time, depending on the how it goes. And then we have a guaranteed time phase for the individual payloads. So that again depends on individual payload team, how they have project, maximum 1 year after the launch, that some of these observing campaigns are sort of on a test mode. Having said that, if there is special conjunctions and special observing opportunities with other particular missions, I think we'll be really encouraging such proposals from the international community. And as now you hear that from even our space organization and our recent visit of the Prime Minister to US, I think this openness is very much visible. And if it comes through a very consolidated way, if the community wants, this is possible at any phase. But beyond this GT phase, which is about a year from the launch, it will be opened up for proposal submission system within the country, and probably 6 months down the line, it will be open for international community. Since you asked the question, I would also like to take a parallel for the AstroSat mission. AstroSat is our first, observatory class astronomy mission, which is now running in its 7th year. And AstroSat does take proposals from international community as well.
Excellent, thank you. We have a question from Dan Seaton.
So there's a question for the whole panel. We talked a lot about the need to build these connections and to find ways to link analysis. We talked about it in the context of Punch itself and ISTP Next. And I think it was Larry who pointed out that it's not a mission's primary mandate to do this. So I just want to ask all of you, and I particularly with Dipankar here, it's even harder to do this internationally. It's hard to get money to do it. It's hard to make those connections. I want to ask all of you, how can we facilitate this kind of connection science, this kind of joint analysis? How can we do it better? How can we develop new frameworks in which to make this happen?
Barbara.
Yeah, should I go ahead first?
Go ahead, Dipankar. Then Barbara.
Yeah. Okay. So essentially what I understand from our government standpoint, that the scientific community has to drive some of these. But having said that, there has to be opportunities or sort of forums where we could do this. There are, already, there are bilateral programs where, scientists and the students are able to exchange visits and then have coordinated, science proposals. So that's a starting point, I would say. So beyond that, I think the space agencies have already started talking, particularly ISRO have been hearing, they're very open. They have joint joint mission plan for JAXA. I hear even the the Solar C is probably going to be launched by Indian satellite. So I think this is very much possible. So if if the scientific community brings up initial proposal to the space agencies, it is doable now. I mean, it was much closer or difficult earlier, but I think time has come to bring it to the space agencies. They are pretty much interested to do this now. I must also point out that ISRO has, in recent years, have probably got this credibility because we are still have to catch up with the international standards in terms of success rate and so on. In terms of space launch and mission operations, ISRO has got this credibility. But as a scientific instrument builder, I think we are far behind. So we have to still learn a lot of way to still go. So I must point that out as well.
Thank you. Then we have Barbara, and then I think Larry.
Yeah, so that that little that graphic I showed, I give it more thought based on the missions that I've seen, the things that have been successful, and there really is a lot of truth in just you make it possible, and then once you've seen what's possible, then you work to make it easy. And then you work to encourage it and facilitate it. And it's the early adoption, you get it moving, and then you build on it, and then you support it. And I think, and I look at this because I think some of the most famous images that you'll see on the stereo mission have been processed by people who are not co-investigators. There are many people on this team who know that we hope that will be Punch's story as well.
It's a multi-layered problem, as you might imagine. And we've been discussing this for the last several years in the Coast Guard task group. That was really the goal of that task group, was to identify some of the international obstacles to coordination and collaboration. The first thing we have to do is define the science. It's science-driven. And so we did that for the Decadal Survey white papers. If you go in and look at those white papers, on the magnetosphere side and the solar inner heliosphere in particular, it is all about systems of systems, about coupling cross scales. And ITM to some extent, although it's a little more diffuse. And so from the science perspective, you get that in, the Decadal Survey hopefully endorses that scientific vision, and then we can go off. Then the question is, how do we do the kind of science we want to do, where we have a bunch of missions up at the same time, coordinating, sharing, software. That's where it becomes more difficult. If you look to the past, it was a little easier in a way because IECG existed. And IECG had basically the associate administrators for the different agencies were there making decisions without regard to the scientific community. So we don't want to go back to that, right? So now we're guided in the US by decadal surveys, and decadal surveys dictate the direction. But those decadal surveys are not aligned with what ESA is doing, what JAXA is doing, what ISRO is doing. They're totally independent efforts. And that is very problematic, right? So we've been trying to informally align our science schedules with ESA, with JAXA, and ISRO. And I like to tell the story about JAXA, that they had a mission called, I forget what it's called now, Factors. That was an ITM mission, 2 spacecraft ITM mission, that no one in the US knew about. People at headquarters didn't really know about it. They would email me and say, Larry, do you have any information on Factors? And again, that's just not ideal, right? You shouldn't go through a couple of random scientists. So I think we have a lot of obstacles. I think first we have to get the decadal survey to endorse the science. And then it's all about the connections. You've got to build the trust between the agencies. There has been, for various reasons, some distrust between the agencies at various levels because of commitments and things like that that are falling apart. And we have to build that trust again. That's being done at my low level, but people like Peg and up at that level are also working. But I'll say one thing, maybe Peg can address this a little bit. Right now, the agencies work through something called bilaterals, where one agency talks to one agency. And then one agency will go talk to another agency. And that's not really efficient. It's hard to coordinate things. But I know that bothers headquarters as well. I don't know if Peg wanted to say anything about that sort of international coordination.
So actually, I was going to talk about the other tricky part here, which is the funding. So, and the international coordination, you're right. I don't have the answer for that. It is something that we, though, are in a position to try and work on. So that's one of the obstacles I was thinking about. But the funding is the key, and how we do things competitively. I think probably the competitive opportunities that we currently have don't have a framework that is going to facilitate the type of vision that you all are putting forth. And that's kind of been crystallized for me. That's been on my mind, but I understand it even more after being here. And so what the answer is, you know, whenever a division changes their RNA program, various people feel they're going to be winners and losers, and some people don't like change, but I have a feeling that that's sort of one of the things that might be in a good thing for us to think about. One, you know, do we ask an advisory committee to sort of help envision something? So I understand. All I'm saying is yes, I understand, but I understand better than I did before even, so thank you.
Thanks for that. Oh, Lika, please. Oh, here comes the mic.
I think that was I think it's a setup question that you asked, Dan. It's really at the heart of everything we do. And I kind of actually want to bring up, it's not really history. If something is only, 5-6 years not having happened is not history. But the system science concept in the Sun-Earth Connection Division happened with the creation of Living with a Star program. And it's a program, of course, but still the entire program was created with the goal of relevance to life and society. Cutting edge science that is also relevant to society, and which essentially at NASA birthed space weather. And if you look at our mission sequences, they are all in the various domains that Larry showed for ISTP. So Living with a Star already set that up with the science goal also. The Targeted Research and Technology program actually created focused topic that wasn't just for any domain. They were connected questions that people have to answer with teams. So there's some, is it working absolutely fabulously? I don't know, you are the judge of that, but there are kind of setup of that. And going into the international part, actually what, Larry mentioned IACG. IACG got disbanded in 2002. And out of the ashes of IACG was born International Living with a Star, because it was that system framework. And this community at the time when it started, had 27 space agencies. They worked together very closely, created missions like Solar Orbiter, which wouldn't have happened without ILWS. Some of the missions in China happened because of ILWS. The Korean space program came alive because of ILWS. So there are frameworks, it's not in the name whether we call it ISTP or ILWS, but there are framework and material available for us to kind of really review and figure out what are the next best steps to take. And as Peg mentioned, funding is always going to be an issue, and our competitive science approach for RNA program is very tough. That is a place where we have never kind of combined resources with the international community, but as we can see, they all participate. Thank you.
All right, I'm going to take chair's privilege here and change the topic, unless, you got a follow-up? Okay, which Sarah asked. I'm going to make a comment first, which is thank you, both Peg and Barbara, for recognizing what we're about here, right? With we're really trying to be as open as possible. And Barbara, I will take those recommendations very seriously, so I appreciate it. And with that, I'll hand it back to Sarah.
And which one are you asking?
Sarah asked all the questions.
All right. Okay. So Barbara, what do you think would be the next steps forward in following recommendations for even better open?
I have steps. Rebecca did a lot of work in taking the teams and organizations and individual recommendations and extracting the ones that she thought would be relevant for the missions and working with other open science experts. And so I will be asking the Punch team to review the stuff that I skipped over, see if they concur with it, comment on it. Then we will go back to the open science team and say, you know, this is now our plan for a mission. These are the recommendations. We agree on this. We might have things to add. We'll come back to that so that we can help other missions do this. And we will also turn inward and act on the recommendations and come up with a plan of our own. But I have confidence in doing that because I know few people more committed to that than Craig and Sarah.
All right, Sarah has another one.
All right, well, okay, just any of them? All right, I'll do Larry, and I have a drill done on that at the next level. Do you have any reflections on how best to pull together our team heliophysics? And I say, and I actually mean it quite seriously, should we have a full community interpreting dance session? Because I think that was actually super fun. But also I had one level down in this question, in the reply. What I'm really asking you is, you had this meeting. What resonates across the subdisciplines?
Right, so the ISTP next meeting, I thought really good about it, how it went. It was, you know, at 80 people in the room, I'm gonna say at least half were mid-career scientists, right? Those are the people that we're doing this for, early in mid-career, right? Because whatever we establish now will be 10 to 15 years from now, I'll be retired, it won't be me, it'll be the mid-career people. And having them there was really nice, because I don't think the early mid-career really give a lot of thought to how things are done because they're so busy doing their science, getting their postdocs, publishing their papers, trying to get a permanent job. And, but we need them. We really need the future. They need to be there. And so having them at ISTP Next was really, really great to see. That meeting was something like we haven't had before, really, where we had all, you know, ITM, MAG, and SIH together in the same room, not breaking out, but listening to each other. And the scene setters in particular, I was really proud of because they talked about, they use similar language. They use system of systems, they use mesoscales, and I think by doing that, people started to see the connections. And then we pulled together the software techniques. Especially nowadays, we're all switching over to Python, apparently, that I'll have to learn. We're all going to start using the same tools. And having us all in the same room, talking about the same problems, was really helpful as well. And there's really no venue where that ever happens. You know, TESS is a meeting we're all supposed to be at. You should all go to TESS, but we don't. And I know certain communities do not go to TESS. So that's not going to be the answer. You need to have very explicit meetings where we're all together, speaking the same language, talking about the same commonalities. We had this great session on simulations. We're all seeing the same problems. How do you go from kinetic to fluid? How do you make that connection? We all have that same problem. Well, we shouldn't all just work in isolation. So I think having meetings like that, where we're all forced together to have working group meetings as opposed to breakouts, where we're all in our same little groups, is really a major step forward.
I'm going to jump in on that. TESS was conceived as exactly that meeting.
It was supposed to be, yeah.
So what could be done differently to make TESS more?
Well, Nikki and I talk a lot about this because she's SPD chair, vice chair right now.
TESS is Craig's responsibility.
Oh, it's Craig, right now it is. So yeah, as you're probably aware, AGU is Space Physics and Astronomy, so SH, MAG, and ITM. And then Solar Physics Division is a solar community. And there's a hardcore group of solar people who will never come to anything that has us MAG people there, right? Because they're astronomers or something like that. And but TESS brings together SPD and AGU, as you're aware, right? And we're all supposed to come to that. Here's the issue, Nikki and I have talked about, is it is currently an SPD meeting with MAG and ITM invited in to your sessions, which is fine, except at the same time, MAG and ITM have CDAR and GEM. And so if people are going to pick a summer meeting to go to, they're going to go to CDAR and GEM and ignore TESS. And so my recommendation
has SHINE.
Is to cancel for the year you have TESS, SHINE, CDAR, and GEM.
They'll never go for that.
I'm just saying, if you really want people to come to TESS, make TESS, SHINE, CDAR, GEM.
Maybe we make SHINE, CDAR, and GEM the TESS meeting.
Yeah, that's what I just said. Yep, exactly. That's the only way you'll get the MAG and ITM people there, I think. We got a ruthless hand.
All right, we have time for a couple more questions if anyone wants to throw anything out.
So in that construct, where does outer heliosphere go?
Ah.
I kind of worry about this system, right?
Yeah.
And we are still sort of stovepiping because, you know, we are creating this new expanse of our science, and outer heliosphere is doing interesting stuff, right? And it is, where do we put that? So what I found at AGU is that the heliospheric people didn't participate as much. They have their own meetings. I don't know, cosmic ray physics or high energy astrophysics or something. So we have to keep that in mind.
Yeah, so they were not excluded, I will say. They did not come, and they didn't ask to come, and they didn't say anything at all about it. So at the moment, I know they've got IMAP, they're focused on IMAP, and they've got the Drive Center, and they're focused on that, and that keeps them pretty busy. They're welcome to be part of the system of systems because when you zoom out, the part of the heliospheric system, right? But at the moment, it's just not, they don't have the driving need that we have. SIH has an immediate need. ITM with dynamic and GDC has an immediate need. But it seems like the outer heliosphere does not have that same urgency that we have. So they're not excluded intentionally, but we are well aware that they're there.
Turning direction a little bit, Deepankar. So you gave us a great overview. Can you give us a little more information about like the complementary nature of the observables that you're doing in VELSI or the other Aditya instruments?
Okay, so for the coronagraph, we have 4 channels. So the continuum channel is going to work from 1.05 to 3 solar radii. But that has also a detector of 2K by 2.5K size. With a sort of spatial resolution about 2.5 arcsecond per pixel. Whereas the spectral channels, we have this 5303 and 7892. This is the traditional 2 lines which have been observed most of the time in the eclipses, 2 ionized line. And as you know, if you have a simultaneous measurement, the line ratios will allow you to get a direct estimate about the temperature. In addition, we have the 10747 angstrom line, which has the capabilities in addition to the spectropolarimetric observations. So 10747 will also allow you to do another spectroscopy also in its default mode. But the spectropolarimetry, of course, will need a lot of time because it has a retarder. It has, targeted for better than 10 to the power minus 4 as a polarimetric accuracy. So it should give us all the Stokes parameters, provided we have sufficient signal. I must point out this spectroscopic field of view from 1.05 to 1.5 is going to be hugely challenging because of the scatter. And as you know, the internal occulter does produce a lot of scatter, and this is our first attempt. In fact, that also demands a very big, smooth surface. On the primary mirror, which was built for the first time in India with certain accuracy in one of the ISRO labs. We demanded about 1 angstrom, but I understand it is slightly inferior than that, about 2.5 angstrom micro roughness of the primary mirror. So there are a lot of scatter experiments going on from the test data. So that will eventually allow us to say what kind of magnetic map we will be able to produce, how much time it will take. So again, with the punch, I think the continuum channel, of course, it just supplements the inner corona and against the outer corona. But also with the NIFI, and the coronagraph observation jointly will allow us to do probe all these blobs and transients, whatever we have been discussing in last couple of days, to have a better source identification and also better thermodynamical properties of these structures. So that would be my take. And also we understand that this is a proposal driven thing. So we have flexibility in terms of exposure times, in terms of the choosing 1 slit against the 4 slits and so on, to reduce the data volume and so on. Having said that, there is also the SUIT instrument, which has the magnesium channel. So we will have pretty good coverage there as well. In fact, it has a 4K by 4K CCD, which was taken from RAL, the chip. So that way, that also covers you a bit of overlap with the SUVI as well. But of course, this is magnesium. We don't have any coronal lines in SOOT instrument. So I think there are really huge potential of joint observing campaigns.
Thank you. All right, we have Noor and then Sarah, and then I've got a question too.
I have a question for Peg. So the decadal is by nature a national exercise. However, most of the mission concepts that were submitted, they rely on international collaboration later on. So did NASA communicate any recommendation to the steering committee to take into account the international component for these mission concepts? And if that is done, how it is done?
So yes, but I can't, I'd have to remind myself exactly how. I do know that Nikki went out and invited international partners to also submit white papers. So we did solicit input from international partners as well. But the degree to which the decadal survey is looking at the international aspects is a good question, and I'm not sure the answer to that.
All right, Sarah.
Okay. Last question I had for somebody on the panel. Yes. It's not up there, so I have to. Oh, there it is. Okay. Peg, what advice would you give? We have a lot of early career scientists here, and obviously they know something about getting involved in a NASA mission because they're here. But do you have any other advice to give people about, how to get connected to NASA science and missions?
So first I would say, I acknowledge that you have to do your science, and I'm not good, so what we're talking about are what are other ways to get connected. And for those of you who are involved in Punch, you certainly have a wealth of connections from that, and hopefully you're seeing ideas. One thing I will say is if you ask, if you volunteer, if you put your hand up and go try to meet people, you'll generally be successful in getting people's attention. People love to talk about what they do and share a little bit about their job. What sounds self-serving, but I think is valid, is you can always volunteer to support panels, RNA panels. If you're not experienced, to serve as an executive secretary on a peer review panel is so needed, so welcome, and it actually is a way to get to know people. And we're starting to do more in person again after COVID, so that you really do have the opportunity to spend time with people.
Thank you. We have a quick follow-up.
So, this is also about early career scientists. Some institutions, in particular universities, do not allow students, postdocs in particular, and early career scientists to be PIs on their proposal, and somebody else has to sign it on it. Can NASA do anything about this? It's totally unjustified. And some of these folks really suffer a lot from it.
So I think that Bill Matthews is the PI on many, many proposals, because isn't that the case at Delaware, where you have to be a professor to be the PI, submitting PI?
I just got an email from Eric Posner talking about that.
Is that right?
Yeah, I have my own research programs that I'm PI of, but there's also an even larger number of projects that are funded by NASA Space Grant, and I'm required by NASA OSTEM, Office of STEM Retention and Development, OSTEM I think it's called, which is not your section, right? That's
yes.
The other side of the hall or something. They require that the Space Grant Director be PI on all NASA EPSCoR proposals. I don't even know what most of them are about, but I have to be the PI on them. I push paper around.
So I think I hear about this being a problem. To the extent that it's an institutional requirement, I'm not sure what we can do, but what I see us doing is try to acknowledge and create a lead scientist role, or there's a role that indicates a lead scientist who's in addition to the PI. So, yes? Science PI, yeah, thanks. So that's one thing I know we've made an effort to make that a thing.
We're going to go to Samaya and then Lika. I think Samaya's is too.
Okay, yeah. This is kind of a convoluted question, but since you guys are here, I thought I'd ask. So I was wondering if there's something coming down the pipeline. It would be great to see NASA headquarters or people in your position push for more ways to reinvest in the community. We talk about opening science. So for instance, pushing conferences or subsections to host meetings in more economically impacted areas, maybe seeking out journal publishers that are not just the big, people who are part of the big machine. So is there anything coming down the pipeline when we talk about opening science and making more opening access to really reduce the amount of traction in these old-fashioned kind of ways of doing science and really opening up the community to the rest of the United States?
So I can just tell you, we talk about it a lot, and the two ideas you just suggested weren't on the table yet. But we look at the fact that just even the number of proposers for beyond the usual suspects is so small, and how do we reach out? And there are bridge programs and there are various things, but your idea of just go hold a meeting in a place too, I think,
Just hold a meeting at an AGU at an institution would impact so much of the research being done there. It would be
so
really impactful.
I will invite you to send me your ideas, and I can definitely share them. We do talk about it, and we are still hunting for ideas.
Mike? Okay.
Yeah, they are great concepts, and that we have the DEIA group, right, who are constantly looking for ideas. So yeah, I think they can always be tried out as examples. I was going to go back to the question that was asked earlier: what do we do with universities or institutions that do not allow early career PIs? At least I'll say we have gotten around that issue sometimes by having exactly what you were saying, Peg, institutional PI. So Stanford was just well known for that, and for years and years, So basically, even at program scientist level, we can talk to the institution and say, you're going to have an institutional PI, but your actual PI is whatever name we give them, task lead or something. So, and the budget is kind of really taken care of by them and the institution. The administrative side is aware of that. But they don't know what to change, and we don't know how to manage it. So it's a huge effort, but we still work on it.
Yeah, we have two follow-ups. We have Larry, and then Bill would like to say something.
I want to follow up to the comment earlier about how do we engage unrepresented universities. This is something we talk about a lot at Goddard, because we do have resources at Goddard. The issue, though, is that it's one-on-one. It's just one person at a time. And you've got to make that personal connection with the university or wherever you're at, or they're not going to send their students to you. And that requires a tremendous amount of effort that I know Nikki and I really care about. We make an effort on it. But we're only two people, for example, and there are people at Goddard that do it as well. But you make one connection a year. Or maybe you're likely to make two connections a year, and you bring them in. And it's just, you can't just put up a flyer and say, please come work for NASA. You got to make those connections, and that requires a lot of grunt work, a lot of legwork, and I think that's why it's so difficult.
So, Peg, my earlier comment had mainly to do with EPSCoR, and that's not anything that we can do about. Maybe you could, but we can't. But actually, with regards to postdocs and so forth being PIs, about 10 or 12 years ago, we couldn't do that at Delaware. And I had a postdoc that probably a lot of you know now, who I wanted to be a PI. And I actually went to the dean and I made them create a form, because the issue was the responsibility of the institution. If the person quits or whatever, who's going to take over? So basically, there's a form that I signed that we sort of invented, where I said I would take over responsibility if this postdoc didn't meet the obligations. And that one went through, and we've had 3 or 4 or maybe more since then. It is possible, but you have to push the deans and so forth to do it.
So sharing that, if we see it elsewhere, saying, okay, there are some universities that have solved this problem, that's something we could do. Yeah.
If you want, I could get you a blank form for you to send out.
Sure.
Excellent. I think the discussion is lively, but we're at the bottom of the hour, and Sarah and I are the only thing standing between you and hors d'oeuvres. So let's thank our speakers one more time for a great session. Before I hand over to Sarah, I want to especially call out both Peg for being here. I know that headquarters is extraordinarily busy right now. And Dipankar for staying up really late. So thank you for being here, Dipankar.
My pleasure, my pleasure.
All right. Okay, I just have some thank yous. But actually, before I do that, Iver had a question, which I can address. He asked about whether the Slido was going to be available, and the answer is yes. And in fact, all of these talks have been recorded, and the posters are available as e-posters. And the Slido will be open for continued comments for a while, right, Kelvin? And we will ultimately post this. This is what we did last time. So we have a record, so that's a very cool thing. Okay, so many people to thank. First of all, everybody who is here at this meeting, and that includes the remote participants, and Kelvin has told me that we've had hundreds every day of unique viewers of our YouTube stream, which is very cool. The speakers, oh yes. The speakers, we've had such amazing talks, but also the discussion has been wonderful, and so the audience's questions is part of that, so the program has been wonderful. Thank you. In terms of the organization, the scientific organization was absolutely done in collaboration with the working group leads. Working group leads, stand up please if you're in the room now. You all have seen them, they have been so active. This has been a really exciting meeting because of the embedded outreach connection. Sherilyn Morrow here in the back of the room, thank you. And we have been enriched by the participation of our outreach group, and I want to make a special thank you to Brianna and Jason for that super cool Fiske outreach event we had last night. That was so much fun. And I loved the interpretive dance. I loved it. Okay, so coming into the room, this has been a smoothly running show, and that is thanks to Kelvin and to Fletch in the back. Thank you so much. And I think I'm going to end with the person who has seen me through all of the last month of God knows how many emails and meet sessions, Carrie Don. Thank you so much. So now I'm going to hand it off to Craig for the final thank yous and to close us out.
All right. The person that Sarah can't ask for a hand for is herself. Sarah has been tireless. So. Let's see. There are a couple of other team members I want to call out specifically who are the Punch Associate investigators who have really not just been an outreach project, but really have been essential to getting us where we are. So I'm going to name the ones that are in the room, and I'd like you guys to stand up. That's Raphael again, Rohit, Gilly, we have Chicho Pecora, yep, Lena Provernikova. Well done, each of you, just really terrific. And of course, not here, but missed are Bea Gallardo-Lacourt and Yan Yang. So let's give them a remote hand. This whole process is echoing, to be honest, much more arduous process that's going on down in San Antonio right now with the Punch development team, who are in integration and test, both in San Antonio and in Washington, D.C. So thanks to everyone who's working hard to get us into space. And then, of course, Ronnie Killo, our project manager, who couldn't be present, but is doing well. He's out of the hospital and walking around. And, of course, on the NASA side, we have Tyrone Dillard, our mission manager. We have David Cheney, sorry, David. David Cheney and Lika, who are our reps at various parts of the agency, so thank you. And finally, I already thanked you for coming, but now I'll thank you for the help, is Peg Loose. So thanks. So, something we can really cheer about, let's go eat.